Hi, hi, hi. So the last time and the time before that, we defined matrix multiplication, and what we're going to do now is we're going to look at the way that the parts of the two matrices combine, that to try to get some insight into how it works, kind of on a lower level, on a combinatorial level. So the check-in is a little bit of a preview of that, and maybe a little bit of a lighter day today. Just people often find that the kind of how the parts go together as a little bit more fun than maybe some of the more theory-oriented stuff. Okay, very good. So I have a matrix, and I'm going to multiply it by these vectors. So very straightforward. So let's have a whack here, if I can remember the parts. Let's see, the matrix is 1, 3, 2, 4. 1, 3, 2, 4. And I'm going to multiply it by, let's see, 1, 3, 2, 4, multiplied by the vector 1 minus 3. Okay, so 1 times 1, 3 times minus 3, I get to minus 8. 2 times 1, 4 times minus 3, so minus 10. And similarly, 1, 3, 2, 4 by 4, 0. 1 times 4, 3 times 0. 2 times 4, 4 times 0. So already we see a little bit of what's coming is the fact that this is a 0 here means that the second component, the 3 and the 4, in the dot product plays no role. Or the fact that this is a 0 here means that all I do is multiply the first component, the 1 and the 2, by 4. So I can think of how the parts combine together as giving me some insight into how linear maps act. Another one, 1, 3, 2, 4, and minus 2, minus 2. So 1 by minus 2 and 3 by minus 2, and so I get to minus 8. 2 by minus 2 and 4 by minus 2 gives me minus 12. And again, this is a minus 2 and minus 2, so I can just think that I took the 1 and the 3, which add to 4, and I multiplied both of them by minus 2 until when all the smoke clears, I end up with 4 times minus 2 is minus 8. So I can understand the results here somehow as some simple combinatorics of the input parts on some level. And then B. B asked me, I didn't really talk about B when it was up to B asked me to multiply G, the starting matrix G, by the matrix. Do you see the matrix is made up by putting the vectors in as parts? Okay, so if you write down 1, 3, 2, 4, and then you put the vectors in as parts, minus 3, 4, 0, minus 2, minus 2, then you won't be astonished to find that the output is you just put these vectors in as parts, minus 8, minus 10. And just before I go any further, because I'm taking 1, 3 by 1 minus 3, and then I'm taking 2, 4 by 1 minus 3, and so I'm seeing that I'm just getting the output parts, 4, 8, minus 8, minus 12. So we emphasize, when we define matrix multiplication, we emphasize its connection to linear maps because I wanted to talk about how the somewhat strange way that the two matrices combine makes sense. It's not arbitrary. It's not one of those things, never mind why it's true. Not a big believer in never mind why it's true. It all makes perfectly good sense if you look at it from the ground up and look at it in the right way. But I'm not proud. We can step back and say, okay, having defined it, having understood why it is that way, we can now try to think about how the parts combine on a kind of mechanical level, and that's what we're going to do today. Okay, very good. Let's see here. Let's bring up the material for the day. Okay, so we're thinking about the mechanics of matrix multiplication, and we're going to think about sort of how the parts combine, and you know, on some level. The combinatorics of multiplication that I'm trying to describe that when you first see matrix multiplication, you say to yourself that, okay, you can combine those numbers in that way if you like, but why do you like it? So we spent the section there, the prior section, spent two videos on it, trying to say it's defined this way because it makes sense. It needs to be defined this way to represent composition. Then we step back and we think about we think about now, having understood why it is that way, we think about, okay, well, what way is it exactly? So if you look at the product GH, what is the IJ entry in the product GH? Well, here it is. I wrote it out, copied from the slide a couple of videos ago. But what marks these combinations, you're taking the dot product of the rows of G with the columns of H, and what marks this combination, can you see I've got in red there, it's red, right? Yeah, it comes out red in the video too. Is that the ones match, the twos match, etc., all the way down to the R's match. Maybe you remember R's from the previous video. See the I and the J, the I and the J, the I and the J. That's this I and this J. And in this example, I have a second row and a third column. They combine to make the 2, 3 entry. So I is 2, J is 3. You take the first thing from the second row, that's the 1 and the 1. First thing from the second row, combine it with the first thing from the second column, 0 times 6. Take the second thing from the second row, combine it with the second thing from the second column, that's this 2 and this 2. So we can view this in at least two different ways. One way is to understand it that the left matrix acts by multiplying its rows into the columns of the right matrix. And that's the example that we finished with on the check-in. Or it also will be fruitful for us to understand this as the right matrix is using its columns to act on the rows of the left matrix. We'll look at them both ways. So the matrix on the left is acting row-wise. The matrix on the right is acting column-wise. So in a product of two matrices G and H, the columns of GH are, you take G times the columns of H. And again, that's what we saw in the check-in. The columns of GH are G times the columns of H, the matrix vector product, G times the columns of H. Or, if you like, it's perfectly correct to say that the rows of GH are formed by taking the rows of G times the rows of H. Excuse me, the rows of G times the matrix H. And that's simply the previous slide's picture. You can imagine that the 4, 5 and the 6, 7 are multiplying by the dot producting by the rows. Okay, now the way to sort of make sense of that theorem that we just saw is to break it down to very simple cases, and then put the very simple cases together. So that's what we're going to do. So a matrix that's all zeros except for a single one. That's a pretty simple case. A matrix that's all zeros except for a single one in the IJ entry is called the IJ unit matrix. Sometimes called matrix unit, but I'm going to call it the unit matrix. So here's the 2, 1 unit 2 by 3 matrix. So it's got a 1 in the 2, 1 entry. And I just put some matrix over here. And what you see is that the row of zeros, it makes 0, 0, 0. The second row has a 1, 0, 0. So 1 times 2, 0 times 5, 0 times 7. You're picking out the 2. 1 times 1, 0 times 6, 0 times 8. You're picking out the 1. 1 times 3, 0 times 4, 0 times 9. You're picking out the 3. So that matrix here, when acting from the left, copies row 1 of the multiplicand, the 2, 1, 3, into row 2 of the result. So it copies row 1 of the thing it's acting on. It picks out the 2, the 1, and the 3, and it copies it into the second row of the result. So it acts here on, well, I'm thinking of the unit matrix as acting on the matrix on the right. On the other hand, if I put the 2, 1 unit matrix on the right-hand side, what does it do? Why, it picks out a column. If you do this product here, you end up with the 4 and the 5 there. Let's just do, so if you take the row 3, 4 dotted with the column 0, 1, of course it picks out the 4. If you take 6, 5, the row 6, 5, and dot it with the column 0, 1, of course it picks out the 5. So if you put 2, 1, the 2, 1 unit matrix on the right, it will pick out column 2 of the first matrix, the matrix on the left, and put it in column 1 of the result. Okay? If you change the unit matrix to make it no longer a 1, but instead you multiply it, in this case by 3, all it does is make everything 3 times as large. So if you have a matrix that is mostly zeros, almost, except for 1, zeros, then you can understand the action of that matrix, either from the left or from the right, is the action of the unit matrix, and then just rescale. So we can understand how these matrices act by thinking of them as either acting from the left or from the right. From the left, they pick out rows. From the right, they pick out columns. If you rescale it so it's 3 times as bigger, it picks out the row or column and multiplies it by 3. Moving up to the sort of next level of complexity here, what if you have more than one entry? So the main diagonal, or sometimes called principal diagonal, and often just simply diagonal, of a square matrix goes from the upper left to the lower right, and an identity matrix is a square matrix where every entry is 0 except for ones on the main diagonal. Now, main diagonal is only defined for us for the square matrix. Okay, so the product with the identity matrix just simply returns the thing you're multiplying it by. So I'm understanding this 1, 0, 0, 1 as acting on this 3, 2 minus 1, 5. And how is this related to the unit matrix from the, well, it's related this way. 1, 0 picks out the 3 and the 2. 1, 0 by 3 minus 1 picks out the 3. 1, 0 by 2, 5 picks out the 2. So 1, 0 picks out the 3 and the 2. 0, 1 picks out the minus 1 and the 5. So the unit, this idea from unit matrices that it picks out rows is exactly what we're looking at here. If you pick out each row exactly, you do that with an identity matrix, and you just simply copy from the one place to the other. Okay, what does it do when it's acting from the right? It does exactly the same thing. 3, 2 by 1, 0 picks out the 3. Minus 1, 5 by 1, 0 picks out the minus 1. 3, 2 by 0, 1 picks out the 2. Minus 1, 5 by 0, 1 picks out the 5. So this identity matrix here or here, acting either from the right or from the left, picks out each entry and drops it back. In other words, leaves the multiplicand unchanged. All right, so just like with unit matrices, we thought, well, what happens if we change the number from 1 to something else? So, okay, there we go. A diagonal matrix is one that's square and has zeros everywhere that isn't the main diagonal, but on the diagonal are non-zero numbers, or some of them could be 0, also potentially non-zero numbers. What's it going to do? Well, I think you can guess what it's going to do. The 2, 0 will pick out the 3 and the 2 and multiply them by 2. The 0, 3 will pick out the minus 1 and the 5 and multiply them by 3. So that's what this diagonal matrix does, acting from the left. What does it do acting from the right? The 2, 0, well, the 3, 2 by the 2, 0 picks out the 3 and multiplies it by 2. Minus 1, 5 by the 2, 0 picks out the minus 1 and multiplies it by 2. It takes the column and multiplies it by 2. The 0, 3, it takes the columns and multiplies. The 0, 3 takes the column and multiplies it by 3. The 2 got multiplied by 3. The 5 got multiplied by 3. So again, we can understand these things acting either from the left or from the right. From the left, they act on the rows. From the right, they act on the columns. So we're starting with kind of relatively simple matrices, trying to understand the parts and how do they act, and of course we're building up to more and more complicated matrices. Next step up, since we can multiply the rows or the columns of a matrix by some number, next step up is to move them around. permutation matrix is square and all zeros except for a single one in each row and column. That is, I'm going to pick out not necessarily that exact row or that exact column. I'll pick out whatever row or column I like. So here's an example. 0, 1, 0, 1, 0, 0, 0, 0, 1. That's like the identity matrix rows, except they're not in the identity matrix order. So instead of picking out the first row, this fellow's going to pick out the second row. And sure enough, there's 4, 5, 6. And here, in the identity matrix, this would be the first row, and it would pick out the first row. But here, it's not the first row, it's the second row. So it puts the 1, 2, 3 in the second row of the outcome. Down here, 0, 0, 1 picks out the third row and puts it in the third row of the outcome unchanged. So this will swap the first and second rows. From the right, you won't be astonished to hear that it acts on columns. It swaps the columns. So, instead of the first column being 1, 4, 7, the first column is now 2, 5, 8 because this took the second column and dropped it into the first. And here took the first column, 1, 4, 7, and dropped it into the second, and the third column is unchanged. So it's called a permutation matrix because it permutes, it shuffles around either the rows or the columns depending on which side it's acting. That's all. So we can move things around in these matrices, make them bigger or smaller, move them around from place to place by choosing either the appropriate row acting or column acting matrix. Can you do all of Gauss's method? And the answer, of course, is you can. Of course you can. The elementary reduction matrices, or just elementary matrices, result from applying a single Gaussian operation to an identity matrix. Let me go back to here. Think of this as being the identity matrix with one Gaussian operation applied. I swapped the first two rows. That gave me, if I took the identity matrix and swapped the first two rows, I get this. The action of this matrix is to swap rows. That's what this says. If you take the identity matrix and swap two rows, you get a matrix that performs that step. If you take the identity matrix and multiply row I by k, you get a matrix that will perform that step. Now, combining k times row I plus row j, you get a matrix that combines k times row I plus row j. So here's an example. Suppose I want to multiply the second row by 1/2. The regular Gauss's method step of multiplying the second row by 1/2, which is what we would have done first week of class, we would have done to this matrix right here. Okay, so you take the identity matrix and multiply its row by 1/2. Excuse me, its second row by 1/2. There you go. What about if I take this matrix down here and I want to take -2 row 1, add to row 3? Well, I write down the identity matrix. To the identity matrix, I apply the operation -2 row 1 plus row 3. And that's what I put here. That's this matrix right here, only done for this specific example. If you take this matrix and write it on the left and perform matrix multiplication, let's have a look. 1, 0, 0 picks out the 1, 3, 0. 0, 1, 0 picks out the 0, 2, 5. 2, 0, minus 1 does the following. It takes -2 times 1 and adds to 2. It takes -2 times 3 and adds to 1. It takes -2 times 0 and adds to 1. It does the Gauss's method step. That's what it does. The lemma says that the operations that we just saw, the matrices that we just saw, perform the required Gaussian reduction steps. That if H is related to G by taking row I and multiplying it by K, then that matrix from the left will perform that operation. If H is related to G by swapping two rows, then this matrix will perform that operation. If H is related to G by the relationship that K row I added to row J, then this matrix will perform that operation. And I wrote for the proof, I wrote clear because you just do a couple of examples and you say, so, oh yes, that is clear. So we can perform Gauss's method. You could say, well, it's an awful hard way to perform Gauss's method. Okay, but nonetheless true. We can perform Gauss's method with these matrix multiplication steps, and that's the corollary. For any matrix H, if you give me a starting matrix H, I can perform Gauss's method by a sequence of matrix multiplications. First multiply H by R1, then multiply the result by R2, then multiply the result by R3, etc., all the way out to the result by capital R sub R. And I'll end up in reduced echelon form, if you like. You can just be in echelon form, but I'm going to happen to need reduced echelon form. So that's why I quoted the result the way I quoted it. Here's an example, but I wonder if I need an example. I took 1, 2, 4, 3 and did some Gauss's method steps to get the reduced echelon form. Minus 4 row 1 plus row 2, minus 1/5 row 2, minus 2 row 2 plus row 1, and I ended up with this reduced echelon form. I didn't include the intermediate matrices because do I need to? I'm claiming that I can do that as a matrix product. So here I did. There's the 1, 2, 4, 3. See it there? First thing I want to do is minus 4 row 1 plus row 2. So right here, written next to, got to get the order right, written next to, immediately next to, the matrix it's acting on, is if you took the 2 by 2 identity matrix and did minus 4 row 1 plus row 2 to it. This is the result of taking the 2 by 2 identity matrix and doing minus 4 row 1 plus row 2 to the 2 by 2 identity matrix. Next thing I wanted to do was minus 1/5 row 2, so it goes next, reading, I know it's in the wrong direction, but it's in the right direction. That is, we're going out, inside out. This is what happens if you take minus 1/5 row 2 to the identity matrix. And this is what happens if you take minus 2 row 2 plus row 1 to the identity matrix. This is the notation written all out here, but in some ways this is clear. So I can do Gauss-Jordan reduction as a matrix product. And again, a person doesn't see right away why I'm especially keen, but we'll see it in the next section. Another example, bigger example. I wrote down an augmented matrix. I'm going to perform the Gauss's method steps. Minus 2 row 1 plus row 2. This is if you take the 3 by 3 identity matrix, it's got 1s down the diagonal, 0s everywhere else. You take the 3 by 3 identity matrix and you perform on it minus 2 row 1 plus row 2. You get this. When you do the mechanics of multiplying from the left, it affects the rows and it affects it in this way. Next step is to take this matrix, we would think to swap rows 2 and 3. Okay? So I swap rows 2 and 3 by writing down the identity matrix, except that it's got rows 2 and 3 swapped. When you do the matrix multiplication, you end up with the swap of rows 2 and 3. And the result is I went from the augmented matrix to echelon form through this sequence of matrix multiplications. Remembering to get the order right, the thing done first gets written nearest to the matrix you're acting on. The thing done next gets written next nearest. Okay, now for next time, we're going to use that result to be able to do matrix inverse. Matrix inverse is just like when you take sort of 7 times x equals 4, and you solve that equation by multiplying both sides by 1/7. Well, we're going to have a matrix equation, really a linear system that is written out in matrices, a matrix equation, and we're going to try to solve it by multiplying both sides by the opposite, the multiplicative opposite, technically the multiplicative inverse of the matrix. Okay, very good. See you then next time. Hi. Okay, last time we talked about the mechanics of matrix multiplication. We talked about how the parts of the two matrices combine and what we can learn about how matrix multiplication works by thinking about how the matrix from the left acts sort of column-wise and matrix from the right, the matrix from the left acts sort of row-wise and matrix from the right acts sort of column-wise. And so, of course, the check-in has to do with that. So let's see, let's have a look here. It says they have a given matrix, just kind of a made up, not too hard matrix, and it says find an H to make this come out. So I'm going to think about how the parts on the left combine with the parts on the right, and then I'm going to see what happens. Okay, okay, great. All right, so let's see. It goes. It is 1, 3, 2, 4. And I want that to be multiplied by another 2 by 2 matrix, A, B, C, D, and it's supposed to come out to be the identity matrix, 1, 0, 0, 1. So if you think about how the parts combine, of course what happens is the row 1, 3 combines with the column AC to give this 1. So I'm simply looking at A plus 3C equals 1, and of course a person can guess where I'm going with this. We're going to do Gauss's method on a linear system. Likewise, the 1 and the 3 combines with the B and the D to give me what B plus 3D, B plus 3D equals this 0 over here. And then you just proceed in that way. 2A plus 4C, 2A plus 4C equals 0, and then the last one is the 2 and the 4 combined with the B and the D, so 2B plus 4D equals 1. And it's a linear system, so we know exactly what to do. Off we go. So I guess I'm going to do what minus 2 row 1 plus row 2. And then my notes say I'm also going to do minus 2 row 2 plus row 4. And I'll spare you the details of exactly what happens there. Row 2 plus row 4. Row 4. I'll spare you the details of exactly what happens there. I end up with, I'll copy it down here, it's A plus 3C equals 1. A plus 3C equals 1. And then B plus 3D equals 0. Plus 3D equals 0. And then I happen to get minus 2C equals minus 2. Minus 2C equals minus 2. And then minus 2D. Minus 2D is equal to 1. I'm not just simply sparing you the agony of watching me do arithmetic, which is agonizing. So I get from the bottom line that D is minus a half. D is minus a half. C is 1 here. C is 1. And then I'm looking here at B plus 3D equals 0. So I get that what B is 3 halves. Okay, and then the last one is A plus 3 times 1 gives 1. So A is minus 2. Okay, and then so the conclusion is that what the 1, 3, 2, 4 minus 2, B is 3 halves, C is 1, and D is minus a half, works out to be 1, 0, 0, 1. And just to check one, how about if we check this 3 halves here? Just pick one at random. So I need the 1, 3 combined with the 3 halves minus 1 half. So 1 times 3 halves, 3 times minus 1 half. Yes, sure enough. Sure enough. Okay. Okay. Okay, so we can understand how the parts combine, and we can answer questions about the matrices entirely independent of, entirely without regard to, the underlying linear maps. It's not that I'm throwing away the underlying linear maps at this point. I'm only pointing out that one thing a person can do to solve problems is to just think about how the parts combine, that's all, and ignore the linear maps. That's perfectly, in lots of problems, that's perfectly practical. Just because we take the point of view in this class that linear maps primary, and that matrices are a computational aspect, computational shade, the computation, the way of computing linear maps, doesn't mean that matrices are just baloney and we'll never think about them again. Rather, it's more complicated than that. Then when matrices are the way to think about something, then we'll think about them that way. That's perfectly sensible. Okay. Okay, and so what we're turning to today then is we're turning to, as sort of hinted at by the check-in, we're turning to thinking about the matrix inverses. We're turning to think about finding the inverses. We've been taking linear maps as primary, so we're thinking of the functions as the things that are the main object of study. And we've done function multiplication by a scalar, so you can take 3f. We've done function addition, so you can take f plus g. We've done a function composition, so you can take f composed with g. And here we are doing function inverses. Okay, so we're going to finish this section by thinking about how to represent the inverse of a linear map. So basically the goal is, if we have a linear map H with an inverse, we want to find the relationship between the representation of H and the representation of H inverse. Did you notice that the bases switched here? This was starting at B, ending at D, but of course the inverse takes you back in the other direction, so the inverse is going to have starting at D, ending at B. Okay, so a little quick review on inverses. It's not not always right on the top of a person's head. So I want to think particularly about two maps. I'm going to take the routine projection map from 3 space to 2 space. So you project down to the xy plane, and there it is. XYZ goes to xy. And then I also want to think about the embedding map. That's a Greek letter iota. It's like an I with no dot on top. So the missing dot is intentional. Anyway, so we take xy and we send it to some place in R3. Now, if I want that to be a linear map, then 0, 0 has to go to 0, 0, 0. So that's why I took the third entry to be 0. If you sent xy to xy1, it wouldn't be a linear map. Anyway, so I got what I got here. Now, it's clear that if you do iota first, if you do iota first, and then pi, you go from xy to xy0 and then back to xy again. So it's clear that the composition iota first followed by pi, remember they go in the opposite order than the order that you write them. Iota first followed by pi is the identity map. Takes you from the 2 tall column vector xy to the 2 tall column vector xy via 3 space, but anyway, takes you from the vector v in R squared back to the vector v. But the other way, not so. If you're going to do the xyz goes to xy and then goes to xy0, if you start with xy1, you're in trouble. You don't end up back where you started from. So what we're saying here is that this property of the fact that in some sense pi cancels iota can change when you move them around, when you move the functions around so that they come in the opposite order. Order matters for function application. And of course, we saw that before when we did that matrix multiplication doesn't commute. We specifically focused on the fact that that's simply because function application doesn't commute. Here's another example, but it's a special case, but it's an important one for us. Okay, so again, if you go from xy to xy0, and then you go from xyz to xy, you cancel, the whole thing cancels out, you end up going from xy to xy. That's the identity map. We say that iota is a right inverse of pi, or pi is a left inverse of iota. The two mean the same thing. That if you compose them in that order, you'll get the identity map. But as we were just talking about, if you do the opposite, if you do pi first and then iota, it doesn't necessarily work. Here's an example of it not working. So you have to call it left inverse and right inverse because it only works on one side. In fact, pi has no left inverse at all. If you're going to go xyz to xy and then somehow back to xyz, the question is, what's z? Well, that's, you can't have f take x, y, z to each one of x, y 0 and x, y 1 and x, y 2 and x, y. F can't do that. That would make f not a function. Functions have a unique output. So it's possible for a function to have a right inverse but no left inverse, or to have a left inverse but no right inverse. Furthermore, a function can also fail to have an inverse on either side. An example is the zero transformation on R squared. If you send every vector v, every x, y, too tall vector v, to 0, how are you going to invert that? If your input is 0, what's your output? Well, it could be that you started at 1, 2, but it could be that you started at 2, 1. Okay, so a function can have a right inverse but no left inverse. A function can have a left inverse but no right inverse. And a function can also fail to have a left inverse, or fail to have a right inverse kind of stuff. So functions are not like numbers. 7 has a 1 over 7. 4 has a 1 over 4. For that matter, 1 over 3 has a 3. But functions can be different. It can be that if you do them from one side, it works. If you do it from the other side, it doesn't. Or it can be that like the number 0, there just is no thing that cancels the function. So function inverse maybe calls for a little review, a little bit different than a person might be used to. Some functions, however, particularly convenient functions, have two-sided inverse. That is, a function that's inverse from both the left and the right. And an obvious example is if you look at the linear function, v goes to 2v, I won't even tell you the input and output spaces. If v goes to 2v, then the two-sided inverse is v goes to half v. If you first double vectors and then you half them, you end up back where you started from. The appendix shows that a function has a two-sided inverse if and only if it's both 1-to-1 and onto. So, a function has a two-sided inverse if and only if it's an isomorphism. If a function has a two-sided inverse, like this function does, doubling and then halving again, doubling has a two-sided inverse, namely halving. If a function has a two-sided inverse, then we just call it the inverse, and we write superscript 1 for the notation. I know there's a potential confusion with 1 over, but this is the standard notation. With linear maps, we'll never want to write 1 over, or at least hardly ever want to say such a thing as 1 over. Instead, inverse of the composition related inverse, the map that when you compose with the original gives you back the identity, that's what you almost always wanted. So that's what we use the notation for. So in addition, you might remember that we had a result that said if a linear map has a two-sided inverse, then that inverse is also linear. We did it in the section on isomorphisms because we needed it there, and we've just remarked that that two-sided inverse is the same thing as isomorphism. But anyway, if a linear map has a two-sided inverse, then the inverse is also a linear map. We saw this up here. V goes to 2v is linear. Also linear is v goes to half v. It's only an example, but it's an illustration. Okay, so the program for what it is we want to accomplish in this chapter becomes: you give me a matrix H, and I try to find a G that cancels it. Again, you give me a matrix H, and I try to find a G that cancels it, where G times H is the identity. In some way analogous to the sort of 7th grade problem of you give me a 7 and I find a number that cancels it, 1 over 7. The point being that 1 over 7 times 7 is the identity element with respect to regular multiplication, the number 1. And of course, it's a right inverse matrix if HG is the identity. And if a matrix H has a two-sided inverse, then we call it an invertible matrix, and the two-sided inverse is denoted H with a superscript 1, H with a superscript 1. Now, so that's the idea of this chapter. So again, we take the functions as primary and the matrices as computational aspects of the function. Doesn't mean we throw them away, but it means that we got to take something as primary. Our point of view is that the function is primary. A person sees from how the functions work how the matrices are going to work. Sometimes it will be the case that you can find a left inverse matrix that isn't a right inverse. Sometimes it'll be the case you can find a right inverse that isn't a left inverse. Sometimes it'll be the case, often it'll be the case that you find a matrix that is a two-sided inverse. In that case, those are particularly convenient matrices, and a matrix of the two-sided inverse is called an invertible matrix, and we denote it with H superscript minus 1. And so having described what the point of this chapter is, we want to represent from the representation of the map, we want to represent the map's inverse. Then the next thing to do is to describe what the point is. Why would you want to do such a crazy thing? So here's an illustration of a matrix and a matrix inverse. 2, 5, 1, 3 is just some cockamamie matrix. Here's the inverse. 3 minus 5 minus 1, 2, and you see that when you multiply them together, you get the identity. A person would say, how do you get that? So, well, of course, we can only do one thing at a time. We're not going to talk about that today. We'll talk about that next video. But we do want to close today with saying, why? Given H, why would you want H inverse? What's the point? So here's the idea. Remember the 2, 5, 1, 3? If you have a linear system whose matrix of coefficients is 2, 5, 1, 3, you can use the H I just figured on the prior slide. You can use it to cancel the 2, 5, 1, 3. Let's focus on the left-hand side of what's happening here. 3 minus 5 minus 1, 2 by the 2, 5, 1, 3 gives you the identity matrix. That's the point of the 3 minus 5 minus 1, 2. That's the point. Why do I want the identity? Because when you multiply the identity by xy, goes away. So in short, this is like 7 and 1/7. This is like 3 and 1/3. This is like 1/4 and 4. They cancel each other, and when all the smoke clears, you just simply have the variable over there. So it's like 7th grade algebra. Okay, now enough of the left side. I'll look at the right side. Of course, when I took this original equation up here and I multiplied both sides by the 3 minus 5 minus 1, 2, of course, you have to do the same thing to both sides. Notice that I do it from the left because with matrices, the order in which you do them, left versus right, matters. So if I did it from the left over here, I got to do it from the left over here. Anyway, I did it from the left. When you do the combination, it's not very interesting. You get a minus 59 and a 23, just some cockamamie numbers, and those numbers are the answer. So if you give me a matrix equation and I know there's an inverse, then finding the answer is trivial. You just take the inverse and multiply it by the constants. That's why I want the inverse, because it makes solving a linear system trivial. If you know the matrix inverse, then it makes solving a linear system easy and quick. Okay. Now, of course, next time we're going to talk about some more here with solving systems, and I got to show you how you figure out given the matrix, how you figure out what the inverse is, and indeed if there is an inverse. But that's next time. Okay, very good. Hi. Okay, last time, of course, we talked about matrix inverses, and we specifically took the point of view that matrix inverses are about functions, like so much in this class, that we take functions as the primary object and that we take the matrices as kind of the computational aspect of functions. That doesn't mean that matrices are foolish or we look down on them. It just means that something has to come first and we take functions to come first. We've seen a couple of examples of that happening and we'll see more today. But so anyway, the check-in, of course, is about inverses, and specifically it talks about the inverse of a function. So let's get to it. Okay, so let's see what I got for a function here. F is, F takes the plane to the plane. Okay, and the action is what? xy goes to, it's x plus 3y, x plus 3y, and 2x plus 4y. All right, and then we're looking for the inverse, g. So g has to start at f's codomain, so f's range, r squared, and has to end up where f started. Again, those are the plane in all four cases, but anyway, that's the idea. And rather than say xy here, which of course would be perfectly sensible, but I'm going to say, in the hopes that it'll cause less confusion, x hat and y hat. X hat and y hat. So I don't know what they are. If I knew what they were, I'd be done. So let's just call it a x hat plus b y hat, and c x hat plus d y hat. So some general map from the plane to the plane. It takes the inputs x hat and y hat and it does things to them. And let's suppose then that I'm looking to find that G circle F of the input is the input back again. So I want G to be the inverse of F. Okay, so let's see what to do. So I'm gonna take x, y, and under the map F, it's supposed to go to x plus 3y, 2x plus 4y, and then when you subsequently apply G, as you do here, it's going to go to, oh, let's see, it's a times x plus 3y plus b times 2x plus 4y, and then c times x plus 3y plus d times 2x plus 4y. And let me gather together the x's and the y's there. What am I looking at here? I'm looking at a plus 2b x and 3a plus 4b y. And on the bottom, I've got c plus 2d x and 3c plus 4d, 3c plus 4d y. And of course, the whole thing, when all is said and done, is supposed to be the identity. So we're supposed to end up with xy. Now, I don't know what a, b, c, and d are. That's the goal of the question, is to figure out what a, b, c, and d are. But I know that a plus 2b is 1x. 3a plus 4b is 0y, and like that. So as so often in this class, we're looking at a linear system. We've got a plus 2b is 1, and 3a plus 4b is 0. And then c plus 2d is 0, and 3c plus 4d is 1. All right, so Gauss's method. I won't bore you with the agony of watching me do arithmetic, so instead I'll just say that after a while I was able to work out that minus 3 row 1 plus row 2, followed by minus 3 row 3 plus row 4, leaves you with this linear system. A plus 2b equals 1, minus 2b equals minus 3, c plus 2d is 0, and negative 2d is 1. Okay, so the Gauss's method stuff, we're all great at Gauss's method at this point, so we're not going to go into that at great length. And so when all you can see from the bottom line, when you get down to the end, you're looking at d is minus a half. If d is minus a half, then c is 1. The next line up tells you that b is 3 halves. And the next line up tells you, let's see, if b is 3 halves, then I'm looking at a plus 3 equals 1, so a is minus 2. Okay, so I was able to figure out here what happened with the, I was able to figure out what happened, what are the A, B, the C, and D that would work. You've seen me do calculations before, it's always a good Indian check. So I'm going to try it with a specific example, just to try to make some sense of. So I'll take 5, 6. So let's see, what does F do to 5, 6? So x plus 3y is 5 plus 3 times 6, so that's 23. And 2x plus 4y is 2 times 5 plus 4 times 6, so that's 24, and 10 is 34. And then what does g do? Let's see, I've got here minus 2 times 23, and then b times 34, so that's plus 3 halves times 34. And then 23, that's 23, that's c is 1, so 23 minus 17. And what the heck is this? This is minus 46 plus 51. 23 minus 17, so I got what I was supposed to get, 5, 6. So the effect of G following F is the identity. Acting from the left, G is an inverse of F. Okay, so again, last time we talked about the inverses of functions and left inverses and right inverses and double-sided inverses. Let's get back to it. So we ended up last time with the definition of that G is, oops, there we go, G is a left inverse of H if G, capital G acting on the left on H produces the identity matrix. The right inverse if capital G acting from the right on H produces the identity matrix. And the case that we'll think about most often, capital H, so a matrix is with a two-sided inverse is called an invertible matrix. And the two-sided inverse is denoted H with a superscript -1. And all this exactly fits with what happens for functions. And of course, we did a couple of examples last time, and I pointed out one reason why a person might want to think about taking the inverse of a matrix is that it makes solving these systems very fast. Okay, so this is material that we didn't see last time. I took the regular function composition arrow diagram that we saw when we were doing matrix multiplication, and I specialized it to the case of the identity map when the function composition is the identity map. And that's what we're looking at. We're looking at if you do H first and then follow it with H inverse, you get the identity function. All right, so one thing to notice about this version of the arrow diagram is that in the previous version, it said V to W to X. Here it doesn't say V to W to X. Here it instead says V to V. And that's simply because the identity function takes capital V in and gives capital V out. That is, the identity function maps capital V to capital V. Still, another thing to see here is that I have, of course, the matrix capital H and the matrix capital H inverse. And on the bottom here, I have the matrix capital I. That's the identity matrix, the one that's square. All zeros except for ones down the main diagonal. Because capital I is the identity matrix, that says with respect to the basis B, and that also says with respect to the basis B. Okay, so this is the arrow diagram for composition specialized to the special case that we want to consider. So as usual, when we introduce an idea here, for example, to relate the representation of the map, capital H, excuse me, lowercase h, with the representation of the map, lowercase h inverse, whenever we introduce an idea, we try to surround it with some ideas to help a person sort of build up the right structure in their mind, the right scheme in their mind to hang later ideas off of. All right, so here's a picture version of the sort of algebraic statement that we gave earlier. Okay, have a couple of results that we're not going to prove. The proofs are usually easy. I'm going to mention one of them. The proofs are usually easy, but I happen to want to get to the computation of matrix inverses. That's the goal for today. So I'm going to go a little light on the proofs, but I'll just mention. If a matrix has both a left inverse and a right inverse, then the two are equal. So it cannot be the case that a matrix has one inverse on the left and one inverse on the right, and they're different. That can't happen. And I'm just going to mention here what the idea of this is. The idea is you imagine that capital H has both a left inverse A and a right inverse B, and then you look at what happens when you take A times H times B. On the one hand, it's A times H times B, which is B, because that's the identity. On the other hand, it's A times H times B, which you guessed it, is A, because that's the identity. So B and A are the same. Okay. So so a lot of these results here are the same idea, that it's just a question of thinking through what the maps are doing. So so here we're looking at the second result says a matrix is invertible if and only if it's non-singular. And again, that's the same idea as we saw before. Non-singular matrix is associated with a non-singular map. Map is non-singular if and only if it's an isomorphism. You go from V to W and you can come back. Well, that's the same thing here. A matrix is invertible, means that you can multiply it and then you can undo that to come back. Now, both of these results have quick proof. You start with a matrix, because both of the results say start with a matrix. You start with a matrix, you fix spaces capital V and capital W, and then you fix bases, you might call them capital B and capital D, and then you just look at what happens with the arrows. Capital H represents a map lowercase h, and the statements are true about the map. If a map has both a left and right inverse, then the two are equal. So the statements are true about the map, and therefore they must be true about the matrix. So the idea, again, is we're taking maps as kind of the original object, the sort of object, and we're worried here about seeing how that's reflected in the computational entities, computational things derived from the maps, the matrices, and it just falls right out. Two more results. Again, the first lemma says product of invertible matrices is invertible. If capital G and capital H are invertible, then capital GH is defined. Then capital GH is invertible also. And capital G, capital H inverse is, it's not what you might think it. You might think it's capital G inverse, capital H inverse. That's not right. Instead, the inverse of capital G, capital H is capital H inverse times capital G inverse. But this is easy to see. You just say to yourself, what does it take to get rid of GH? Well, first, you want to stick in a G inverse to get rid of the G. Let me go to the scratch work. There we go. So what does it take to get rid of GH? And of course, what you want to do is get rid of the G first. Those will cancel to give an identity. And then after that, you can get rid of the H. So you get rid of the G first, and then the H and H inverse, and you do indeed get the identity. Okay, so that's just a question of sort of writing things down in the right order, and exactly the same argument as above. Exactly the same argument works for the functions. Okay, and then finally, I'm at the result that I want to get at. The result that tells you how to compute the inverse of a matrix. So a matrix H is invertible if and only if it can be written as the product of elementary reduction matrices. And then here's the part that we're going to focus on today. We can compute the inverse by applying to the identity matrix the same row steps in the same order that you use to Gauss-Jordan reduce H. So this says how to compute the inverse. So we're keen because we want to get the answers. In the back of the book, that's always interested in finding the answers. Again, I'm not going to go through the proof, but again, the proof is got a simple idea to it once you think about stuff we've done before. So we want to find G so that GH equals the identity. So what is it? What is it that multiplies H to give the identity? Well, we saw when we were doing the mechanics of matrix multiplication that there are matrices that do the Gauss's method steps. I'm here at H, I want to get to the identity, so I want to do the Gauss's method steps that do Gauss-Jordan reduction. So we saw a result last time that says there's a sequence of matrices. I think I called that last one capital R sub little r, where if you multiply them together, then you're doing the Gauss-Jordan steps that take H to the identity. So this is exactly what I want. This is capital G. Multiply those matrices together. Stated in the form of the lemma, I'll write capital G as, write them out here, and I'll multiply them all times the identity. That is to say, I'll start off with the identity and then do R1, and then after that I'll take the result and do R2 to it, and after that I'll take the result and do R3 to it, and etc. And that's all it is. I'm just simply recognizing that Gauss-Jordan reduction is what I want to do, and that the steps of Gauss-Jordan reduction, if performed on the identity matrix, will result in the matrix capital G that I want. So let's see an example. Okay, so here's a matrix that is non-singular, and so therefore it's invertible. And I'm gonna of course find the inverse. It's non-singular, square, and if you do Gauss's method on it, you'll get echelon form with no zero rows. So, all right, so let's do the steps I just described. So the steps I just described is you start with the identity. See the identity over here? This is the matrix capital A, and this is the identity. You start with the identity, and you perform on the identity the Gauss-Jordan reduction steps. So that's what I'm doing. I wrote the identity next to the original matrix. I'm performing the Gauss steps here. I didn't all fit on one slide, so I got to do more on the next slide. I'm performing the Gauss steps here. For example, minus 2 row 1 plus row 2 is how I use this one to get rid of that 2. And if I follow it all the way across the row, minus 2 row 1 plus row 2 puts this minus 2 right there. Likewise, minus row 1 plus row 3 gets rid of that 1 and also puts a minus 1 here. And you continue along in that way in the usual Gauss's method way. And again, the Jordan, half of Gauss-Jordan is on the second slide. I just couldn't fit it all in one slide. Here I have echelon form. Next step in Gauss-Jordan's reduction. Do you remember the next step? The next step is to turn all of the diagonal elements into ones. So I have to multiply row 2 by minus 1/6, and I have to multiply row 3 by minus 2. Make some messes over here on the other side. And then here you go. You have to take the entries, remember in the opposite order, moving from right to left now instead of left to right. You take the entries and you eliminate up. And you eliminate up. When you do, follow through the arithmetic, you get this. That is the answer. It has a disadvantage of being a bit of a mess. It has the advantage of being the answer. Okay, so we found the inverse following the result that I just quoted, that if you perform the Gauss-Jordan steps on the identity, you'll get the inverse. Now, finding the inverse of a matrix is kind of a lot of work. Gauss-Jordan is kind of a lot of work. Imagine if the matrix was 100 by 100, I wouldn't be keen. Why would you do such a thing? That is, the person can say, well, I already knew how to solve linear systems. Why are you so keen? So I'm going to illustrate one example of why you might want to do such a thing. There are lots of examples, and there's also the knowledge that you gained, but I'm going to illustrate one example of why you might want to do such a thing. So here's a linear system. Do you recognize that matrix of coefficients? It's the one from the prior slide. Here's a linear system, and I wrote 2, 12, 4. I just made up 3 numbers and put them over there for the constants. Gives this matrix equation, again using the matrix that we found the inverse of in the prior slide. We saw already that you can use the matrix inverse to solve this matrix equation. You multiply it from the left on both sides of the equation. When you multiply the matrix inverse from the left on this side of the equation, the matrix and the matrix inverse cancel, and you just get the vector of unknowns. When you multiply the matrix inverse onto the other side of the equation, the right-hand side of the equation, here it is, matrix inverse multiplied by the right side of the equation, and you get something that's, again, just a little bit ugly with thirds, but anyway, it's the answer, so that's what I want. X equals 16 thirds, etc. Okay, all right. So what was the point again? Here's the point. I wrote down a linear system that looks like the one from the prior slide, but it's just a little different. You see that that has a 2? And that has a 1. I'm able to, with the matrix inverse, I'm able to very quickly solve this one. Of course, I get a somewhat different answer because I started with a somewhat different question. This process where you have the same system on the left-hand side but slightly different right-hand sides comes up a lot in practice as an example of where matrix inverse would be handy. I'll name a specific example rather than just wave my hands around. So, for example, economists often use linear systems to model what happens in an economy. So the people who are buying steel cause the price of steel to go up, and because the price of steel went up, the price of automobiles is going to go, all this kind of stuff. So they often use linear systems to model what's going to happen in the economy, and they say, well, next year we're predicting. One of the things that a person should do when they make predictions is they should try to see how accurate the predictions are. In one sense that the predictions would be accurate is if you take your expectations for next year, I expect this to be 2 next year, and you change it slightly. What if instead it's 1? Then you're interested in how that changes your model's prediction. If your model's prediction changes drastically depending on what you write down for these numbers, why then you got to be very careful about what numbers you put here. So that's called sensitivity analysis. How sensitive is the result 14 thirds minus 1/3 minus 8 thirds? How sensitive is the result to changes in the assumptions? And what we see here is that once you have the matrix inverse, you can rapidly get answers for changed assumptions. So that's an example where you'd want the matrix inverse. It gives you some idea of how to proceed quickly. Okay, almost done. So with the 3 by 3 matrix, the one that I just did was a 3 by 3 matrix. With the 3 by 3 matrix, you can imagine going through and writing A, B, C, D, E, F, G, H, I, and doing Gauss's method. Right? You have an A, B, C, D, E, F. So you're going to say something like, well, minus D over A times row 1, add to row 2, and that'll use the A to eliminate the D. And you can do that. I've done it. It takes a long time. It's a bit of a pain. It's one of the answers to the exercises, but you can do it. It's not so much of a pain if you just do it with 2 by 2s, though. With the 2 by 2 matrix, it's not really very much trouble at all. You can ask yourself here, I'll put A, B, C, D, and on the other side of the matrix, I'll put 1, 0, 0, 1. And I'll take minus C over A, row 1, add to row 2. That'll use the A to eliminate the C, and you follow that through. You get all the letters, and again, in one of the homework exercises, you get all the answers are in terms of letters, and it's a little bit fiddly, but not too bad. When you do, you find that the formula for the general 2 by 2 matrix ABCD's inverse is this. It's a fraction. You might remember with the matrix A, it was a bunch of thirds. So the fractions come up here. We'll see why in the next chapter. But fractions come up here. So the fraction in this case has for the bottom of the fraction A times D. So you multiply the corners. A times D minus B times C. That's just what it works out when you do the letters. That's just the way it works out. And then what are the entries? So the entries are, you see the A and the D, you interchange them, and you change the sign, the SIGN, of the off-diagonal entries. And so the inverse for a 2 by 2 matrix is calculated using this formula. It's worth memorizing this formula. 2 by 2, needing to solve 2 by 2 equations comes up reasonably often, and a person can, if the numbers are straightforward enough, a person can do this in their head. So it's worth memorizing this particular formula. Okay, and the computation is exercise 21, but it's a little bit fiddly, but not too bad. Maybe 1 page of paper. Here's an example, 2, 4, minus 1, 1. So let's see, where do I get the 1/6? 2 times 1, that's AD, minus B times C. B times C is minus 1 times 4, so that's 2 minus a minus 4, so that's the 6. And then what are the entries again? So you got to flip, D and A flip. So you got to flip the 2 and the 1, 1 and 2. And you got to change the sign, change the SIGN of the 4 and the 1. So the 4 becomes a minus 4, and the minus 1 becomes a plus 1. And when I carry through the 1/6, that's what I get. So it's worth memorizing this particular one. I don't know about memorizing the 3 by 3, but it's worth memorizing the formula for the inverse of a 2 by 2 matrix. It's not too bad at all. Okay, very good, very good. So let's see, for next time, we're going to move to a new chapter. So we're going to be doing something different. We'll see what happens to, for example, the representation of a vector when you, with respect to a basis, when you change the basis. Okay, very good. Hi. Well, of course, last time we did the inverse of a matrix, computing the inverse of a matrix, and so naturally the check-in has to do with that. It asked me to find the inverse of those pair of 3 by 3 matrices, and it says if it exists. So there's, you've been student for enough years to know that one of them is going to exist and the other one isn't. Let's see which one it is. Okay, let's get rid of that. There we go. All right, here's the paper. So let's see. The first one is 1, 3, 3, 1, 4, 3, and 1, 3, 4. Okay, and the method that we learned last time is to do Gauss-Jordan on this matrix, that is to reduce it to the identity matrix, to do Gauss-Jordan on this matrix while at the same time performing the same operations starting with the identity. So here we go. 1, 3, 3, 1, 4, 3, 1, 3, 4. and you put a vertical bar, like an augmented matrix vertical bar, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now, so often in the past videos, I've been saying, you know, I'll just show you the steps and you can fill them in yourself. But because this is a little bit different, I'm going to do at least a couple of steps. So the first one is minus row 1 plus row 2. And it goes 1, 3, 3, 1, 0, 0. And then the row that's changed goes 0, 1, 0. And then minus 1, 1, 0. And the third row isn't even mentioned. 1, 3, 4, 0, 0, 1. So I'm performing the regular Gauss's method steps. I'm carrying those operations over into this second half. Just, of course, we saw the theory, the reason why this particular operation does indeed produce the inverse. But one thing you can think, one intuition that can help to build your idea of what's happening here, is that this minus 1 down here in the row 2, column 1 position, in some sense remembers this operation. Okay, anyway, enough hand waving. So now I will take a minus row 1, add to row 3. And that gives me the 1, 3, 3, 1, 0, 0. 0, 1, 0, minus 1, 1, 0. Those, of course, are the unchanged rows. And then 0, 0, 1, and minus 1, 0, 1. And again, that minus 1 in some way remembers this operation is an intuition that a person can have. Ordinarily, in the Gauss-Jordan reduction, the next thing you do is to turn the diagonal entries into 1s. They happen to already be 1s. They don't happen to be 1s. I made up problems so that they're 1s. And so now I turn and start pivoting up. The thing to remember about pivoting up is that it's easiest if you do it instead of from left to right, as I've been proceeding so far. It's easy if you do it from right to left. So use the 1 to get rid of the 3 kind of stuff. Here we go. So that's what minus 3 row 3, minus 3 row 3 plus row 1. It gives me 1, 3, 0 for that top of the left-hand side. 4, 0, minus 3. And then 0, 1, 0. Minus 1, 1, 0. And then 0, 0, 1. Minus 1, 0, 1. And then finally, all I have to do is use this 1 to get rid of that 3. So I take minus 3 row 2 plus row 1. And then I'll be done. I just have to say, let's see, it's 1, 0, 0, and then 7, minus 3, minus 3, right? Because minus 3 row 2 makes this a minus 1. You add to the 4, that explains the 7 kind of stuff. Then 0, 1, 0, minus 1, 1, 0, and then finally 0, 0, 1. Minus 1, 0, 1. Minus 1, 0, 1. And so the answer is that, A inverse is what's over here. 7 minus 3 minus 3. Minus 1, 1, 0. Minus 1, 0, 1. Okay? And you could try multiplying those two together and make sure, either way, either from the left or from the right, multiply it by this and make sure that you get an identity matrix, which given my arithmetic skills is probably a good idea. But I'm not gonna do it. I'm just gonna forge ahead. For number 2. Let's see, it is what, 2, 2, 3, 2, 2, 3, 1, minus 2, minus 3, and then 4, minus 2, minus 3. And same thing, you put the 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? And you start in. So you take a minus 1/2, minus 1/2, row 1 plus row 2. And also at the same time, I'm going to do minus 2 row 1 plus row 3. I don't know why I didn't combine those two, other than just wanting to illustrate a little more slowly. So 2, 2, 3, 1, 0, 0. And then I get 0, minus 3, minus 9 halves. Can you see it says minus 9 halves? Minus 1 half, 1, 0. And then 0, minus 6, minus 9, and minus 2, 0, 1. And now we've done so many Gauss's methods that I wonder if a person doesn't have some idea what's happening here and spot, because your antenna is up, spot that the second row here is in the left-hand side of the matrix. The second row is the third row is twice the second. But plunging ahead as though I haven't noticed that. Minus 2 row 2 plus row 3, and I get 2, 2, 3, 1, 0, 0, 0, minus 3, minus 9 halves, minus 1 half, 1, 0, and then 0, 0, 0. And I could stop because I know there isn't going to be an inverse, but I'll just go ahead just for the sake of having done it. Minus 2, 1. So minus 1, minus 2, 1. And here, because the matrix is singular, it has no inverse. Okay, so because I got a row of zeros, no inverse. So either you plunge ahead and you do Gauss-Jordan reduction and it goes the whole way through and you get an inverse, or else when you do Gauss-Jordan reduction you run into some snag, and that's the no inverse case. And those are two things that can happen. You either have a problem or you don't have a problem. Okay, so we're ready for the next section that we're going to talk about. So we now have been working for some time with the ability to represent a vector with respect to a basis, and we have emphasized that somehow this representation is the computational aspect of an object. That I've used the analogy that if I take a trip somewhere, that the real thing is the trip, and the pieces of paper with numbers on them that I hand in to the accounting folks, that those are somehow not real. Those are somehow the not primary. Those are somehow the evidence of the trip, the computational aspect, the computational thing they use to compute the trip, but it isn't really the trip. So what I've got here is that if you give me, for example, a vector, I can represent it with respect to some basis B1, and I get a bunch of numbers. Or I can represent it with respect to some basis B2, and I get a bunch of numbers. So what I want to do here is, what's the relationship between the two bunches of numbers? Is bunches, is that plural bunches of numbers? Anyway, what's the relationship between the two number bunches, I guess? So given a vector, I'm going to fix a vector, and I'm going to vary the bases. How does the representation vary? So first is to observe that that if you take a vector 1, 2, 3, because I'm not a very imaginative person, and you represent it with respect to two different bases, then you get two different representations. So it's easy to compute an example. There's an example. You fix the base. Excuse me. You fix the vector and you change the bases. Why then you change the representations? The question is, if I tell you E3 and B, can you tell me how to convert from 1, 2, 3 to 0, 2, 1? Right? So here's the idea. We've been emphasizing, I've been talking for some time throughout the sort of the third chapter about how we're trying to view that the maps are primary, and the sort of matrices and everything are not foolish by any means, but secondary. Something's got to be primary, and we're putting the maps as primary. And what we're talking about today is a great example of that the maps give a meaning to what we're doing, in the way that just saying, well, here, set up this linear system and then do Gauss's method on it, does not give a meaning. When I took this course, the way it was laid out, everything was set up a linear system, do Gauss's method on it, and you'll get the answer. And I left the course feeling that I could get all the right answers. I got an A in the course, but that I had never had any idea what was happening. I never had any kind of conceptual, here's the idea type of thing. So we're very focused on what the idea is here. We do a lot of computation, but we're very focused always on what's the idea behind the computation. That's where the sort of taking maps as primary pays off. Today is a great example. I want to translate from the representation with respect to B of a vector V to the representation with respect to D of a vector V. V is not changing. It's V here and it's V here. So I'm thinking of the identity map from V to V. The identity map from V to V. And so as I'm thinking of this picture, I wrote it up and down because ordinarily the map pictures go side to side, but I wrote it up and down because in the next subsection there's going to be another drawing where it's convenient to have it up and down. There'll be other things side to side, so that's why it's up and down. So I have a space. I'm mapping the vector V to itself, and I'm worried about what's the conversion. If you have a representation with respect to B and a representation with respect to D, how do you get from here to here? And of course we've seen how to represent a map. It happens to be this map, but so what? It's a map. We've seen how to represent a map with respect to the input and output bases, the domain and codomain bases. All right, so that's what I need. Change of basis matrix is the representation with respect to B comma D of the identity map. That's all. The fact that we take the maps as primary, that we look to the maps for the meaning of what we're doing, tells us that there's no tough computation involved here. You just simply write down the representation with respect to B comma D of the identity matrix. Excuse me, of the identity map. That's all. So I wrote exactly what that matrix is, but we know what that matrix is. So you figure out here what is the identity map acting on the first basis vector, what is the identity map acting on the second basis vector, etc., all the way down to the identity map acting on the nth basis vector. And then you represent the result with respect to D, the result with respect to D, the result with respect to D, the result with respect to D. Of course, the identity map acts on beta 1 by setting it to beta 1. That's what the identity map does not much. All the way out to it maps the last basis vector to itself. And then we just represent those folks with respect to the codomains basis, the output basis, right down here, the D. All right, so of course we're going to compute a couple of those, but my point about the whole map versus matrix thing is that because we're taking the point of view that we want these things to have a meaning, we want to think of them in terms of maps, that the meaning is clear. There's no linear system to set up. The meaning is clear. Okay. So that gives me this. Is that if you have a representation with respect to a basis B, and you want to convert it to a representation of the same vector with respect to a basis D, why you want to left multiply by the matrix, representing the identity map with respect to B comma D. Okay, and the converse works also. If you have a left multiplication by a matrix that changes bases, then M is a change of basis matrix. And the book has the proof. I want to do the computations because we take that a person is watching the videos first, then reading the book, and then doing the homework. Okay. So you know how I work. I'm going to write down some not too hard but not too easy cases, and then I'm going to do the computation. Because I think by taking out a pencil and saying to yourself, what goes here? And then looking up at the example when you get stuck, that's how a person makes progress. We zigzag our way to knowing the truth. First you start out knowing 70%, then 85%, then 95%. So here we are, we're hoping to make a first cut at it. Okay, so I have the domain space is P2. I'm going to change representations from with respect to B to with respect to D. So I've got to compute the representation with respect to B comma D of the identity map. Okay, so what does the identity map do to the first of capital B's basis vector? What does the identity map do to the second of capital B's basis vectors? What does the identity map do to the third of capital B's basis vector? And of course, the identity map doesn't do anything at all. So that's the outcome of applying the identity map to the basis vector 1. That's the outcome of applying the identity map to the basis vector 1 plus x. That's the outcome of applying the identity map to the basis vector 1 plus x squared. Represent those with respect to d, represent with respect to d, represent with respect to d. And d is simple enough that a person can eyeball the answer. In any event, I'll spare you the agony if eyeballing fails you for one of the three. It turns out when you do the arithmetic that the representation with respect to d of the first basis vector in capital B is this. The representation with respect to d of the second basis vector in capital B is this. The representation with respect to d of the third basis vector in capital B is this. And we know how to make the representation of the map as a whole. You write those three vectors in order. That's why we have bases coming in order. Write those three vectors in order. There they are, and it makes a matrix. And of course, I did an example. Suppose that you have a vector that is v minus x plus 3x squared. You can calculate here that the representation of that vector with respect to b is this. And you can calculate that the representation of that vector with respect to d is this. It's of course very easy to go from the representation to the vector. You just take 3 times the first minus 4 times the second plus 3 times the third and just check. Likewise 1/2 times the first, 1 minus 1 times the second, and 5/2 times the third, and just check that it works out to be 2 minus x plus 3x squared. And a person can easily check that if you take this matrix and you multiply it by 3 minus 4, 3, here's the 3 minus 4, 3. Multiply it by 3 minus 4, 3, you do indeed get 1/2 minus 1 5/2. So the diagram that we had, this diagram right here, it does exactly what it's supposed to do. It changes the representation with respect to b to a representation with respect to d. Okay. The next result is that a matrix changes bases if and only if it's non-singular, and only if it's an isomorphism. A matrix changes bases if and only if it's non-singular, and as often happens, we're going to do an example rather than the proof in these slides. Just that's the way we operate, trying to get an understanding, and the understanding leads to a proof, and then that bundle taken together leads to the homework. So here's an example. So I'm going to take a non-singular matrix M, and any non-singular matrix M decomposes into a product of elementary reduction matrices, right? So we can show that M changes bases by showing that each Ri changes bases, right? So you remember that you Gauss-Jordan reduce M to the identity, and then you express that as identity times all of those. And so we can show that M changes bases by showing that each Ri changes bases. Now, I'm not going to show the proof shows that each Ri changes bases, but here's an example. I took minus 4 row 1 plus row 3. I took that matrix, the matrix that performs minus 4 row 1 plus row 3, and I multiplied it by the representation with respect to b of v, and I don't have that. I just have r1, r2, r3. It's a 3 tall vector with letters there, and I did the matrix vector multiplication, and of course what you get is r1, r2, and then it does indeed take minus 4 row 1 plus row 3. Row 1 is pretty simple, but anyway, it does it. It takes minus 4 row 1 plus row 3. If this is the representation with respect to capital B, and this is capital B, then the right side is the representation with respect to this b hat. So if this represents a vector v with respect to capital B, then this represents the vector v with respect to this b hat, because look, r1 times beta 1 plus 4 beta 3, that's the first thing here. R2 times beta 2, that's the second thing here. R3 times, minus 4 R1 plus R3 times beta 3. And when you add it all up, it adds up to what it's supposed to add up to. Verifying that b hat as a basis is routine. That's what the proof has to worry about. But verifying that b hat as a basis is routine. That if b is a basis, then b hat is a basis. So that's routine, checking that it's linearly independent and that it spans the space is routine. Okay, so that is to say a matrix is non-singular if and only if it represents the identity map with respect to some pair of bases. A matrix is a matrix is a matrix is a non-singular matrix. Remember the definition of non-singular matrix. Square, and when you do Gauss's method on it, you get the echelon form no zero rows. So a matrix is non-singular if and only if it represents the identity map with respect to the appropriate pair of bases. Okay, when we come back next time, what we're going to want to do is to think about how we change not just the representation of a vector with respect to the input and output bases, but how do you change, if you have a matrix representing a map, what happens when you change the bases? So the map is represented with respect to some b comma d. What happens when you change the bases to some b hat comma d hat? How do you translate from the one to the other? Okay, very good. Bye-bye. Hi. So last time we learned how to relate the representation of a vector with respect to b to the representation of the same vector with respect to d. So naturally the check-in asks us to do exactly that. So let's have a look. Let's see. So I'm going to do an example that involves whoops, what happened? That involves 3 plus 2x plus x squared. So v is 3 plus 2x plus x squared, 3, 2, 1. And it's a member of the space of polynomials, quadratic polynomials. And b1 is, it's a 1 plus x squared. Use that basis a lot just as an example of a basis that's not too hard and not too easy. And b2, again, another example of a basis that's not too hard and not too easy. X squared minus 1, and x squared minus x, forgive me, x squared minus x plus 1. Sorry about that. And the first question asks me to represent this vector with respect to b1 and b2. So the representation with respect to b1. So I just have to figure out here, I'll write 3 plus 2x plus x squared. And I got to figure out how many 1s, how many 1 plus x's, and how many 1 plus x squareds does it take to represent, to get that total. Okay, we've seen this before. There's only one x squared on the left-hand side, and there's only one x squared on the right-hand side, so I need for the coefficients to be the same. There's only one x on the left-hand side, only one x on the right-hand side, so I need for the coefficients to be the same. And then what's the story with the constants? So 1 plus 2 is 3, and I have 3 over here, so I don't need any of those. So just because I could do it by Gauss's method doesn't mean I should. I can just eyeball the answer. The representation with respect to b1 of the vector v, 3 plus 2x plus x squared, is it's got to get them in order, 0, 2, 1. Likewise for the other one. The representation with respect to b2 of v, well, 3 plus 2x plus x squared, and that's how many x squareds? How many x squared minus x? And how many x squared minus x plus 1? So, again, I'm going to eyeball it. I see there's only one constant on the right-hand side, so I need that to be a 3. Once that's a 3, I have minus 3x, and so I need for the number of x's to be minus 5. That way, minus 5 times minus 1 makes positive 5. Added to minus 3 gives me the 2. And then lastly, what's the story with the x squared? I have 3x squared minus 5x squared. I need a total of 1x squared, so I need a 3 there. So again, I could do Gauss's method, but I'm able to eyeball the answer, so I eyeballed the answer. So the representation with respect to b2 of the vector v, 3 plus 2x plus x squared. Just wrote it in a different way. I don't know, just to write it in a different way. 3 minus 5, 3. All right, and then for the second part, I want to represent the, how do you convert from the one to the other? How do you convert representations with respect to B1 to representations with respect to B2? And of course, we saw last time, the result from last time was that if you draw the picture right, then the maps tell you what to do. So B1, comma, B2 of the identity map. So you ask yourself, what happens to the first basis vector under the identity map? I know it's silly, but I'm trying to be consistent. What happens to the second basis vector under the identity map? And what happens to the third basis vector under the identity map? I won't do it for the rest of the semester, but just to make the point. And then you represent, with respect to B2, each of the 1 plus x, and the 1 plus x squared. And I get here 0, minus 1, 1. I got here 1, minus 2, 1. And I got here 1, minus 1, 1. If you can read my handwriting. So I smushed them, or the three of them together, into a matrix, and that's the answer. Just to check, I'm going to check that it converts the one to the other. So let's have a whack. 0, 1, 1, 0, 1, 1. Minus 1, minus 2, minus 1, and 1, 1, 1. So that's what happened when I smushed that column with that column with that column, when I concatenated those three columns together. And I'm going to check that if you multiply by 0, 2, 1, do you indeed get what I'm hoping to get? 3 minus 5, 3. And let's see, so 0, 1, 1, dot product with 0, 2, 1, and you can see that that's a 3. Minus 1, minus 2, minus 1, dot product with 0, 2, 1. Boy, those zeros sure are convenient, aren't they? So minus 2 times 2 makes minus 4, minus 1, so you get a total of minus 5. And boy, it's certainly going to work out. 1, 1, 1, sure. So that checks. Okay, all right, very good. All right, so we did vectors, so surely what happens next is maps. Do the exact same thing, only with maps, that's all. So in we go. Again, it's a matter of understanding that if you've paid attention to the map, if you've looked for the meaning in the situation, instead of just blindly saying, well, there must be a linear system here somewhere, I'll just write down the correct linear system and chug away. If you look for the meaning of the system, it all makes perfectly beautiful sense. So I want to convert the representation of the map H with respect to BD over to the representation of the same map H with respect to some different, maybe the same, I suppose, B hat, D hat. So down here we see the appropriate diagram. Let me take you through the parts. Here's the representation with respect to B, comma D of this map lowercase h is, of course, the matrix capital H. We've done that lots of times before. On the bottom row, here I have the map H again, takes you from capital V to capital W, but now I'm representing it with respect to different bases, B hat and D hat. So naturally I expect to get a different matrix, H hat. How do you connect the top row to the bottom row? Well, we saw that last time. Here, you're changing the representation of a vector with respect to B to the same vector with respect to B hat. And over here, you're changing a vector W represented with respect to D to the representation of the same vector W, lowercase w, with respect to some different D hat. So this picture tells you in terms of the map what's happening here. When you think about what the meaning is, then it becomes much clearer than if you try to set up elaborate linear systems. You can set up elaborate linear systems, but the meaning makes it much more straightforward. All right, so where the heck are we? Well, we want to find H hat. We're given H. We want to convert from capital H over to capital H hat. So we want to find H hat. So if you're given h, then you can use it in some calculation. So I want to find h hat. I want to move from the lower left to the lower right, and so I'm going to take the following. I'm going to move, instead of lower left to lower right directly, instead I'm going to go up. I know I'm swimming against the ID arrow there, but we'll see what to do. You go up, you go over, and you go down. And again, we can go over because we already have capital H. We started with capital H. We're trying to compute capital H hat. Okay, so the two ways that this diagram gives you to compute capital H hat is by either writing down B hat and D hat and H and figuring out what is the representation of lowercase h with respect to B hat and D hat, or else you can go up, over, and down. Okay? Okay. Okay, so the down part over here on the right-hand side, we already saw that last time. You start with vectors in capital W, you end with vectors in capital W. So you're looking at this here. You're taking a vector, lowercase w to itself, so that's the identity map. Good, 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 good. I'm going to represent the identity map with respect to the starting basis of B and end it with ending basis of D hat. So starting basis of D, ending basis of D hat. So this part is familiar from last time. Over here, aren't you going against the arrow? Well, kind of. You see, the identity map takes little v to little v. So I drew the arrow from top to bottom for reasons that don't matter, but don't matter here. But I could have drawn it in the other direction. I'm simply looking to take the identity map also going up. I'm representing little v maps to itself, little v. So this is the representation of the identity map with respect to B hat B. So to go up, over, and down, you first do B hat B, identity map. You see it on the right-hand side. You got to get the order right. Next, you do H, like it says on the top line. And next, you come down again. So D hat of the identity map. The proof says it's evident from the diagram. I recognize that the diagram sometimes takes a little getting used to, but that's why we have a couple of examples to work through. Whenever I do one of these problems, just as a tip, whenever I do one of these problems, I write the diagram every time. If I write the diagram, I find I get them correct. If I don't write the diagram, all hell breaks loose. So I write the diagram. All right, so of course, our goal here is to try to make the abstract stuff, like this diagram, concrete by working through a number of examples. So here we go with the first example. One of my favorite maps is the derivative map that takes you from the quadratic polynomials to the quadratic polynomials. It could take you to the linear polynomials, but I happen to have written the codomain as the quadratic polynomials because I want to write v and v. Here's a basis, here's a basis. I could, of course, calculate the representation of the derivative map with respect to b comma d. I could also calculate the representation of the derivative map with respect to b hat comma d hat. So I can find those, the representation with respect to b comma d and the representation with respect to b hat comma d hat. And it's all, routine stuff. I mean, a little bit dull, but we've done it before. It's all routine. What about the going up and over? Previous slide says to go up, you want to go from b hat to b. So you got to keep that's why I write the diagram. You got to keep the bookkeeping right. You want to go from b hat to b. So that's what I got here. From b hat to b. And then the other one is to go from d to d hat. And again, I write the diagram to keep the bookkeeping straight, but I think I got the bookkeeping straight. D to d hat. Here's the b hat to b. Here's the capital H. Here's the d to d hat. And when you multiply these three together, a person needs to check this, of course, but when you multiply these three together, you should get that. And it isn't some accident of the way the numbers combine. It's because it means something. There's another example of exactly the same thing. This is the ordinary rotation of plane vectors counterclockwise. Pi over 6 radians. So 30 degrees. And we've done this before, but it doesn't matter. It's not too hard to calculate that the representation with respect to the standard basis of rotation counterclockwise by pi over 6 radians is this. I want to translate that to a representation with respect to this basis here. So again, I don't want to, don't want to sound like I think everybody is a dope, but I want to sound like it's a good tip. Draw the diagram. It will make sense in a way that memorizing the things doesn't make sense. So when you draw the diagram, what you get is, on top is the representation with respect to the standard basis. On the bottom is the representation with respect to the other basis. I know that the last problem I called this B hat and D hat, and now I'm calling it B and D. Get over it. Identity map, the whole diagram makes sense to move from lower left here to up to over to down. To get H hat, we move from the it says upper left, but it's supposed to say lower left. I apologize. Move from the lower left up, over, and then down. It didn't fit on the slide, so here we go. With respect to the standard basis, it's pretty easy to figure out how to move up. So back again. So representation, how do you get up? Representation of the identity map with respect to B, comma, E2. There it is, and again, I'll have to let you take out a pencil and do the calculation. Done it a lot. The matrix for moving down, I went the wrong way, darn it all. Matrix for moving down is the representation E2, comma, D. Now, B and D are the same, happens a lot in practice. B and D, that B and that D are the same. So in fact, to go up is the opposite of to go down. So you could calculate down separately, but you could also observe that it's simply the inverse matrix because it just goes in the other direction. So the representation BE2 is there. To find the representation E2, comma, you could call it B or you could call it D. You can take the one I just calculated and find the inverse. We have a formula for inverse, so there it is. So I saved myself a little work, and I wouldn't have really remarked it except that it comes up an awful lot. All right, so here we go. Do this calculation, and you get the familiar answer from before. See, there's the 3/2. Whoops. There's the 3/2, the minus 1/2, the 1/2, and the square root of 3/2, minus 1/2, 1/2, and square root of 3/2. There it is, square root of 3/2, minus 1/2, 1/2, square root of 3/2. When you do all the calculation, you get this for the representation with respect to B, comma, D of the rotation. So there's the familiar one from before. Here's the two matrices that I just calculated, and there's the answer. Okay, so it does seem to me this is, I'm skipping past the special case here and going to the general case. It does seem to me that this is memorizable. That writing these down every time you do this problem will make the problem make sense in a way that the formulas, I'm not embarrassed about formulas, but if you write that down, then the formula that's down at the bottom of the page makes all the sense in the world. Okay, what did I do? There we go. Okay, so ready to close here is that we will call two same size matrices, H and H hat. We'll call them matrix equivalent if you can translate from the one to the other. Right. So a person should practice a few of these now. Then we'll come back and talk some more about changing map representations. Okay, very good. Bye-bye. Hi. Okay, last time we learned how to change the representation of a map when you change the bases. So we have a map, lowercase h, as illustrated by this check-in. We have a map, lowercase h, and we have two sets of bases, B and D, and B hat and D hat. And what we want to learn is how do you translate from the basis pair, B, comma, D, to the basis pair, B hat, comma, D hat. And of course we saw that last time, so this is kind of a long calculation. Let's go through it. So let's see here, just to write down what I have. I'm looking at H takes the plane to the plane. And it maps here xy over to x minus 2y and 2x plus 3y. All right, and I'll copy down the two bases for just for reference. B is the standard basis on R2, and D is, as always, I try to pick examples that are not too easy and not too hard. If they're too easy, then they sometimes fail to illustrate all the points you want to illustrate. If they're too hard, then you're just hitting yourself with a stick while you're doing that. So D is 1, 0, 1, 1. B hat is 1, 1, 1 minus 1 that we've used so often, and D hat is 2, 0, 0, 3. So I'm trying to pick ones that I'll be able to eyeball, but also ones that are not so easy that they fail to illustrate what I want to do. So let's see here. First thing I want to do is represent with respect to B comma D the matrix H. Excuse me, the map H, map lowercase h. So I got to figure out where does the elements of B go under H. And I think if you apply H to 1, 0, you get to 1, 2. And if you apply H to 0, 1, you get to minus 2, 3. Then I have to represent those with respect to D. So the representation with respect to D of 1, 2. And the representation with respect to D of minus 2, 3. Now I picked ones that a person can eyeball, so let's see, 1, 2. So I think in order to get 1, 2, you have to multiply the second vector by 2. And once you multiply the second vector by 2, in order to get a 1 here, you need a minus 1 up here. And likewise, I can eyeball this. If in order to get a 3 on the bottom, I have to multiply the second vector by 3. Once you multiply the second vector by 3, then you have a 3 up there. In order to end up with a total of minus 2, you need minus 5. Okay, so H here, which is the representation with respect to B comma D of lowercase h, is you stuff those into columns, minus 1, 2, and minus 5, 3 in the right order. All right. Next up is the representation with respect to B hat D hat of lowercase h. So same stuff. It's that's what I meant by a long calculation. I got to figure out where the basis elements go, and 1 minus 1. So let's see. 1, 1 goes to 1, 1 goes to 1, 1, so that's minus 1, and 1, 1, so 5. And then 1 minus 1 goes to 1, 2, so that's 1 minus a minus 2, so 3, and 3 minus 1. I'm trying to do too many things at once here. Okay, so now I got to represent with respect to D hat minus 1, 5, and represent with respect to D hat 3 minus 1. So let's see here. D hat is especially easy, so I guess in order to get a minus 1 on top, I need minus 1/2. And then in order to get a 5 on the bottom, I need what, 5/3. And in order to get a 3 on top, I need 3/2. And in order to get a minus 1 on the bottom, I need minus 1/3. So that H hat, which is the representation with respect to B hat D hat of lowercase h, is stuff these things into columns. Minus 1/2, 5/3, and 3/2, minus 1/3. Okay. Okay, I'm going to need another piece of paper to do the second half of the problem. So let's see, the second half of the problem. Second half of the problem asks me to to do the change of basis calculation. So part B asks for the diagram, and really the diagram has saved my answer so many times. When I was trying this for my notes, I got confused and wrote the wrong side, but the diagram straightened me out right away. So the spaces are r squared in all 4 cases. So the plane in all 4 cases, I've got a basis B and a basis D, a basis B hat and a basis D hat. I've got a map lowercase h and a map lowercase h. Up here I'm representing it with a matrix I call capital H. Down here I'm representing it with a matrix I call capital H hat. And of course what ties the top line together and the bottom line together is the identity maps. In short, H hat is, you've got to go up, over, and down. You can go straight across, that's this, or you can go up, over, and down. And here's the part that a person gets wrong. Up, over, and down, you write the up first. Representation with respect to B hat B of the identity. Then the over is H. Then the down is the representation with respect to D hat of the identity. So the order is so confusing. I can't tell you how many dozens of times, hundreds of times, maybe thousands of times in my life I've gotten the order wrong. The diagram is a big help for aiding your memory in trying to get it right. Okay, so up, over, and down, remembering to get the right order. Darn that order, but anyway, that's the way it goes. Okay, so in order to write down these parts, I have to write down the representation with respect to B hat B of the identity, and I'll do the D hat D and the D hat in just a minute. On the previous piece of paper, I did this calculation in a certain way, so I'm going to do it the same way here, because when a person is first starting, they should do all the calculations in the same way. At some point, you'll start saying to yourself, oh, I got it, I can take the shortcuts. But when you first see it, you should do everyone the same way. So in short, I'm going to do the silly thing here of writing that the map is the identity. So I'm writing the basis elements 1, 1, and 1 minus 1, and I'm applying the map. I know that's silly. I know that's silly, but I'm going to do it anyway, because I'm going to do every problem the same way until I say to myself, oh, I got it already. Start taking shortcuts once you're good at it. I got to represent that and that with respect to the, represent that and that with respect to the ending basis. Do you remember that the basis B is the standard basis? So the representation with respect to the standard basis of 1, 1, and the representation with respect to the standard basis of 1 minus 1. So I took that and wrote it there, took that and wrote it there, just as I did on the previous piece of paper. And this is E2. Every vector is represented with respect to E2 by itself. So all this stuff, when a person gets good at this, you start saying, I can skip all those steps and go right to the fine. But when you're first learning it, you should do it everyone the same way. And then I'll skip the matrix for just a minute, and I'll do the representation because I only have so much room on the piece of paper with respect to what D comma D hat. And again, the diagram has reminded me why it's D hat here and it's B hat B here, because going up you start with the hat, coming down you start without the hat. Okay. So representation with respect to D hat, if I don't flub it up, of the identity. And again, I'm going to do the silly thing. I'm going to write down the basis elements from D. Basis elements from D are 1, 0 and 1, 1. I'm going to apply the map. I know that's silly. And then I'm going to represent those with respect to the ending basis, the D hat. Representation with respect to D hat. Okay, and do you remember D hat is this 2, 0 and 2, 0 and 0, 3? So that's 1/2 0 and 1/2, 1/3. Okay, and again, I'll write down the matrix in just a second. So writing this right here, down here, I got to remember this stuff from the previous slide. So let's see, what the heck was h hat? What the heck was h hat? H hat was, so h hat was minus 1/2, 3/2, 5/3, minus 1/3. That was h hat. And the translation formula for translating from h to h hat is write the b hat b over here, write the h here, write the d hat here. And just I'm going to write them in the order that I said them. So the b hat b goes 1, 1, 1 minus 1. The h I got to remember from the previous, it's minus 1, minus 5, 2, 3. Okay? And the h hat goes here. 1/2, 0, 1/2, 1/3. Okay, so a long calculation, I know parts of it I made longer than perhaps a person who is good at it would zoom through those, but nonetheless, a long calculation, but it shows the translation. You gotta get the order right. That's the part, as a person who flubs things up, I can tell you that's the thing you'll flub up. Gotta get the order right, and the diagram is a tremendous help in getting the order right. Okay, very good. Okay, right. Okay, so last time we talked about this equation that we're looking at on this slide right here, and the equation and the diagram are closely related. There's the general diagram. Of course, in the example we just saw, we had the plane for the space, but nonetheless, there's the general diagram, and the diagram and the equation say the same thing. They say that you can do the bottom by going up, over, and down. Up, over, and down. Don't forget the order. So what I have here is a relationship between two matrices, H and H hat. We saw that at the very end of the check-in. We have a relationship between two matrices, H and H hat. They are related by somehow being H is right multiplied and left multiplied by these two matrices. H is right multiplied and also left multiplied by these two matrices. These matrices are special. They're the representation of the identity, so they are non-singular matrices. They're a special kind of matrix. So I have a non-singular matrix here, a non-singular matrix here. And so when we finished last time, the very last thing that we showed is we'll say that two matrices are related by the term for this relation is called matrix equivalent if there's non-singular matrices P and Q, where capital H is right multiplied by Q and left multiplied by P to get H hat. So two matrices are matrix equivalent if they have this relationship, and of course I'm interested in that relationship precisely because we're interested somehow in maps. So we're taking the point of view here, not to the exclusion of all other points of view, but we're taking the point of view that the primary objects are maps, and that the matrices are used to compute things about the maps. And again, that's not that matrices are foolish, or we never think about matrices. Indeed, in a few minutes we're going to think about matrices directly, the sort of combinatorics of matrix multiplication. But nonetheless, we try to take the point of view that matrices are about meaning, maps are about meaning, and so we want to understand meaning. So when two matrices represent the same map, they in some sense mean the same thing. So we want to say, when do two matrices represent the same map? And the answer is when they are related in this way. We want to come to understand this relationship. When do two matrices represent the same maps? When are two matrices related in this way? So we've seen this kind of when are things the same picture before. We will take the universe of all matrices and split it up into parts. These two matrices are related in the way at the top of the slide. These two matrices represent the same map. And over here are matrices that all are related to each other. Over here are matrices that are all related to each other. Over here are matrices that are all related. We split the universe of matrices up into parts. It's an equivalence relation that basically means that the parts don't overlap. So we split the universe of matrices up into parts where the parts that somehow H and H hat are somehow two different names for the same thing. It's as though you took my name, Jim Heffron, and my social security number, which I'm not going to tell you, and you put them together and say they both mean Jim Heffron. It's some dim analogy. So now how do I know, when I'm looking at a matrix, how do I know that it's, that it's related to this other one? So we want to find, in each part, we want to find one matrix that best sort of explains what that part is about. We saw that before. We saw, for example, in Gauss-Jordan reduction, we saw reduced row echelon form somehow best explains its part. Well, we get the same thing here, is that the matrix in each part has a certain form. The matrix that somehow best represents each part has a certain form. So an M by N matrix of rank K is equivalent to this matrix here, where there are K ones down the diagonal, and everything else in the matrix is zeros. So an M by N matrix of rank K. Do you remember what rank K means? Do Gauss's method. When you're all done, there are K, many, non-zero rows. An M by N matrix of rank K is equivalent to one that is all zeros except for K, many ones down the diagonal. We'll call that a block partial identity. You can see that the upper left is a partial identity. And it breaks the matrix up into 4 blocks. The other 3 blocks are all zeros. The upper left is an identity matrix. It's only part of the matrix, but it's an identity matrix. Okay, now as so often with the theorems, I'm going to do an example rather than the proof, but the example will persuade you about what's going on. So I'm going to recall that the non-singular matrices like P and Q can be factored into elementary reduction matrices, Gauss's steps matrices. So this is the matrix, remember, that takes K row I plus row J. This is the matrix that multiplies row I times K, and this is the matrix that swaps row I and row J. I want you to recall also from the mechanics of matrix multiplication, this is what I was talking about a minute ago. We don't sneer at matrices. We're looking at them here and here, but we try to take maps as primary. But that doesn't mean that matrices are beneath us. So remember again that from the left, matrices operate on rows. For example, here we're taking this is the matrix that takes -4 row 1 plus row 3. If you apply this matrix from the left, it acts on the rows, -4 row 1 plus row 3. And if you take the same matrix and apply it from the right, it acts on the columns. It happens to do -4 times column 3 plus row 1. It acts on the columns. So from the left, matrices operate on rows. From the right, they operate on columns. That's just the mechanics of matrix multiplication. I'm going to use those 2 pieces of information here to figure out how to write this matrix into block partial identity form. This matrix has rank 2. If you do Gauss's method, you'll get 2 non-zero rows and of course a 0 row. I'm going to find the P and Q. So, as so often happens in this class, it involves Gauss's method. I took the matrix and applied the Gauss's method steps. See the -4 row 1 plus row 2? -4 row 1 plus row 2. Remember, it's got to go on the right. That's because of the order in which these things get multiplied. -7 row 1 plus row 3, there it is. -2 row 2 plus row 3, there it is. Turn the diagonal entries into 1s, there it is. When you put those 4 together, they perform these operations. If you multiply them all together, and it took me a while to get it right, when you multiply them all together, you get this fella here. It just happens to be what you get. So far, the calculation that I have, acting on rows first, is that if you multiply here times the matrix we're interested in, I haven't figured out Q yet. If you multiply here by the matrix we're interested in, you get, it's not quite in block partial identity form. It's got stuff I got to get rid of, but it's starting to look like a lot of zeros, and there's 1s on the diagonal. starting to look like a lot of zeros, and there's ones down the diagonal. So to get the P, you do Gauss's method, arrive at echelon form, do that in matrices, remembering the order, multiply it all together, put it there as P. Okay, what to do next? How to get Q? So you'll remember that multiplying from the right, you act on columns. Multiplying from the right, you act on columns. So I did column operations. To get rid of this 2, we've never done column operations before, but they're not all that different from row operations. To get rid of this 2, I took minus 2 times column 2 and add to column 3. Minus 2 times column 2 and add to column 3. And then when you follow through, you can do that yourself. When you follow through, you take minus 2 times column 1, add to column 2 to get rid of that 2 kind of stuff, and then column 1 plus column 3, and you end up with this. So I use column operations to use this 1 to get rid of that 2, and then to use this 1 to get rid of the stuff to its right. You combine the reduction matrices to get capital Q. You see it over here. The only trick here is that in contrast with the construction of P, they go left to right. Minus 2 column 2 plus column 3 goes to the left. Minus 2 column 1 plus column 2 goes next leftmost. And then column 1 plus column 3 goes next leftmost. Because you see, here's the H right here. So this is the first thing done to H. This is the second thing done to H. This is the third thing done to H. So that's why they go left to right, whereas the matrices in the other half go right to left. So nearest H, next nearest, next nearest. Anyway, you put them down, P, H, Q, you get the block partial identity form. P, H, Q gives you the block partial identity form. It's not a proof, it's only an example, but it's pretty clear that you can do this with I's and J's, isn't it? One reason we're interested in this particular matrix, we think this is an especially handy matrix, is look, it's easy seeing what it does. If you take this matrix and multiply it by xyz, matrix vector multiplication by xyz, it gives you xy0. This is straightforward projection. This projects from R3 down to the xy plane. Now, this is a 3 tall vector, so I didn't say R3 to R2, but nonetheless, this is a straightforward projection down to the xy plane, so it's easy to understand its action. So from among all the matrices that are 3 by 3 and have rank 2, in some sense, this is the one whose action is easiest to understand on a purely mechanical level. So that's why I'm calling it the canonical representative, the somehow best representative of its class. The class is the 3 by 3 matrices of rank 2. So, matrix equivalence classes are characterized by rank. Two same-size matrices are matrix equivalent if and only if they have the same rank. And it basically boils down to they can be put in that form. They can all be put in that form, so they're all interrelated. If you have two 3 by 3 matrices, if you have a pair of 3 by 3 matrices of rank 2, then they're related. Both of them can be brought to this block partial identity form that we were just looking at. So you can, if you have A and B, and they're both 3 by 3 matrices of rank 2, you can bring A to the block partial identity form. You can bring B to the block partial identity form. So you could bring A to B by bringing A to the block partial identity form and then reversing the steps to get to B. So it's a big chunk. Every 3 by 3 matrix of rank 2 is equivalent to the one that we just had on the prior slide. Whoops. Here. Here also. Skip past it. Here also. Okay. So two same-size matrices with the same rank are equivalent to the same block partial identity form. Okay, very good. Okay, so that ends the material from change of basis. We pretty much nailed the problem. We completely understand which maps change to which other maps. And so next time we're going to do something different, going to do something with a little bit of geometry in it, orthogonal projection. So it's got some nice pictures that we can draw. Okay, very good. See you then. Hi. So we have some fun geometry today, but first, of course, we're going to do the check-in. So last time we talked about matrix equivalence. Two matrices are equivalent if they represent the same underlying map. We've talked about before how we try to take, and this guy's got to take some point of view, and the point of view we're going to take is that maps are the primary objects and matrices are what we use to compute maps. That doesn't mean that we sneer at matrices or they're beneath us or any such thing. That's not right. In fact, we've talked about them at some length before, but what it does mean is that the point of view we take is that it is fruitful to consider maps as somehow the underlying meaning of the subject, and we've seen that in a number of places. So matrix equivalence is when two matrices have the same sort of underlying meaning. We saw the result last time that matrices are equivalent if they are the same size and have the same rank. Rank means that you do Gauss's method, you count the number of non-zero rows in the echelon form, that's the rank. So here the problem says, here's 5 matrices and decide which of them are matrix equivalent. So I'm just going to do Gauss's method on those 5. All right, let's have a look. Let's see here. So number 1 is 1, 3, 2, 4. And I'm just simply doing Gauss's method, that's all. Minus 2 row 1 plus row 2. And I get 1, 3, 0, minus 2. So obviously the rank is 2. If I was going to write down the block partial identity, I'd have 2 1s. And everything else is 0. So it's actually just an identity. Number 2 is 0, 3. That's right. 2, 1, 3, 3, 2, 6, 3, 2, 6. Now I'll spare you the pain of watching me do the arithmetic. Everybody can do Gauss's method at this point, so I'll just say after you do Gauss's method in the standard way, you would get 1, 0, 3, 0, 1, minus 3, and 0, 0, 3. And there's 3 non-zero rows, so we're looking at a rank 3. For number 3, I have a variant on number 2, 1, 0, 3, 2, 1, 3. Instead of 3, 2, 6, I said 3, 1, 6. Now Gauss's method gives you 1, 0, 3, 0, 1, minus 3, and 0, 0, 0. So that here the rank is 2. If you were to do the block partial identity here, you'd see 2 1s. Everybody else 0s. Okay. So let's see. 4, 4, 2, 2, 1. Gauss's method gives you 4, 2, 0, 0. So the rank there is 1. And then finally 5, 3, 3, 1, 2. Gauss's method gives you 3, 3, 0, 1. So the rank is 2. So what we're seeing, for example, is that matrix 1 and matrix 5 are both 2 by 2 matrices of rank 2, so they're equivalent. Notice that matrix 3 is also of rank 2, but it's not 2 by 2, so not equivalent. The picture that we drew, we enclosed all matrices, and we broke the universe of all matrices up into parts, and parts are comprised of matrices with the same size and the same rank. So just as for instance, matrix 1 and matrix 5 belong in there. Well, matrix 2 doesn't belong with 1 and 5, so it goes in a separate place. Matrix 3 goes in its own place down there. Matrix 4 goes in another place. If you look at this fella here, that's a rank 2, 3 by 3 matrix, so it also goes right in there somewhere. In fact, because that's the canonical representative, that's kind of the most obvious one, matrix that is 3 by 3 and rank 2, you might think of it as somehow as being like the capital city of that region. It's the matrix that you think of first when you think of who's in that part of the universe. Okay, and again, this somehow represents a map. This somehow represents. These are in some way, these are both different names for the same map. There's a BD, there's a B hat, D hat. These are different names for the same map. So a thin analogy, but it's an analogy. You can imagine that instead of matrices, you can imagine that have strings. And in this section here are two different strings that both point to me. So you might have my name, Jim Heffron, and you might have your social security number. I'm not going to tell you my social security number. And they both point to me. So I am somehow the underlying object behind all of those names. Well, these two are different names. This is the point of view we're going to take. These two are different names for the same underlying map. Matrix equivalent. Okay, very good. All right, so what I want to talk about today then, the material for today is, as I mentioned, is a little bit of geometry. So projection. First, I'm going to start by talking about projection onto a line, orthogonal projection onto a line. So here's the picture. I have a line right there, and it's all the multiples of some vector s. So that's the span of some vector s. And there's another vector that I drew not on the line, and so I want to project that vector down onto the line. What part of the vector here, what part of the vector v lies with s? So I drew a picture, isn't it a terrible picture? I have a little person who walks out on this line until the tip of v is above their head. And then they say, now I'm there, this is the spot, put a stake down. So the picture I have is this. The person has walked out on the span of vector s. The person has walked out until they are at a place where orthogonal to CPS just touches the tip of v. That is to say, v minus CPS is orthogonal to CPS. So I have a nice right triangle there. To figure out what CP would be, you just use the orthogonality. Do you remember that orthogonal means dot product is 0? So I have v minus CPS dotted with s. I could have used CPS, but I just use s. It doesn't matter what multiple of s I use. They're all going to be orthogonal. So v minus CPS dotted with s gives 0. That's orthogonal. Dot product is 0. So you solve for CPS. You have v dot s on the top of the fraction. On the bottom of the fraction goes s dot s. So that's just a question of solving the equation. And the intuition is that I've decomposed v, this vector v, decomposed v into two parts. The part that lies with s, CPS, and the part that has no component in the direction of s at all. It's orthogonal to s. V minus CPS. Oh, I don't know why v doesn't have a little arrow over it. Oops. Anyway, v minus CPS has no part in the direction of s. So intuitively, when you look at the vector s, some part of it lies with s and some part of it does not. I broke v up, I decomposed v into two parts, and that's the two parts that we're looking at there in that picture. I'm just remarking here that I'm only going to work with real n spaces because I have a definition of angle for real n spaces. So I'll write that down as an equation. Here's the fraction that I just computed a minute ago. This is what I called CPS. So this is v dot s over s dot s multiplied by the vector s. So this is some multiple of the vector s, it's this particular one, is the projection onto, do you see that says span of s? So that's the line. The span of s, remember square brackets mean span. So that's the line of all multiples of s. Projection of the vector v onto that line, and which is just the calculation we just did. And these calculations are not hard at all. I mean, they're big to write, but they're not hard at all. So I made up some vector and I made up some line, all the multiples of 3, 1, 1, and I projected the vector down onto the line. I have, there's the fraction, there's the s, and here's what I get for an answer. You know, 1/3, 1/6, 1/6 is not a very big vector, but anyway, it's the right answer. This is the projection of this vector onto this line. I couldn't fit the picture on this slide, so the picture's on the next slide. Here's the vector v from the previous slide. Here's all multiples of the vector s. I got the computer to draw it for me because you've seen how I cannot draw. So what you see here is the reason that the projection, see the projection in red there? The reason that the projection is so small is because v is almost perpendicular to the blue line already. So because v has almost no component in the direction of s, you get a small projection. In fact, when you take out a calculator and do the calculation, the length of v is about 2.5, but the length of the projection is only about 1/2. So v does not have much in the direction of s, and we saw that in the sort of small components of the vector. Okay, I want to take that orthogonal projection and I want to generalize it to a bigger case. The prior subsection, the part that we just did, suggested that projecting a vector onto the line decomposes the vector into two parts. How much of v lies with the line and how much of v lies not at all with the line. How much of v lies with the line and how much of v lies not at all with the line. Because they are orthogonal, those two, they are in some sense non-interacting, and I have to give a definition for what non-interacting means, but we have the technology for all those things. Excuse me. So, a set of vectors are mutually orthogonal if any two of them are orthogonal. And an example would be the standard basis. That's a good model for orthogonal vectors. Here's another example, a kind of less trivial example, and we've been using these two vectors here in many a basis. When I do examples, I often pick a basis consisting of these two. There they are. You can see that they are at right angles to each other. If I want to make non-interacting precise, this theorem does it perfectly. Non-interacting in a linear algebra class means linearly independent. So the theorem just says that if you have vectors in a set that are mutually orthogonal and non-zero, then they have to be linearly independent. So mutually orthogonal and non-zero implies independence. And the proof is very straightforward. You write down the linear combination of the vectors, set it equal to 0, as you always do for a linear independence calculation, and you take the dot product with vi for any of the i's. Because they're mutually orthogonal here, vi dotted with v1 gives you 0, vi dotted with v2 gives you 0, etc. And you end up with vi dotted with 0 gives you 0, and so the whole thing gives you 0, and so you're looking at an answer of 0. So vi dotted with the linear combination gives you 0, and so you get that mutually orthogonal means linearly independent. And our interest in that is that in a k-dimensional vector space, in Rk, in a k-dimensional vector space, if the vectors in a size k set are mutually orthogonal and non-zero, then that sets a basis for the space. So if we have mutually orthogonal, we automatically get a basis. We're doing, of course, Rk here. And the reason is that the previous theorem says orthogonal gives you linear independent. If you're in a k-dimensional space and you have a linearly independent set of size k, you get span for free, and so it's a basis. So the definition is that an orthogonal basis for a vector space is just a basis of mutually orthogonal vectors. That orthogonal implies linear independence, so it's especially convenient. In fact, the calculations with these bases are often very, very straightforward. So a lot of times when we have to do some calculations, we will make the basis. We will be given a basis, and we'll instead make it orthogonal. We're going to see how to do that in just one second. Make it orthogonal. Before I go on to do that, I'll make a comment here, is that for many authors use the word orthogonal basis to mean not just that the vectors in it are orthogonal and non-zero, but also that the vectors in it all have length 1. I try to maintain a distinction between the two, but many authors do not. So if you're on the internet and clicking around and you see somebody says orthogonal basis and they have gone to the trouble of making all the bases vectors have length 1. That's why. They're using orthogonal to mean orthogonal and all of length 1. And that's very common. Okay, so here's the theorem. If you're given a basis, how do you turn it into an orthogonal basis? This is called the Gram-Schmidt orthogonalization process. Anyway, if you're given a basis, here's the basis, beta 1 through beta k. If you're given a basis, how do you turn it into an orthogonal basis? Okay, so the basic idea is pretty straightforward. For the first member of the new basis, you just take the first member of the basis you were given. For the second member of the new basis, you take the second member of the old basis and subtract away any part that lies with kappa 1. So you're taking any part of beta 2 that lies with kappa 1 and subtracting it away. So the only thing left will be the part of beta 2 that does not lie with kappa 1. And of course we saw that before. The part of, where's my picture? There we go. The part of beta 2 that does not lie with kappa 1 is going to be orthogonal to the span of kappa 1 is the basic idea there. For kappa 3, you take beta 3, you subtract away the part that lies with kappa 1, and then you subtract away the part that lies with kappa 2. And like that. Okay, so as we do so often, we won't give a proof here. Instead, we're going to give an example, and then the person watches the video with the example and then comes to the proof in the book with some intuition about how it's going to go. Here's first, we're going to give two examples. Here's the first example in R2. So I'm given two basis vectors. It's clear that they're not orthogonal. If you take the dot product, you don't get 0. I want to get a basis, kappa 1, kappa 2, that is orthogonal. So for kappa 1, I just simply take beta 1. For kappa 2, you take the part of beta 2 that does not lie with kappa 1, the part of beta 2 that has no kappa 1 in it. So beta 2 minus the projection onto the span of kappa 1 of beta 2. So beta 2 minus how much of beta 2 lies with kappa 1. What's left has no part that lies with kappa 1. Minus 2/5, 1/5, and you can see when you take the dot product of those two, you get 0. So the basic idea, the simple idea, I should say, simple idea is to take the second given vector, subtract away any part of the second given vector that lies in the direction of the first given vector. And what's left has nothing in the direction of the first given vector. That is to say, it's orthogonal. Another example. I have a basis, and I just made up some, you've seen me make these up before. They're not too big, not too small numbers. So to start, I take kappa 1 to be the first. As in the previous example, to take kappa 2, you take beta 2, the minus 1, 2, 1. You take beta 2 and you subtract away the part of beta 2 that lies with kappa 1. So this is the part of beta 2 that lies with kappa 1. And that's the calculation that we saw earlier, the part of beta 2 that lies with kappa 1. So the projection onto the span of kappa 1 of beta 2. And when you do the calculation, you get minus 3/2, 0, and you can check that when you dot product these two, you get 0. So indeed, they're orthogonal. And then the next step is the only one that could confuse a person. You take beta 3, subtract away the part of beta 3 that lies with kappa 1, and also subtract away the part of beta 3 that lies with kappa 2. So I'll say that again. Beta 3, subtract away the part of beta 3 that lies with kappa 1, and also subtract away the part of beta 3 that lies with kappa 2. What's left has no part in the direction of kappa 1 and no part in the direction of kappa 2. And the kappa 1 and kappa 2 are on the prior slide. Well, they're actually here and here. But you can check that if you take the dot product of this with those two, you'll get 0. Now, a person might say to themselves, well, wait, you're doing all this subtracting. Is it not possible you take away everything? Is it not possible you end up with 0, 0, 0 here, and that can't be a part of a basis? That's the thing that the proof has to check. The proof has to check that when you take beta 3 and subtract away these things, you can't end up with 0. Just a comment about the intuition there. Beta 3 can't consist only of a part in the direction of kappa 1 and a part in the direction of kappa 2, because if it consisted only of somehow parts from kappa 1 and kappa 2, then you wouldn't have a basis to start with. Beta 3 has to have some part all its own, some part that's brand new. Anyway, the proof goes through and shows that you can't end up with a 0 there. So here's a picture. This is nice geometry. So I got the computer to draw a picture for me because I can't draw these pictures. Here's the original basis I started with. For example, beta 1 is 1, 1, 2. So x equals 1, y equals 1, z equals 2. And the angles there are not right angles. They're just not. I mean, you know, if you take 1, 1, 2 and you dot product it with 0, 3, minus 1, you don't get 0. You just don't. But when I change to kappa 1, kappa 2, kappa 3, beta 1 is the same, but kappa 2 and kappa 3 are new vectors, derived from the old, of course, but new vectors. And you can see that what's happened here is that these three vectors are mutually orthogonal. Computer can draw it much better than I can. Those three red vectors are mutually orthogonal. And for some calculations that a person does, having mutually orthogonal makes the calculations much, much easier. So that's a thing commonly done in practice, is to change a given basis to one where the basis vectors are mutually orthogonal. And in fact, as I mentioned earlier, what's often done in practice is you go on to make the basis vectors not only mutually orthogonal, but also of length 1. You would take, for example, 1, 1, 2, and divide it by the length of 1, 1, 2 to get a vector of length 1. And you do that for all three. So that's to say we could go on to make this basis even more like the standard basis by normalizing all the members to have length 1, and you could call that an orthonormal basis. So the red, you take the red and you make all those vectors have length 1, you'd call that an orthonormal basis. I've mentioned before that many authors will, in fact, sort of always do that without saying it. They won't call it an orthonormal basis, they'll just call it an orthogonal basis, and they won't worry about the fact that that they haven't counted the normality. They'll just call that. So orthogonal basis often means orthonormal basis in practice. Okay, very good. So that ends chapter 3, so very exciting. The course breaks really into 3 parts. Chapter 1 and 2 is the first third, chapter 3 is the middle third, and then chapter 4 and 5 is the third third. So great, we're going to start in on chapter 4, so we're going to start in on the third third of the course. Very good, we'll see you then. Hi. Okay, so last time we went over a nice geometry situation where we were trying to find the orthogonal projection of vectors onto lines, and then we went on to apply that to get the to take a regular basis and turn it into a basis that's especially easy to compute with, namely a basis where the members are all orthogonal to each other, basis for Rn, where all the members are orthogonal to each other, and in fact you can then go on to make them all have length 1 and get an orthonormal basis. So that's naturally the check-in asks for an example of that, so let's get to it. Okay, so let's see here if I can get the basis down. Let's see, the basis that I'm given is a 1, minus 1, 0, 2, 0, 1, 3, minus 1, minus 1. Okay. And there's those basis vectors are not orthogonal. Just as an example, if you take the dot product of the first two, you just don't get 0, you just don't. So we want to derive from this basis another one where the members of the basis are orthogonal, mutually orthogonal, pairwise orthogonal. So what you do then is the first basis vector of the new basis, kappa 1, will just simply be the first basis vector of the old basis. That is, you've got to start somewhere. So our initialization is to start with kappa 1 equals beta 1. And then kappa 2 is you take beta 2, but that won't do because beta 2, that won't do by itself because beta 2 has some component in the direction of kappa 1. So this won't do for kappa 2. Instead, we subtract away the part of beta 2 that is in the direction of kappa 1. So let's see. That's 2, 0, 1 dot producted with 1, minus 1, 1. Oh, 1, minus 1, 0. I'm sorry. That's the top of the fraction. The bottom of the fraction is the dot product of 1, minus 1, 0 with itself. And this is multiplied by the vector 1, minus 1, 0. So I'm subtracting away the projection of beta 2 onto the line generated by kappa 1. So this is a multiple of kappa 1. I'm subtracting that away, and when I'm all done, I will have what's left in beta 2 when you subtract away any part in the direction of kappa 1. And I already did this out. So what did I get? I got 1, 1, 1. This is 2, 0, 1. Take away 2 halves of 1 minus 1, 0, and I got 1, 1, 1. Because if I tried to do this live, we'd be here for some time. So, so I worked it out in advance, and it comes out to be 1, 1, 1. So then kappa 3, a person can say, okay, but now you're starting to look at multiple interactions. Do I have to look at the interaction of the interactions? So that's why we go as high as 3 to do the general case. So kappa 3 is you start with beta 3, 3 minus 1 minus 1. And you subtract away the part of beta 3 that lies in the direction of kappa 1. So that's going to be, let's see, 3 minus 1 minus 1. Dot producted with 1 minus 1, 0. And on the bottom goes 1 minus 1, 0. Dot producted with itself, 1 minus 1, 0. And all multiplied by the vector 1 minus 1, 0. So this is the scalar and this is the vector. So this is the part of beta 3 that is in the direction of kappa 1. And now I'll subtract away the part of beta 3 that's in the direction of kappa 2. So 3 minus 1 minus 1. Dot producted with kappa 2, which is 1, 1, 1, 1, 1, 1. And then 1, 1, 1 dot producted with itself, 1, 1, 1, all multiplied by 1, 1, 1. I won't put a dot there just because I don't want to make the picture more confused than it actually is. And so I get here, this is 3 minus 1 minus 1. Subtract 4 halves. I know that's 2, but anyway, 1 minus 1, 0, and subtract away 1/3 times a 1, 1, 1. And when you do it all, you end up with what? 2/3, 4/3, no, 2/3, 2/3, and minus 4/3. Sorry about that, 2/3, 2/3, and minus 4/3. So the orthogonal basis is 1 minus 1, 0, comma, 1, 1, 1, comma, and then 2/3, 2/3, minus 4/3. And a person can see that these are mutually orthogonal. Just to pick two, how about if I pick the second and the third? If you take the dot product of the second and the third, you get a 2/3, a 2/3, and a minus 4/3, and it comes out to be 0. So that's right. Now, I cautioned you a couple times that in the literature, if you go online, for example, you Google around, you may very well find that when authors use the phrase orthogonal basis, they often mean orthonormal basis. That is, they go on to normalize every one of these vectors. They find the length 1 version of all of these vectors. So I'll go on and make the orthonormal basis. And so let's see. So the length of that is square root of 2. So I'll multiply 1 over square root of 2 to get 1 minus 1, 0. That's the first member of the orthonormal basis. The second is got length 3. So length square root of 3. So 1 over square root of 3 is the orthonormal version of this. Is the normal version of this. And the last one is what 4 and 4 and 16 makes 24. So 1 over the square root of 24 over 9 by 2/3, 2/3, minus 4/3. And you can really see why authors consider this to be kind of a trivial step. There's no interesting content there. But in any event, this basis is especially convenient for many calculations because all of the members are orthogonal to each other and because all of the members have length 1. Okay, very good. All right, so we're moving on to a new chapter. So I want to talk about what's in the new chapter, and it's let's see, what's the right thing to say here? It's a straightforward idea, but it's one that the execution will be sort of doing something that you may very well not have seen before. That many folks in the room, almost everyone in the room, has not seen the kind of approach we're going to take, and so that can throw a person for a loop. So, while we're going through it, I'll talk about the approach. That's of course not really mathematical content, but nonetheless, it helps sometimes to hear somebody say, "At this point, you should feel," sort of stuff. Okay, so I'm going to start by pointing out the importance of the idea of non-singularity. We saw it right away at the beginning of the book. Non-singular is where you have a square matrix, of coefficients it was at the beginning of the book, and you do Gauss's method and you don't have any zero rows. So non-singular means don't have any zero rows. Non-singular means sort of the kind of sensible, natural case. Of course, if you have zero rows, that doesn't make it not unsensible, that doesn't make it ridiculous, but it just means that you expect to find unique solution, and non-singular is the case where you did find unique solution. Maybe it's a psychological effect, not a mathematical effect, but there you go. So non-singular, nice in some sense. Non-singular is equivalent to all of these things, non-singular for a square matrix, is that if you have a linear system, it has a solution and solution is unique. Non-singular is equivalent to Gauss-Jordan reduction yields an identity matrix. So a person should be feeling, as we go through these bullet points, that every one of these is the nice case. The rows form a linearly independent set. The columns form a linearly independent set, which is a basis for Rn. Any map that is represented by T is an isomorphism. There's an inverse. The inverse exists. All of these cases give a sense of non-singular as whatever this means, desirable. Now again, in mathematics, we tend to avoid value judgments, but if a person is sitting there saying to themselves, I got this problem, and it would be great if the matrix turned out to have a unique solution, what you're thinking to yourself is it's desirable to have non-singular. Okay, so it's natural to be, you're looking at a matrix, let's say it's 20 by 20, and you're saying to yourself, I wonder if that fella is non-singular. So you can start in on Gauss-Jordan reduction, or just plain Gauss reduction, and look to see if you get any zero rows. That's a very sensible thing to do. But another sensible thing to do is to say to yourself, well, look, whether or not it's non-singular is a function of the entries of the matrix. So there must be, you think to yourself, there must be some formula that determines whether the matrix is non-singular. What's that formula? I'll just plug my entries into the formula. That's good. That formula is called the determinant because it determines whether the matrix is non-singular. So if a person was thinking to themselves, I wonder what the formula is, well, what would you do? You'd take out a pencil and you'd say to yourself, well, let's look at this. Let's look at the 2 by 2 and the 3 by 3, and we'll write down what the formulas are. We'll see the pattern. That's a good plan. We already saw the 2 by 2 case. The A, B, C, D is non-singular. Do you remember that we did the inverse of the 2 by 2 matrix? And the inverse of a 2 by 2 matrix turned out to have a fraction in front of it. That is, it was scaled by a real number. The fraction was 1 over AD minus BC. So obviously, in that case, you run into trouble getting the inverse if AD minus BC is 0. That is to say, if AD minus BC, if you multiply A times D and subtract B times C, if AD minus BC is 0, you find there is no inverse. If AD minus BC is 0, you find that the matrix is not non-singular. Said without the double negative, you find that the matrix is singular. So AD minus BC unequal to 0 is the non-singular case, is the case we're looking for. Okay, so that's a 2 by 2, we already did that. So now you take out a 3 by 3 and you write down the letters A, B, C, D, E, F, G, H, I, and you start in on Gauss's method. You take, let's see, I want to use the A to get rid of the D. So you take the negative D over A times row 1, add to row 2, but somewhere on the piece of paper you write down providing A is not equal to 0, and you cover that case separately, sort of stuff. And you start in and you do Gauss's method to end up with echelon form, covering all the cases like the A equals 0 case. You do Gauss's method to end up with echelon form, and you get this for a formula. Just like up here we got this for a formula, it's the bottom of the fraction. Here we get this for the formula, that's the bottom of the fraction. Same thing for 3 by 3s, except it's more complicated and I'm not going to show you. So it's somewhat reminiscent of what's up there. There's a not equal to 0, so that's very suggestive. but it's a little tough, not a little tough, it's kind of a lot tough to understand what's happening on the left-hand side. Well, let's ignore that for the moment, and let's just say the not equal to 0 is a pattern, and then you fall back on the one by one case, and then the one by one case is very straightforward, but it also has a not equal to 0. So in our mind, in what I like to think of as my mind, I'll imagine a family of formulas. AD minus BC. This formula here, too, that I won't repeat. There's a different one for each size matrix. And each formula defines a determinant function, det sub n by n, that inputs n by n determinants and outputs a real number. And then we say to ourselves, in what way does it determine non-singularity? Well, the matrix is non-singular if and only if the determinant is not 0. So we're thinking that the pattern shown here, the 1, 2, 3 pattern, it would continue for all n. And in fact, it will continue for all n, but it isn't perfectly clear what the pattern is it? Okay, so the plan is that the formulas don't make clear what should happen in the general n by n case. So we're going to do something that you may very well never have seen before. It becomes sort of more standard in mathematics as you proceed up through more and more sort of advanced levels, but this is, for many folks in the room, this is the first time they've ever seen it. So I'm going to talk about it for just a little bit. Instead of writing down the determinant function is calculated by this formula, instead what we're going to do is we're going to say the determinant function is described by these conditions. And then we'll go looking for a function that satisfies those conditions. Eventually we'll come up with a formula, but we're going to start off by saying the determinant function satisfies these conditions. Okay, and those conditions will let us compute the determinant of a square matrix via the same way we always proceed, which is Gauss's method, that we know is fast and easy. Now, I want to spend a minute talking about writing down conditions for a function. So suppose I told you that I was looking for a function that takes in natural numbers, 0, 1, 2, 3, and it outputs, when the numbers are multiple of 5, it outputs 0. You'd say to me, okay, you could do that. You'd say but there are lots of functions that do that. For example, there's the function that anytime you multiple 5, outputs a 0, but anytime you have something that isn't a multiple of 5, outputs a 1. That's a perfectly good function, and it satisfies your condition. Another function that satisfies your condition is it always outputs 0 under any circumstances. So you'd say, well, that's true. Those are two different functions that satisfy the condition that I stated. That's true. So you might state some other condition. Okay. So I'm looking for a function now that if you give it a multiple of 5, it outputs 0. And if you give it a multiple of 2, it outputs 1. Okay, now you're in a different circumstance entirely, because instead of there being lots of functions that satisfy in this case 2 conditions that you stated, now there are no functions that satisfy the 2 conditions, because what if you give the function 10? It's a multiple of 5, so the function should, to follow the first rule, output 0, but it's a multiple of 2, so it should, to satisfy the second rule, output a 1. So now there are no functions that satisfy the 2 conditions. So if you're going to say to me, I'm looking for a function that satisfies a list of conditions, okay, fair enough, that's fine, but you're going to have to go on at some point to verify that there is at least one such function, and also that there is at most one such function, because otherwise there could be many such functions or there could be none. So that's a situation you've probably never been in before. Probably in prior classes, Calculus 1 sort of stuff, whatever, you might have had like a combinatorics class or a statistics class. You probably, you write down formulas and then you say this formula describes a function. That's fair, that's great, but we're in a circumstance here where the formula is not clear. So instead, to describe the function, we're going to give a set of conditions, and then we'll use those conditions to allow us to apply Gauss's method to do the thing that you think we'd do. But because we are describing the function with conditions, we will at some point have to show that the function is unique. We'll do that today in this video. And we'll also have to show that the function exists. Okay, so that's the plan. Right? So we're going to have to show that the function is unique and that the function exists, and that's called showing that the function is well defined. Okay, so here are the conditions. I'm giving 4 conditions, and I'm saying that a determinant function has to satisfy these 4 conditions. And a person notices, you haven't had a chance to read it yet, but once you've had a chance to read it, your person notices that conditions 1, 2, and 3 are simply stating that in some way, this allows me to apply Gauss's method. What do you mean it allows me to apply? Well, for condition 1 is really the first one. It's really the main one that we ever think about. If you do k rho I plus rho j to the matrix, if you do k rho I plus rho j, then you get the exact same result. The determinant of the matrix before you do k rho I plus rho j, here it is the same as the determinant of the matrix after you do k rho I plus rho j. And of course, k rho I plus rho j is that combination operation is the heart of Gauss's method. So if the determinant before you do k rho I plus rho j is the same as the determinant after you do k rho I plus rho j. And then, of course, the next 2 lines are going to say something about swapping rows and multiplying a row by a scalar. So I'll cover them in just a second, but the point is that these 3 are the steps that you need to do Gauss's method. So saying I want a function that satisfies these conditions turns out to be saying that I want to be able to perform Gauss's method on these matrices and use that to determine the non-singularity of the matrix. Okay, condition 2 is that if you swap 2 rows, see how it says rho I and rho j over here, and then over here it says rho j and rho I? So if you swap 2 rows, then you change the sign, the SIGN of the matrix. So if the matrix had the sign of the determinant of the matrix, excuse me, I misspoke. So if the matrix had determinant 5, and then you swap 2 rows, the new matrix, the after you swapped it matrix, will have determinant -5. In the book, we go on, we do some examples to show that, in fact, that's what actually happens. So that's why this condition has the funny minus sign. You might say to yourself, why don't you just have an equal? And it turns out the equal doesn't give you what you want. But so certainly, if we're worried about being 0 or not being 0, changing the sign, changing the SIGN, doesn't affect being 0 or being not 0. And then condition 3 is somewhat reminiscent of condition 2. In the book, we go through some examples that show in the 2x2 and 3x3 cases, this is what happens. And so we project that this is what's going to happen in the 4x4 and the 5x5 and the 6x6, etc. In any event, what it says is that if you take a matrix and find the formula for it, the determinant, the function, in this case we're defining a function. If you take a matrix and find the determinant of that matrix, if you multiply a row by k, one row by k, not the whole matrix, one row by k, then you multiply the determinant, the entire determinant by k. So if, for example, you had a 4x4 matrix and you multiplied row 2 by 16, then you would multiply the determinant of the entire matrix by 16. So again, a person might scratch their head and say, well, why you don't need that? You could just say determinant after you multiply by k is the same as the determinant before you multiply by k. But the book goes through the examples that show, no, you do need this to cover the 2x2 and the 3x3 cases that we talked about. And besides, it's clear that if you're worried about non-zeroness versus zeroness, this won't have an effect. Multiplying by 16 won't change whether or not the matrix is 0. The determinant of the matrix is 0. Keep stumbling, I apologize. Whether or not the determinant of the matrix is 0, multiplying by 16 won't affect that. And then lastly, condition 4. I need the determinant of the identity matrix. So I'm going to do the simplest possible thing. I'm just going to provide the scaling factor of 1, that the identity matrix has the determinant of 1. If I wrote down here the determinant of the identity matrix is 5, then all the calculations we do in the rest of the chapter, and in fact in the rest of the book, would be bigger by a factor of 5. We're just going to take it to be 1. We often write here these up and down braces for the determinant of t. These up and down braces here might remind a person of absolute value, might remind a person of the length of a vector. So we have a general idea in mathematics of using these up and down braces to indicate size somehow of the included object. So the size of a vector is its length, the size of a number is its distance from the origin, and the size of a matrix, for reasons that we'll see in the next section, the size of a matrix is the determinant function. Okay. Okay, just a remark that condition 2, the condition about swapping rows, is redundant because you can accomplish swapping rows by using condition 1 and condition 3. So that's another thing about this minus sign in this k, is that in order to maintain consistency, you have to do certain things. But before we get into the details of that and get into those in the book, we really want to go on and calculate some things with the definition and get comfortable with the definition. So I'm going to take that, again, we're doing something that I don't know that a person has done before. So I'm going to take that definition, I'm going to provide a couple of results, and those results will enable me to calculate the value of the function. So again, I've defined a function, det, satisfying some conditions. I'm going to show in the lemma that we're about to look at, I'm going to show that if you satisfy some conditions, then it has these consequences. And we will use that to calculate the value of any function that satisfies those conditions. So something that a person has never seen before, recognize that, trying to help a person orient themselves. What the heck are we doing? What we're doing is, it's not clear what the formula is, so we're writing down some conditions. The conditions will allow us to do Gauss's method. That's how we ever determine non-singularity. All right, so just to go through them quickly here, I know a person can read, but a matrix with two identical rows has a determinant of 0. Just thinking in terms of non-singularity, that's what we want. If a matrix has two rows the same, then of course when you do Gauss's method, one of them would turn into the 0 row and you'd be singular. A matrix with a 0 row has a determinant of 0. Again, if you had a matrix that started out with a 0 row, you'd say to yourself, well, I know right away that's singular. A matrix is non-singular if and only if its determinant is non-zero. So that's what we want, that one there, that's the goal. And then finally, the determinant of an echelon form matrix is the product down its diagonal. So picture in your mind an echelon form matrix. Maybe you have sort of a 1 and then a 3 and then a 5 for a 3 by 3 matrix. 1, 3, 5 as the leading entries. The determinant of that matrix is going to be its echelon form, so it's got zeros below. Determinant of that matrix is going to be 1 times 3 times 5. Okay, so I'm going to verify the four statements one at a time. So to verify the first sentence, if it's got two identical rows, then it has a determinant of 0. So you swap the two rows. If you swap the identical rows, you get the same matrix. But one of the conditions says that the sign, the SIGN of the determinant changes. So the only way that could be is if the determinant is 0. For the second sentence, you have a row of all zeros. Multiply by 2. One of the conditions says that when you multiply by 2, you multiply the determinant. When you multiply one row by 2, you rescale one row by 2. You multiply the determinant of the entire matrix by 2. But when you multiply the 0 row by 2, you get back the same matrix. So the only way that could be is if the determinant as a whole is 2. It's going to be 0. Sorry. Now, the third sentence, remember before I switch over, the third sentence says a matrix is non-singular if and only if its determinant is non-zero. So that's the one we're super keen on. So the idea is if you give me a matrix and I do Gauss's method on it, I'll start with T and I'll get to T hat. By the first three properties of the determinant, T is 0 if and only if the determinant of T hat is 0. Now, don't get me wrong, you could have swapped some rows, so T hat might be, the determinant of T hat might be negative, where the determinant of T is positive. That could happen. Or you might have multiplied a row by some number, and so the determinant of T hat is K times the determinant of T. That could happen, but the zeroness or non-zeroness will be unaffected. Now, of course, a non-singular matrix T, Gauss-Jordan reduces to the identity matrix. And so if we take the identity matrix to be T hat, then we get, it has a non-zero determinant. Again, the SIGN or the sign or the size could have changed in the course of the Gauss-Jordan reduction, but the zeroness or non-zeroness does not change. And then finally, if you look at it, we looked at the non-singular case. Non-singular gives non-zero determinant. If you have a singular t, then it reduces to a t hat that has a zero row, and by the second sentence, then t hat's determinant is zero. And then since Gauss's method doesn't change the zeroness of the determinant, the determinant of t must have been zero also. So one thing that you're seeing here, there's another part we have to do, but one thing that you're seeing here is that the argument is a little slicker than you may be used to seeing really even in this class, but also in sort of calculus or again, whatever statistics class you might have had, whatever prior classes mathematics classes you might have had. So we are coming into something that we're starting with the very first sort of steps into some sort of more advanced mathematics, some sort of more abstract mathematics, which is exciting by itself for a person, but it also can be a little bit daunting. You say, well, this is not really the kind of way things I've succeeded at in the past have gone. That's right, but okay, so this just gives us something new to succeed at. I'll remind you what condition 4 is. Condition 4 says the determinant of an echelon form matrix is the product down the diagonal. So here we go. So the fourth sentence has two cases. If the echelon form matrix is singular, then of course the determinant of the matrix is 0. We saw that in the prior sentence, in the prior paragraph, which is the prior sentence of the lemma. And if you think of a echelon form matrix with a 0 row, multiplying down the diagonal at some point hits the 0 row, and of course at that point you're multiplying by 0, so the entire determinant is indeed the product down the diagonal. Okay. On the other hand, if the echelon form matrix is non-singular, then none of its diagonal entries is 0. So you're looking at something like this. Remember, the vertical bars here on the matrix means determinant. So you do the condition that allows you to bring out. So you multiply the entire you bring out you bring out the T11 from the first row, you bring out the T22 from the second row, all the way out, you bring out the TNN from the third row, and you'll remember that when you bring out T11 from the first row, it multiplies the entire determinant by T11. T22 multiplies the entire determinant by T22, and etc. Now you have ones down the diagonal. If you continue on with Gauss-Jordan elimination, you will eliminate up. These things will go away, and you have all zeros there. You've got the identity matrix. The determinant of this is 1. That's condition 4. And you're just looking at the multiple of the TIIs. So, the conditions enable you to get to echelon form. The conditions enable you to bring the TIIs out, although they rescale the determinant by a factor of TII. And then the conditions allow you to do the Gauss-Jordan part, and you get here the identity and without swapping any rows, so there's no sign change, and you're just looking at T11, etc. Okay, so here the determinant of this echelon form matrix is indeed the product down the diagonal. There's no possibility of having to do row swaps, so you don't have to worry about sign changes. Okay. So all that, again, I'm aware of, I'm sympathetic to a person's sense that something is happening that they maybe never have seen before or not seen all that much. But we're now back on maybe more familiar ground, so that'll help a person feel like they haven't been steamrolled. So I'm going to take this matrix and perform the Gauss-Jordan familiar steps, Gauss's method steps, and get to echelon form. So this is a 3 by 3 matrix. I know we have a formula for the determinant of a 3 by 3 matrix, but I'm going to do Gauss's method on it. So minus 2 row 1 plus row 2, minus 3 row 1 plus row 3. I perform those two steps and I got to echelon form. Now, those two steps do not change the determinant. So this says determinant of this equals determinant of this. That's condition 1. And determinant of this equals determinant of this. That's condition 1. Again, these combination steps don't change the determinant of the matrix. So I have the determinant is unchanged. And now I recognize this as echelon form. So the determinant is the product down the diagonal, whatever the heck that is, 14. So the determinant of this is 14, so the determinant of this must be 14, so the determinant of this must be 14. So Gauss's method allows us to calculate the determinant of a matrix. We're back to the definition of the function by its conditions. We're saying that we want a function that satisfies these four conditions, and the reason for those four conditions is not a big secret. The reason, the sort of higher level reason for the four conditions is they allow us to do Gauss's method to determine whether or not we get zero for the determinant, to determine non-singularity. There's this business with the minus sign and the business with the k, again, is explained at greater length in the book, but from a higher level description here, these are recognizable as the Gauss's method steps. And so we find ourselves, not that what was here, was gibberish, but after some step into something that is perhaps a little bit not 100% perfectly familiar territory, we're back on calculating. And so we're going to calculate. One of the jobs of this class is to try to help a person get more comfortable with these more abstract ideas, because they are bigger ideas that you can think bigger thoughts with these abstractions, but we're always trying to make it concrete. So here we are back on concrete. The Gauss's method steps give us 14. 14 seems pretty concrete to me. Here's another example. Suppose I look at this matrix, and clearly in order to do Gauss's method, I got to start off by doing a row swap. All right, so do a row swap. That changes the sign. The condition tells me that one of the conditions in the definition of determinant tells me that I'm looking for a function that has the property that when you do a row swap, you change signs. Well, now I'm ready. This matrix is familiar. Minus row 1 plus row 3, and then minus row 2 plus row 3. I'm carrying the negative sign. See, this negative sign gets carried, and I end up over here. Ignoring the negative sign for the moment, this is an echelon form matrix. Multiply down the diagonal. 1 times 3 times 1 makes 3. Along with the negative sign, I get a negative 3. So Gauss's method, keeping track of the row swaps and also keeping track of any factors that you multiply, that you factor out of the determinant, Gauss's method enables me to calculate the determinant of a matrix, because the definition is exactly calibrated to allow me to do the Gauss's method steps, the most important of which are these combinations like minus row 1 plus row 3 and minus row 2 plus row 3. Okay, then, of course, I illustrated two of the conditions, so of course I'm going to illustrate the third. Here I have 5, 10, 3, 4, and here I have 1, 2, 3, 4. And the relation that condition 3 gives you is that if you factor out a 5 and you go to 1, 2, 3, 4, that doesn't just sort of multiply sort of half of the matrix, so you get a 5 halves. No. Factoring out a 5 multiplies the entire matrix by 5. Well, the determinant does. The entire matrix by 5. So factoring a 5 out of one row scales the entire determinant by 5. All right, but the 1, 2, 3, 4 is not hard. We know the formula for the 2 by 2, so you can probably calculate it in your head right now. But I'm going to go through the Gauss's method step because that's what I'm illustrating. So I carry the 5, carry the 5, carry the 5. 1, 2, 3, 4 minus 3 row 1 plus row 2 gives you this. That's an echelon form matrix. 1 times minus 2 gives a minus 2. Don't forget the 5. The whole thing is minus 10. So the contrast is that when you multiply one row by 5, you get a determinant that is 5 times as big. So before we go on here, before we stop, I'm going to give you a caution. You probably noticed that AD minus BC has something to do with these diagonals. The AD and the BC has something to do with the diagonals. Some folks watching this will have learned in calculus class, I know I learned in calculus 3, that we didn't really learn what determinants are, but we learned a formula for the determinant of a 3 by 3 matrix, which is you write the first two columns down. Please, we're not going to use this formula. There's nothing wrong with it, but we're focused on something else. But I want to warn a person who may be misled. So I learned in calculus 3, you write down the first two columns. Then you multiply down those diagonals, the A, E, I, the B, F, G, the C, D, H, see them there? and then you subtract the backwards diagonals, the GEC, the HFA, and the IDB. And a person says, well, that's kind of like this is a forward diagonal, this is a backward diagonal, you subtract the backward diagonal. These two are kind of the same. Don't try, please, don't think that you've got it now. I understand the pattern. Don't try to extend it to 4 by 4 or larger sizes. Instead, the right thing to do, it's much faster, it's much easier, we're very familiar with it, so it's very hard to make a mistake. Use Gauss's method. So the purpose of the definition of determinant that I gave you, determinant is a function described by these 4 properties. The purpose of that definition is to use Gauss's method because Gauss's method is fast and accurate. So don't be misled into thinking, oh, this is what I learned in Calculus 3 and I'm, smarter than other people. I'm going to use, no, you're just fooling yourself. Okay, so I told that silly example of the function that does something with multiples of 5 and something with multiples of 2. So as we described before, the definition of determinant, defining a function by giving conditions has a downside, and that is that we have to verify that there is such a function, and furthermore, we have to verify that there isn't more than one such function. So we have to verify existence and also uniqueness. Well, as to existence, somebody might say, how could there fail to be such a function? What do you mean? I've been computing the outputs. So I'm going to point out that you can do Gauss's method in more than one way. When I introduced Gauss's method, I of course introduced it by doing all the problems the same way because that's how you teach. You don't teach by saying, well, you could do this or you could do this. That's a good way to have a disaster. But it is nonetheless the case that you can do Gauss's method in a number of different ways if you choose to. I can take 1, 2, 3, 4 and do the obvious thing of minus 3 row 1 plus row 2. Or I could take 1, 2, 3, 4 and then swap the first 2 rows. And then do minus 1/3 row 1 plus row 2. And you could say, well, why would you do that? But you could. Now, in this case, both of them yield a determinant of minus 2. Don't forget here that you swapped a row, so if you're worried about determinant, you got to keep track that the determinant now will be the negative of the determinant in the starting matrix. But just because we got consistent results in this case doesn't mean that we have to get consistent results in every case. So the rule, if you're thinking in your head something like, well, determinant is just, do Gauss's method, keep track of the minuses and the scale factors, and then at the end multiply down diagonal. You've got the right formula. That's how we're going to do it. You're absolutely right. But if you're thinking to yourself, why do I need to do more? The mathematical problem is that there's more than one way to do Gauss's method, and we have to verify that doing it by different ways won't give a different determinant answer. That's the problem. Okay. So we have to verify existence and uniqueness. Uniqueness will turn out to be easy. We're going to do it in just a second. But existence will turn out to be a bit tougher. Okay, so before I give any other ways to compute the determinant, that we're going to give a formula. Instead, I'm going to first do uniqueness. So in order to show that the determinant function exists, I'm going to give an explicit formula for computing it, although it's a formula that you shouldn't use to compute it because it takes a long time. But nonetheless, I'll give a formula that'll solve the theoretical problem of is there such a function? But before we do that, I want to settle the problem of uniqueness. So I want to show uniqueness that if there is a function satisfying the conditions that we gave at the start of this video, then there's in fact only one. So we'll find ourselves in, again, a circumstance that you may not have been in before, you likely not have been in before this class. So we are worried about whether there is a function. And we're going to show that the function exists. It's going to be that there's a formula that exists, and so it computes the function. And it'll turn out to be a formula that we won't use, but we'll show that one exists. And then we also have to verify uniqueness. So we are going to, when I close the video at the end of this slide, we are going to know that the function is unique, but not know whether it exists. That's okay. I mean, you can only do so many things at a time. We're going to do uniqueness first. Turns out to be easier to do uniqueness. Okay, so for each n, if there is a determinant function, then there's only one. And the basic idea here is you suppose there are two, and you come to the conclusion that they calculate the same function. So you suppose there are two functions, det1 and det2, satisfying the properties, and you're given a square matrix. I'm going to show that they compute the same output for every square matrix M. So you're given a square matrix, you fix some way of performing Gauss's method. You might think that you're just going to write a computer program, and this computer program is going to perform Gauss's method to get to echelon form. Now my computer program and your computer program might not be the same program. Mine might, for example, for no sensible reason, start out by swapping the first two rows. So we might proceed by different ways, but nonetheless, we're just going to start here, fix some way. So in your mind, you fixed a way to perform Gauss's method that goes to echelon form. It doesn't matter which way, just fix one. By using this reduction, as in the above examples, keeping track of the row scaling factors and how the signs alternate, then we compute the value that these two functions have to return on M. My computer program always computes the same value for a given M. So DET1 and DET2, which says if you follow the rules, you'll compute a value, DET1 and DET2 have to work with my rules. So if DET1 and DET2 exist, they have to compute the same value for M because the rules say, because they both accord with the rules. So if there is a function, I'm not saying there is a function, we will in the next video, but if there is a function, then there's only one function. Okay, so again, very mindful of the fact that a person is put, many folks in linear algebra are put in the position that they've never been in before of thinking a little bit more abstractly about functions, and not that it's super hard, but just that it's a new circumstance, and a person can sometimes say, never been here before. Am I thinking the right thing when? Okay, so next time we'll talk about the properties of determinant, and we'll start developing the formula that computes the determinant function, and that therefore shows that there is a determinant function. Okay, very good. Hi. All right, so last time we started in on chapter 4, we worried about whether or not a matrix is non-singular because it seems to be such a key property, and so we're looking for basically a formula to determine non-singularity. Now, the way we phrased it last time is that we're actually finding a function to determine non-singularity, and we're eventually going to develop a formula that determines non-singularity, a formula that calculates the function. But at the moment, we're worried about formulas that determine non-singularity because we, as you see in the check-in, we already have the 2x2 version and the 3x3 version of those formulas, and we're determined to use them. So I simply want to emphasize that we're describing the non-singularity of matrices, non-singularity versus singularity of matrices, and so that's what the check-in is about. All right, so a relatively easy one here just asks me to calculate the formula. So I have a matrix, it is 2, 1, minus 4, 2. 2, 1, minus 4, 2. Okay, and so I'm going to calculate AD minus BC. So that's 2 times 2. Two times 2. Whoops. 2, 1. Oh, minus 4 minus 2. I'm sorry. 2 times minus 2 minus 1 times minus 4. So I get to minus 4 plus 4 equals 0. And in fact, when I think about it, the second row is minus 2 times the first row. So we have this is singular. Okay, so we have a formula that determines singularity, and in the 2x2 case, it's worth memorizing, AD minus BC. The 3x3 case, on the other hand, it is not worth memorizing, or at least not worth memorizing unless you're going to do an awful lot of these. So let's see, I wrote it down here, A, B, C, D, E, F, G, H, I equals, and I don't have it memorized, so A, E, I plus BFG plus CDH, and then subtract HFA, subtract CDB, and subtract GEC. And again, we went over last time. I gave a little bit of a warning. There are various mnemonics that you can use here to try to describe what the what these formulae is. You do something with the diagonals and the backwards diagonals, but I'm going to skip over that because it sometimes causes confusion, and I'm just simply going to describe it as just a kind of involved, not grossly involved, but a kind of involved formula. All right, so now when I go to look at 1, 3, 1, 2, 0, minus 1, and 0, 1, 3. And as opposed to the first problem, it was pretty clear that the second row was a multiple of the first. Here, I don't know, it could be that 5 times the first minus 2 times, I don't know, some kind of thing. So I'm going to do the calculation and see if I can do it. It gave me a little trouble when I was trying to do it here in preparation. So 1 times 0 times 3 plus 3 times minus 1 times 0 plus 1 times 3 times 1. And then the minuses are 1 times minus 1 times 1 and 3 times 2 times 3 and 0 times 0 times 1. So what do we get here? That's a 0, that's a 0, that's a 3. That's a 1. And that's a, forgive me, that's a 2. I'm sorry, 2. And that's a 2. There we go. And that's a 1. And that's, let's see, 3 times 3 is 9, times 2 is 18. And that's a 0. Okay, so when all the smoke clears and when I correct the mistake that I made up here, I've got 2 and 1 makes 3, minus 18, so we're looking at minus 15. And I don't actually really care at the moment in this section. I don't care about the size. We'll care about that in the next section. But at the moment, all I care about is whether it is 0 or not. And it's non-zero, so non-singular. Non and non. So modulo copying down the wrong digit, the calculation is reasonably straightforward, although the formula is a little bit hard to remember. Nonetheless, the goal is to come up with a way of determining non-singularity, at least in principle, determining non-singularity. Okay, so let's see here. We're ready for the material for the day here. Oops. Again, I hit the wrong button. I hit the wrong button a lot. It's a little discouraging. There we go. So I'll remind you where we are. We are trying to figure out here. We already have uniqueness. So we are trying to figure out a formula that calculates the determinant. And the reason why we want a formula that calculates the determinant, we already have Gauss's method, and it works very well, very fast, so it's a good method. The reason we want a formula to calculate the determinant is because we want to prove that there is a determinant function. So remember, we're in this somewhat odd circumstance where we defined, it wasn't clear what the formula was. So instead we defined the determinant function by some properties. Those properties allowed us to do Gauss's method. But when you define a function by properties, it isn't perfectly clear that there is such a function, nor is it perfectly clear that there's only one such function. You have to verify those things. So we've already verified that if there is a function, there's only one. So we verified uniqueness. And now we're going to verify existence. In order to verify existence, it's a little more involved. We're going to build up a sort of technology to use the properties of the determinant as described in the definition to calculate the value. So basically, we're going to build a formula, except that it's more involved than just saying, here's the formula and check. Okay, so the real lesson here, the lesson for today, is that this is a course called, remember, it's called linear algebra, and the determinant function is not a linear function. So it is not the case. Do you see the word not there? Not. Not the case that the determinant of k times t is k times the determinant of t. It just isn't. Here's an example here. So I took 3 minus 3, 9. I doubled it to get 6 minus 6, 18. And I calculated the determinant of this fellow. I calculated the determinant of this fellow. You can imagine I used the formula that I just used in the check-in. And it just simply doesn't double. It just simply doesn't. It doesn't. That's all there is to it. Okay. So here, if you look at, I doubled the 3's minus 3, 9 to get 6 minus 6, 18. I doubled the 1, the minus 1, 7 to get 2 minus 2, 14. I doubled the 2, 4, 0 to get 4, 8, 0. I don't get double the determinant. I just don't. Instead, what condition 3 says is that the determinant scales one row at a time. So, if you take the 6 minus 6, 18, and you bring it back to the 3 minus 3, 9, that brings out a 2, and the 2 multiplies the entire determinant. So bringing a 2 out of one row multiplies the entire determinant. If you go on and bring the 2 out of the second row to make a total of 4 at the beginning here, a product of 4, then what you get is, again, doubling, bringing 2 out of one row, out of a single row, doubles the entire determinant, and finally bringing 2 out of the bottom row, making the 480 into 240, bringing 2 out of the bottom row, again, doubles the entire determinant. So in fact, what's the relationship between these two numbers? Well, this one is 8 times that. So the lesson is the determinant function is not linear. Instead, it's one row at a time. These k's come out one row at a time. Determinants are not linear. With scalar multiplication, the scalars come out one row at a time. Well, a person can say, well, okay, well, I remember linear. Linear involved bringing out scalars and also involved breaking along a plus sign. So what happens with pluses? Good question. Of course, pluses and times are related in the usual grade school way, that if you have an apple and an apple, that's 2 times the apple. So here, if you, for example, imagined the 2 times written this way, or imagined it written this way, then that corresponds. See how the determinant is breaking along that plus sign in that row? The determinant is I wrote 2 row I as row I plus row I, and then I got 2 times the determinant over here by writing determinant with a row I and determinant with a row I. So this suggests that the determinant is breaking one row at a time for pluses as well as for scalar multiplies. Now this doesn't prove, but it strongly suggests. And in fact, it's true. So determine a function that satisfies the 4 conditions that we saw in the last video is not linear, but it's what's called multilinear. Here we see that the k on a single row comes out to be k times the entire thing. And here we see what we were just exploring on the previous slide. A plus on a single row comes out to be a plus of the entire things. A k on a single row is k times the entire thing. A plus on a single row is the plus of the things. So determinants are linear sort of one row at a time. And that's called multilinear for the obvious reason. You can't call it linear because it simply isn't linear. And I got to verify here the 2 conditions that are listed there. Property 2 is just simply condition 3. So there's no need to verify it. I have to go on and verify property 1. There are 2 cases. Again, we saw this last time. This material is a little bit more abstract than some of the material, especially we saw in the beginning of the class. But part of the goal of the class is to raise a person's ability to cope with abstractness. So we're periodically salting in a little bit of more abstract material, helping a person to get comfortable with seeing these kind of higher level thinking sort of things. All right, so there's going to be 2 cases to show that condition 1 is true. There's going to be 2 cases. You look at all the other rows, not the v plus w row, not the v row, not the w row. All the other rows, the ones that are called with the Greek letter rho. So row 1, row 2, all the way up to row I minus 1, row I plus 1 through row n. That's a set of rows. It's a set of row vectors. If that set is linearly dependent, If, for example, row 1 is 3 times row I minus 1, if that set of rows is linearly dependent, then that matrix is singular because it doesn't involve v plus k, it involves the other rows. That matrix is singular because it doesn't involve v, it involves the other rows. And that matrix is singular because there's some linear dependence among the other rows. All three would be singular because I have a linear dependence among the rows, a linear dependence among the rows, and a linear dependence among the rows. So I'm looking at 0 equals 0 plus 0, so the statement is true. Okay, so if the set of other rows is linearly dependent, then the three matrices are singular. The determinants of everybody is 0. 0 equals 0 plus 0, we're done. So clearly the other case is that the set of other rows is linearly independent. So we've been in this game for a while now, and I think a person can see what to do, or at least have some idea of what to do. I know it's abstract, but still a person can have some idea of what to do. When you have a set of n minus 1 many linearly dependent things, what you think to do is to throw in one more. So you have a set of n minus 1 linearly independent things. I think I might have misstated it. Set of n minus 1 linearly independent things. And you think to throw in one more and get a basis. So that's the plan. We think to throw in one more, I'm calling it beta, to get a basis. Of course, I'm going to express v and w with respect to that basis. Again, we've been playing this game for a while now, so it has a certain, the tunes have a certain familiar rhythm. So we express v and w with respect to that basis. I chose vi for the coefficient of beta and wi for the coefficient of beta here. And I'm comparing. There's the v, there's the w, there's the v plus w. You consider the left side, and you expand the v plus w. There we go. Oh, I meant to click back and show you the left side. Remember the left side has a v plus w in it? So you've got the determinant. There's the v plus w part. And I have a row I, and there's a row I. So I'm going to do Gauss's method on this. I'm going to take minus v1 plus w, row 1, added to this row right here. Again, minus v1 plus w1, row 1, added to this row right here. And of course, what that'll do is that'll get rid of this. Same thing, I'm going to take minus vn plus wn and add it to this row right here. Minus vn plus w, oh, so I said that wrong. Minus vn plus wn times this row, add it to this row right here. Again, because I said it wrong. Minus vn plus wn, add it to this row. Minus vn plus wn times this row, add it to this row. As I go through the Gauss's method steps, and I can eliminate everybody except for beta. I go through the Gauss's method steps, and from this determinant, I eliminate everybody except for the beta part. Okay, all right. Well, there's a multiplier, so bring it out. I brought it out. Vi plus wi, I brought it out. Now break this regular grade school, maybe it's junior high school, distribution along this plus. There's Vi times the determinant plus Wi times the determinant. And now bring the Vi back in, bring the Wi back in, put all the row 1, row 2, row 3 parts back together using the combination operations, which it doesn't affect the determinant at all, and you're back to the original 2. Okay, so that was a little bit tricky, but not brutally tricky, but a little bit tricky. Okay, so before I go on, though, I want to make a remark. I know that in this internet age, a lot of times when people are studying material, they'll Google around and they'll find something here, find something there, and piece it together. I often do that when I'm trying to learn new material. So here's the definition of multilinear, and here's the original definition that we gave of the determinant function. I have to click back a little bit. I'm sorry. There. Many authors, if you go and look on Wikipedia or you go some other linear algebra material, many authors will use multilinearity in the definition of determinant. It's just a different approach. I like this approach right here. I like this particular definition where you derive multilinearity from it. It's a little more involved sometimes, but I like it because it seems less abstract. To a person who is not all that comfortable with abstraction, because this, for many folks, this is the first course where you see abstraction. For such a person, this at least seems related to Gauss's method. And then from that relatively familiar definition, then we get the property of multilinearity. So we proceed sort of from familiar to new material as opposed to sort of jumping right in feet first to new material. Just a different approach gets you the same answer. So what you're seeing when you click around to other sites, they're all getting the same answer. We're just, sort of somewhat different ideas about how to do that. Okay, so what's the point of multilinear? So here's the point of multilinearity. So it got a little abstract for a moment. We're back on solid computational ground. Here we go. I'm going to take 1, 2, 3, 4 and expand it using multilinearity. So 1, 2, 3, 4. 1, 2 is the sum of 1, 0 and 0, 2. So I'm allowed to break 1, 2, that row, into two separate determinants, the determinant with 1, 0 and the determinant with 0, 2. I mean, I could have broken into 1, 1 and 0, 1. I could have. That will turn out not to be fruitful, but I could have done that. But instead, I broke it into 1, 0 and 0, 2. Well, you see the game. 1, 0, I can look now at the 3, 4 row and break that into a 3, 0 and a 0, 4. So the 1, 0, 3, 4 breaks into these two. The 0, 2, 3, 4 breaks into these two. And what I've got now is 4 matrices. You could say, well, you made 4 problems out of 1. That's true. But some of these problems are very easy because look, this one, the 2 rows are multiples of each other. So that's 0 right away. There's a linear dependence among the 2 rows. That right there must be a singular matrix. Boom, 0 for a determinant. Right here, those 2 rows are multiples of each other. So that's got a determinant of 0. Boom, done. So I'm down to 2 different relatively easy matrices. This one here, what's the determinant of this matrix? Well, it's an echelon form matrix, so you multiply down the diagonal. So 4. What's the determinant of this matrix? Well, it's not echelon form, but one row swap will make it echelon form. So you do one row swap, remember the minus sign in your mind, and now it's a diagonal matrix with 2's and 3's on the diagonal, so the determinant is 6. So in total, we have a determinant of minus 6 because a swap followed by multiplying the diagonal gives you minus 6. So we get 0, 4, minus 6, 0. Add the 4 and the minus 6 together, and you've got a minus 2. So I turned this is not a complicated problem, but a relatively complicated problem into 4 relatively easy problems. Okay. Next one, 3 by 3. So you've seen the game here, so you can play the same game. I broke this up into here. You break the 1, 2, 3 up into 1, 0, 0, 0, 2, 0, and 0, 0, 3. Then for each of those 3, you break it up into 4, 0, 0, 0, 5, 0, and 0, 0, 6. And for each of those, what's that, 9 so far? For each of those 9, you break up into 7, 0, 0, 0, 8, 0, 0, 0, 9. And you get a whole bunch, 27 of them in total. You get a whole bunch of determinants, a lot of them, exponentially many, 27 determinants. But each of them is straightforward. So just to go through a couple here. So here, first row, second row, they're multiples of each other. Boom, 0. First row, second row, they're multiples of each other. 0. First row, second row, they're multiples of each other. 0. First row, third row, multiples of each other. 0. Second row, third row, multiples of each other. 0. So what you're seeing is I'm getting a whole lot of problems, but most of them, not all of them, this one isn't 0, but most of them are very easy. The 1, 5, 9, what's the determinant of that? Well, 5 times 9 is 45. Here, first row, third row, multiples of each other. Here, one row swap will make this matrix be a diagonal. So the determinant of this is negative sign 1 times 8 times 6, so that's negative 48. Okay, so the determinant of this, Boom, 0, because second row, third row. Well, so like that. You proceed along in this way, sometimes doing row swaps to get yourself an echelon form matrix, but a lot of times just saying, boom, 0. And you get a relatively simple answer. So anytime you have two or more rows that are multiples of each other, the determinant of the matrix is 0. So I've reduced to a sum of determinant where each matrix is all zeros except for a single entry in each row and each column. Can we go back here? Over here, there's an entry here, actually 3 entries in the first column, so that's a 0. There's 2 entries in the first column, so that's a determinant of 0. 2 entries in the first row, in the first column, so that's determinant of 0. There are 2 entries in the second column, so that determinant is 0. Down here, 2 entries in the third column, so that determinant is 0. So what we're getting then is we end up with everybody 0, except for if you have a single entry in each row, a single non-zero entry in each row and column. So there's 3 places to put the first. There's 3 columns in which you could put the entry from the first row, and then there's 2 columns remaining, and then there's 1. So there's a total of 6 of those. So the 27 that I got, almost all of them are 0, except for 6 are non-zero, or potentially non-zero. And there we go. And those 6 are relatively straightforward. Mentioned that that one is 45. Mentioned that that one is minus 48. I apologize. Minus 48. That one is minus 72. That one is, doesn't that one take 2 row swaps? So that one's plus 84. That one is, I don't have to go back and change these minus signs and plus signs. I apologize. I flubbed this up. That one, so if you take 1 row swap or 0, if you take 0 row swaps, then you're good. You just multiply down diagonal. If you take 1 row swap, then you have to have a minus sign. If you take 2 row swaps to go back to a diagonal matrix, then you're back to plus. 3 row swaps would take you back to minus. I apologize about these pluses and minuses. That's a typo. I'll have to fix that. So after bringing out each entry from the original matrix, we're left with matrices that are all zeros except for a single one in each row and column. So this determinant right here, inside 48 is what it'll be. But the determinant of this matrix will be -1 because it takes 1 row swap to bring this to the identity. Determinant of this one, I'm sorry, I really should have said this. The determinant of this one is -1 because it takes 1 row swap to bring it to the identity, swap row 2 and 3. Determinant of this one is +1 because it takes 2 row swaps to bring it to the identity matrix. Determinant of this is -1 because it takes 1 row swap to bring it to the identity. And the determinant of this is +1 because it takes 2 row swaps to bring it to the identity. So we have a sum that this is all correct, but I should have put in the plus and minus ones here. So I got to go in and make a correction and mark that it's pluses and minus ones. Okay. Okay, so very good. So what we've got then is we develop multilinearity. Multilinearity allows us to break a determinant up into many smaller jobs, each of which is either 0 or very straightforward. Okay, very good. So we'll stop there and then and work with multilinearity on the homework, and then we'll go on and work some more with multilinearity to come out with the formula for the for a determinant. We won't use that formula to calculate determinants because it's too big and awkward. We'll always use Gauss's method, but of course there's an advantage to having a formula. The advantage is that it shows that there is such a function because the formula computes the function. Okay, very good. Hi. Okay, let's recap where we are. So we were looking for a formula that takes in the entries of a matrix and decides whether or not the matrix is non-singular. So we tried the 2x2 matrices, the 3x3 matrices, and what we found was we got some kind of formula, and then it said unequal to 0. So the matrix is non-singular if and only if whatever formula it is unequal to 0. Now, the formula was not very clear. It was not instantly evident what the pattern was in the formula. So instead of trying to figure out what the pattern is, we shifted strategies. We did something that maybe is not completely familiar from previous classes, probably you never saw before. And we've defined a function the determinant function, that is given not by a formula, but instead not by an algorithm, but instead is given by properties. So the determinant function is the one that has the following properties, and there were a total of 4 properties. The point of those properties were that they allowed us to use Gauss's method to figure out whether or not a matrix is non-singular, which is of course our standard way to figure out whether or not a matrix is non-singular. The difficulty with describing a function by properties is that it could be that there's more than one such function. It proved early on to be easy to show uniqueness, so we finished that problem. But it also could be that there's no such function, and you'll remember an example where I said I'm looking for a function that returns 0 on multiples of 5 and returns 1 on multiples of 2, and a person might say, well, what happens if you input a 10? And then you're in trouble. So you have to establish that there is at least one version of the function. That's the existence problem, and that's the one we're dealing with now. We're trying to show that there exists a function given given the set of n by n matrices, that there exists a function det sub n by n. There exists a function that takes in the matrix, it does something with the matrix entries, and then puts out a number, and if that number is 0, the matrix is singular. If that number is non-zero, the matrix is non-singular. So last time we talked about, we're on our way there, and we talked about multilinearity. Multilinearity is a property of determinant functions. It comes straight from the definition, and we are going to use it. Last time we used it to expand the matrix. We are going to use it to come up with basically a formula. A formula that computes the function computed by any function with those properties. So I didn't really say that very well. So given the 4 properties, this function computes the value of the determinant. So since there's a function that computes it, we'll figure it must be that the determinant, since there's a formula that computes it, it must be that the determinant function exists. Okay, so long story. The short version is that we are worried here about multilinearity. So the check-in is just reminding ourselves about multilinearity. So here we go. Speaking of reminding ourselves, what the heck? Oh, so here we go. So for question number 1, I was looking for the determinant of 5 minus 1, 3, 4. And of course, we have a formula to compute 2 by 2 determinants. So let me go through that. So you multiply the corners, right? So 5 times 4 minus 1 times 3, and so that's 20 plus 3, so 23. Even I can do that, 23. Question 2 said use multilinearity to expand the given matrix. So that's the new idea. 5 minus 1, 3, 4, and remember the vertical bars mean determinant. We haven't paid too much attention to the size of the number here, 23. We'll do that in the next section, but we've noticed here that because 23 is not 0, we have non-singular. So the vertical bars mean something like how big is this matrix, and 23 is big enough, meaning not 0, to be non-singular. Okay, so let's look at the multilinear expansion using the property of multilinearity. So the idea is you think of the first row, 5 minus 1, that's a 2 wide row vector, and you say to yourself that's 5, 0 plus 0 minus 1. And so we're allowed to break along that plus sign, and we get the determinant 5, 0, 3, 4, plus the determinant 0 minus 1, 3, 4. Okay, so multilinearity allows us to break along a plus sign, and we're choosing to break along a plus sign that's going to generate a lot of zeros. You can do the same thing on the second row, so you end up with 5, 0, 3, 0, 5, 0, 0, 4, and then 0 minus 1, 3, 0, and 0 minus 1, 0, 4. Okay,
So a person could say, very sensible of a person to say, look, you had a problem, wasn't a very complicated problem, and now you made it into 4 problems. How's that progress? And the answer goes, at least part of the answer goes something like this. 5, 0, 3, 0, those two are multiples of each other. That is to say, there is a linear dependence between those two rows. So boom, boom, that's 0. That's a singular matrix. We know that singular matrices, any function that we're giving the name det will, when presented with a singular matrix, produce a 0. Likewise here. Oh, so it's at least not exploding in size, getting bigger but not exploding in size. Okay, so what about the others? Let's see. So I'm going to write this. We saw last time that the right thing to do is to write 5 times 4 times the determinant of 1, 0, 0, 1. And we saw in the video last time that we want to think about the determinant of that fella. And then likewise over here, I'll get minus 1, 3 times the determinant of 0, 1, 1, 0. Oh, and there's the plus 0. I didn't get it all in the same line. All right. Okay, so so what the heck is happening here? Well, this is identity matrix. Identity matrix has a determinant of 1, so this is 20. Let's see, that's a minus 3, of course. What's going on here? Well, this isn't an identity matrix. In fact, it's a permutation matrix, you might remember from a previous section. But in particular, you can make it an identity matrix if you do one row swap. Swap the 2 rows that are there, one row swap, and it'll turn it into an identity matrix. So that means that the determinant of this is minus 1, because every row swap changes the sign, the SIGN of the determinant of the matrix. So one row swap would change the sign. So we're looking at plus minus 1 times 3 times minus 1. And obviously I get the same answer. Okay. Okay, so the lesson from multilinearity is that it allows us to break a job up into many, many small jobs, a lot of which turn out to instantly have an answer of zeros. The ones that don't have an answer of 0, what you do is you factor out the numbers from the original matrix, the 5 and the 4, the minus 1 and the 3. Factor out the numbers from the original matrix, and what's left is a matrix that has 1, 1 in each row, and also 1, 1 in each column, a single 1 in each row, and a single 1 in each column. You calculate the determinant of those folks by, if necessary, row swapping them to be the identity and remembering how many row swaps, because each one changes the SIGN. Each one changes the sign. Okay? Okay, so multilinearity proves to be a way to turn a big job into a lot of, but still smaller jobs. And each of the smaller jobs proved to be routinely easy. Okay, so now from the check-in, we recognize that the matrices that we got, when you bring out the members, the entries from the original matrix, what's left is then is a permutation matrix. Permutation matrix, we defined it earlier, is square. Every entry is 0 except there's a single 1 in each row and column. I'm going to introduce some notation for permutation matrices that unfortunately looks a little more awkward than it actually is, but anyway. So a permutation is a function that takes the first n numbers as input and returns the first n, those same first n numbers as output. The function is 1 to 1 and onto its correspondence. So the basic idea, let's look at phi 2. I'm going to use phi for permutations because phi is kind of like a p. So let's look at phi 2 for permutations. 1 maps to 2, 2 maps to 1. I basically shuffle the numbers 1 and 2. And I'm usually not going to use this function notation. I'm usually going to use this notation instead to say that phi 2 shuffles the numbers 1 and 2. It takes a 1, 2 and it turns it into a 2, 1. So the 2, 1 is it's like you shuffled cards. That's the shuffle. Here's an example. It's a little easier to look at bigger examples. These are all of the shufflings, all of the mixing ups, if that's a word, of 3 numbers. So you can take 1, 2, 3 and shuffle them into 1, 2, 3, or shuffle them into 1, 3, 2. That's all the ones that begin with a 1. Here's phi 3 and phi 4 are all the ones that begin with a 2. 2, 1, 3, 2, 3, 1. Phi 5 and phi 6 are all the ones that begin with a 3. 3, 1, 2, 3, 2, 1. So just to pick on one here, let's look at phi 4. So the idea is that this notation is that phi 4 is a function. 1 maps to 2, 2 maps to 3, 3 maps to 1, and we're going to choose this particular format because it will prove to be convenient. One more bit of notation. I'm sorry, there's a lot of notation here. I apologize. One more bit, though, is that if you have a row vector that's all zeros except for a single one, I'm going to, in entry j, I'm going to denote that with an iota j. So that, for example, the 4 wide row vector iota 2 has the 1 is in position 2. And now, if our notation for permutation matrices is if you give me a permutation, some kind of shuffling of the numbers 1 to n, then the rows of the matrix are iota sub phi of 1, etc., through iota sub phi of n. And if that's too much notation for you, this example, I think, makes the whole thing clear. If you give me a permutation, a shuffling of the numbers 1 to 4, 2, 4, 3, 1. I don't know, I just made up a shuffling of the numbers 4. The first row is going to have its 1 in position 2. The second row is going to have its 1 in position 4. The third row has its 1 in position 3. And the fourth row has its 1 in position 1. And a somewhat shorter way to say that is that this is iota 2, this is iota 4, this is iota 3, and this is iota 1. So it's really the defining is more complicated than the actual doing. Sometimes that happens. All right. So you'll remember from the very beginning of this video that we are looking for a formula. Our goal is to find a formula that computes the function defined by the 4 properties. If we have a formula to compute the function defined by the 4 properties, why then that function must exist. So this looks an awful lot like a function. Here we go. It says the determinant of an n by n matrix is, and then there's a bunch of multiplies and pluses, the kind of stuff. Looks a lot like a function. This is just the check-in. You'll remember that the check-in we used multilinearity to expand it to be a sum of a lot of smaller, easier determinants. Many of them dropped out, became 0. The ones that didn't drop out had the property that they had a single entry from the original matrix in each row and a single entry from the original matrix in each column. Okay, well, I factored them out. Remember the 5 and the 4 I factored out, and the -1 and the 3 I factored out from the check-in? Well, that's what I did here. I factored out those numbers, factored out those numbers, factored out those numbers, and what's left is a permutation matrix, determinant of a permutation matrix for the first permutation, determinant of the second permutation matrix for the second permutation, etc., etc., etc. So this looks an awful lot like a formula. There are things multiplied together and then added up kind of stuff. Let me write it down here in the somewhat more compact notation, the summation notation. It says on the left the determinant of t. I'm using t because this is a square matrix, so you can see it as a map from, for example, Rn to Rn. So it's a transformation. This is the sum over all possible permutations. Remember, for example, there were 6 3 permutations, and there were 2 permutations, for example, of terms of the form. So what does each term look like? Well, you fix the phi sub. This is phi sub 1 in each case. This is phi sub 2 in each case, all the way down to phi sub k in each case. So you fix the phi sub. That's what I did. I fixed a phi. And then it goes t1, phi of 1, t2, phi of 2, t3, phi of 3, etc., all the way out to tn, phi of n, multiplied by the determinant of the associated permutation matrix. Okay, so this is basically, essentially, a formula. A formula that says, since we derived it using the properties of multilinearity and even further back, the properties defined in the definition of determinant, this is basically, turn that off, there we go. This is basically the formula to compute, this is a formula, to compute the determinant of a matrix. Now, we won't actually compute things this way. It turns out that this particular formula is very slow, but it's useful for the theory. Very often convenient for the theory. Okay? So just to illustrate. So you recall that there are two permutations. The identity one, and the one that interchanges 1 and 2. So those are the associated permutation matrices. And if I want to take an arbitrary 2 by 2 matrix, remember on the check-in I had, 5, -1, 3, 4. So I factor out the entries of the original matrix. In this case, it's 1, 1, and 2, 2. So in the places where those ones are, I factor out the entries of the original matrix. In this case, it's the corners where the ones are here, and then I compute the determinant of the permutation matrix. That has a determinant of 1. That has a determinant of -1. Because remember, one row swap brings it to the identity. Okay, so there I go. This is a formula which computes this determinant. Now, we already had a formula for 2 by 2s, but my point is there's nothing stopping you from doing this for 4 by 4s or 100 by 100s or 2000 by, or whatever size makes you happy. If you rename these from subscripts to letters, you get AD minus BC. So what's happening now is that we have what amounts to a formula for calculating the determinant, any function satisfying the 4 properties, for calculating the determinant of a square matrix. There it is. I like this version, but you may like this version. We're basically done at this point. We simply do these calculations here. When we get to the determinant of the permutation matrix, you can swap it to become the identity. Do however many swaps. If it's an even number of swaps, then the determinant is +1. If it takes an odd number of swaps, the determinant is -1. And you get the determinant of this matrix because there's a formula for the determinant of this matrix. Then there must be a function satisfying the 4 properties. Okay? Not quite. Not telling the whole truth, close to the whole truth, but not telling the whole truth. Here's the issue, technical issue. When you go to swap these permutation matrices to be the identity, you can do it in more than one way. You could, for example, swap row 1 and row 2, swap them back again, and then go off and accomplish something useful. So technically, in order to have a formula, we have to prove that when you find the determinant of a permutation matrix, there's only one possible answer. It can't be the case that you swap to get the determinant of a permutation matrix and you end up with +1, and I swap around to get the determinant of the same permutation matrix and I get -1. That can't happen. That's a technical issue, and the next section is optional because it's really not because it's silly or dopey, but just because it seems to have a little less to do with linear algebra than some of the other topics that we cover. But nonetheless, a person would very legitimately feel, looking at that slide with the permutation expansion, okay, I'm satisfied. That's a formula. I can see where the formula came from. Comes from multilinearity, and I'm going to move on. So the next section is optional, is what I'm telling you. Because the next section is optional, a person who didn't take it would miss the 2 results there. So I'm going to quote them for you. The first result is what we've just been talking about, that for every n, there's an n by n determinant function because there's a formula to compute it. We will give a formula to compute the determinant of permutation matrices in the next section. So that there's a form that completes the permutation expansion formula. So for every n, there's an n by n determinant function, and that was a long job, a theoretical job. As I mentioned, one of the goals of the course is to help a person raise kind of their level of abstraction, raise sort of their level of ability to work with these kind of abstract ideas. And so the right way to do that is periodically present people with the abstract idea and work through it, and they keep going back to concrete ideas. All right, so not apologizing about it, not embarrassed about it, but just to give a person some sense of what's happening. And then there's a result that follows from that we will find that we will find convenient in a number of places. We will need in a number of places, and that is that the determinant of a matrix is equal to the determinant of its transpose. You remember what the transpose is? The transpose is where you take the matrix and turn the rows into columns and turn the columns into rows. And the determinant of those 2 matrices will be the same, and that's a result in the next section that we'll need from time to time. In particular, this last result, we can prove it in the next section, but a lot of people will skip the next section, so I'm only quoting it here. In particular, for this last result, the fact that the determinant of a transpose equals the determinant of a matrix allows us to transfer results. Any statement about rows in determinants becomes statements about columns. For instance, the first condition in the definition determinant is that the determinant is unchanged by row combinations. If you do k row I plus row j, you don't change the determinant. Now, because of that last result that I just quoted, because the determinant of a matrix is equal to the determinant of its transpose, that same statement holds for column operations. If you have a matrix and do the column operation of k row I plus row j with I unequal j, of k row I plus row j, then you also don't change the determinant of the matrix. So this fact that the transpose of a matrix has the same determinant as the matrix gives you a transfer that you can transfer statements from row properties to column properties. So just as an example, a matrix with 2 equal columns is singular matrix, has a determinant of 0. Another example, column swaps change the sign of a determinant because row swaps change the sign of a determinant. If you want to prove that column swaps change the sign of a determinant, start with a matrix, transpose it, swap the rows, that makes the determinant negative, transpose it back. The columns have swapped. And another example, determinants are multilinear in their columns. Of course, we saw the result that they're multilinear in their rows, but by transpose, you get the determinants are multilinear in their columns. Okay, so you transpose the matrix, and then you transpose it back, and that's how you turn statements about columns into statements about rows. Okay, so again, the next section is optional, so a person who is watching these videos could very sensibly just simply skip it, go on to the section after that, and the other consequence is that we're going to start when we do the next section, we won't have anything, we won't have a check-in, just so that a person doesn't miss that. Okay, all right, very good, very good. So we'll see you next time, whatever next time is. Hi. I went away there for a second, but I'm back. Okay, so last time we talked about that we've boiled the problem down to now showing that the determinant is defined, functions satisfying the 4 properties exist, provided that we can show that the determinant of permutation matrices is well defined. Many instructors will leave it there and move on to other material. If you want to see that full development, then we're going to cover it here on this slide, on this video. But because it's optional for many instructors, we're not going to do the check-in. We're just going to proceed along with the material, just so that a person who skips it doesn't miss the check-in. Okay, so we're showing that determinants exist, and what remains to show is that the determinant of a permutation matrix is well defined. In order to show that the determinant of a permutation matrix is well defined, what we've got to do is come up with a way to calculate it. And so here's the way to calculate it. If you give me a permutation where k is bigger than j, then we say that they are in an inversion of their natural order. And similarly, in a permutation matrix where iota k comes before iota j, we say that the 2 rows are in an inversion of their natural order. So an example tries to make a little clearer what's happening here. So if you have 3, 2, 1, the 3 comes before the 2. That's in an inversion of the natural order of numbers. The 2 comes before the 1. That's in an inversion of the natural order of numbers. And the 3 comes before the 1. That's in the inversion of their natural order. I have a little table here that helps a person keep track of who's before who. The 2 comes before the 1. The 3 comes before the 1. And the 3 comes before the 2. So I count 3. 1, 2, 3. 3 inversions of natural order there. So I am trying to figure out somehow a way to find the determinant of a permutation matrix, and I'm going to compute the determinant of a permutation matrix by assigning some number to it, and that number is going to have to do with the number of inversions, that basically the number of row swaps it takes you to get back to the identity. Here's another example. So I have a permutation matrix. In each row is a single one in each row and each column. I said that backwards. So there's a 1 in each row and each column. Everybody else is zeros. That's iota 2 because the second entry is the 1. That's iota 1. That's iota 4. That's iota 3. So looking there at the 2, 1, 4, 3, we can see that 2 comes before 1. 3 and 1 are good. 3 and 2 are good. 4 and 1 are good. 4 and 2 are good. And by 4 and 2 are good, I mean that it's not the case that 4 comes before 2. Instead, it's the opposite. But 4 comes before 3. So I count a total, this is my little bookkeeping device, I count a total of 2 inversions. And of course, I'm interested in calculating the determinant of a permutation matrix, so I'm interested in how many row swaps, an odd number or an even number of row swaps, does it take to get from the permutation matrix you're given to the identity matrix. Because remember, each row swap changes the sign, the SIGN of the determinant. So this lemma says a row swap in a permutation matrix changes the number of inversions from even to odd or from odd to even. If you do a single row swap, swap 2 rows, any of them, row 5 and row 23. That will change the number of inversions from even to odd or odd to even. That is, it flips the parity of the number of inversions. The book contains a proof, as happens so often. I consider these videos to be a kind of run-up to the book. You would look at the videos first, and then you would try to follow along in the book. So I'm going to do an illustrative example, and that way when a person comes up to the book, they say, oh yes, I remember that part. So here we go. There are 2 cases. The 2 cases are that the rows are adjacent, and the second case is that they aren't adjacent. So here's what happens when you swap adjacent rows. Row 2 and row 3 here. I'm going to swap them, and you see that I've swapped row 2 and row 3. I'm going to count the number of inversions. So here is what happened, and here's what happened. So it used to be the case that that I had iota 1 and then iota 3. But we swapped these 2 rows, and now I have iota 3 coming before iota 1. And we see that here. It used to be the case that 1 and 3 were in their sort of natural relationship. Now it's the case that 3 comes before 1. So we added exactly 1 inversion. These other x's, and for that matter the non-x's, things that are not this box here, are unaffected by the changing of by the swapping of these 2 rows. The only thing that's affected is that it used to be the case that 1 came before 3, so it don't get an x. Now it's the case that iota 3 comes before iota 1, so it does get an x. Okay, so that's for adjacent rows. What happens when you swap non-adjacent rows? Okay, so what happens, for example, if you take these 2 permutation matrices and you swap row 1 with row 4? See up here, row 1 was iota 4, and now I swapped it, so down it goes to the bottom. Here, row 4 was iota 3. I swapped, so it goes up here to the top. Well, to swap these non-adjacent rows, I'm just going to do a sequence of swaps of adjacent rows. So to get row 1 down to row 4, I'm going to swap row 1 and row 2, and then I'll swap row 2 and row 3, and then I'll swap row 3 and row 4. And now, after those steps, what used to be row 1 is all the way down to the bottom of the matrix. Now, the bottom has not come up to the top yet. I'll get to that. But what was at the top has gone down to the bottom. Okay, so let's take the iota 2 that used to be at the bottom and move it up. So you swap row 3 and row 2, you swap row 2 and row 1, and you're moving iota, oops, here it is. You're moving iota 2 all the way up to the top. That was 1, 2, 3, 4, 5 row swaps. So even non-adjacent rows will take an odd number of swaps, each of which flips the parity of the number of inversions. That is, I took 5 swaps. We know that each swap flips the parity. So the total number of flips of the parity is, right, in total, the parity switches because there's an odd number of swaps. So whatever the parity was, maybe it's even, switches to odd after an odd number of swaps, or if it was odd, it switches to even after an odd number of swaps. So the way I'm going to find the determinant of a permutation matrix is I define this function, the sinum. Sinum of a permutation is -1 if the number of inversions is odd, and it's +1 if the number of inversions is even. So that is to say, I want to give here a formula for calculating the determinant of a permutation matrix, and I'm going to calculate the determinant of a permutation matrix not by doing Gauss's method or something. Instead, I'm going to count the number of inversions. The number of inversions is related to the number of swaps, and then I'll be done. So just as an example, here's the permutation 3, 2, 1. There's the associated permutation matrix. There's obviously an odd number of inversions. 3 comes before 2, 2 comes before 1, 3 comes before 1. And so the signum is -1. The permutation 3, 2, 4, 1 has 4 inversions. So the signum is +1. So you take the number of inversions. If the number of inversions is even, you write down a +1 for the outcome of this function. If the number of inversions is odd, you write down a -1 for the outcome of this function. Obviously, given a permutation matrix, you can count the number of inversions. Look, I just did it. So given a permutation matrix, you can count the number of inversions. And so you can decide +1 or -1. There's no question about whether that's defined. And that's what I'm looking for. I'm looking for a no question about whether that's defined. You can't do this two different ways. Definition of the determinant of a permutation matrix. So if a permutation matrix has an odd number of inversions, then swapping it to the identity matrix takes an odd number of swaps. If a permutation matrix has an even number of inversions, then swapping it to the identity matrix takes an even number of swaps. In other words, we can find the determinant of a permutation matrix by counting the number of inversions. We don't have to do those swaps. We can count the number of inversions. And you can say, well, I don't think that's nearly as clear. I don't care. All I care is that you can only count the number of inversions in one way. But you can swap the permutation matrix to the identity in more than one way. So it's not clear that you have well-definedness of plus or minus, but it is clear that you have well-definedness of number of inversions. That part's clear. So this represents the goal. This is the thing we've been working for. And it's actually straightforward, but often corollaries are you got to the end of all the work, and so the work is all done here. The identity matrix has 0 inversions. To change an odd number to 0 requires an odd number of swaps, and to change an even number to 0 requires an even number of swaps. That's okay. So very straightforward. So, whoopee, I have a little celebration JavaScript animation here. So we're trying to show that a function exists that satisfies the 4 conditions in the definition of determinants. We have to show that for each input square matrix, there is a well-defined output value. Like Gauss's method can be done in more than one way, so it isn't obvious that by keeping track of the signs and by multiplying down the diagonal, we always get the same output. That if I do it one way and you do it the other way, we'll guarantee to get the same number. So instead, what we did was we produced the permutation expansion, and that left us with reducing the entire problem to finding the determinant of a permutation matrix. But the corollary that we just saw says that the determinant of a permutation matrix is the signum of the permutation. The determinant of a permutation matrix is the signum of the permutation. So I replaced that in the formula, and now, after a lot of work, we've got that desired formula for a determinant. So the advantage of this formula is that the number of inversions is clearly well defined. You can count them, like I've done a couple examples of counting them already. So we'll be done if we show that D satisfies the conditions in the definition of determinant. Okay, so a lot of work finally getting to the sort of success here. So the lemma says that the function D is a determinant, and therefore determinant functions exist. So we show that determinant functions exist by producing a formula for the determinant. Again, said many times, but say it one more time. In practice, to calculate a determinant, if you have a homework problem that gives you a 4x4 matrix, to calculate a determinant, we won't calculate it this way. This way is very slow. I mean, maybe there'll be an exercise that says use the formula to calculate the determinant, but typically in practice, you will use Gauss's method to calculate a determinant. But the existence of the function guarantees that there is the existence of the formula guarantees that there is a determinant function. That's what we needed. Okay, so the book has the proof which verifies the definition of determinants for conditions. Instead, I'm going to go through an illustrative example, and when you see the example's pretty involved. You'll see why we're not going through the sort of the details of the proof. Not that they're embarrassing, but just that you got to start with numbers before you go to letters. Okay, so here's the D expansion. Remember this? Did you notice? I'm not calling this DET, I'm calling it D because we haven't yet established that it's DET. Okay, so this is the D expansion for a 3 by 3 matrix, and doesn't it look just exactly like the permutation expansion? Of course it does. I don't have room on the slide. I'm sorry, it just took too much space on the slide. So instead of using SGN, I wrote S, 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 and S. I'm sorry, it's just a question of real estate, that's all. Okay, and I'm going to illustrate the proof's verification of the for condition by using the 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix, just because I'm not a very creative person. Okay, so condition 4, that the determinant of an identity matrix is 1, is you go back and look here and you say, well, in the determinant matrix, A, F, and J are 1, everything else is 0. So if you have anything other than A, F, and J, you're multiplying by 0. Anything other than A, F, and J, anything other than A, F, and J, anything other than A, F, and J, anything other than just A, F, and J, you're multiplying by 0. So you're just left with this, and so you get 1. Okay, and the other conditions are verified in much the same way. I'm going to go back to that formula and check that the cases work. Some of them are more detailed, of course more involved, but the basic idea is I go through the conditions and say, does condition 1 hold, does condition 2 hold, does condition 3 hold, that kind of stuff. Condition 3, so I'm going to multiply a row by k. Okay, so I chose here to multiply the second row by k. When you go back to that formula 2 slides ago, I won't go back every time, but maybe I'll go back this once. When you go back to this formula here, here's the expansion. There's a 5K, a 6K, a 4K, a 6K, a 4K, and a 5K. Every one of these terms has one single K in it. None of them have 0, none of them have 2. Every one of these terms has 1K. Factor out the K, the result is K times this big, as it was 2 slides ago. Okay, condition 2. So condition 2 talks about row swap changing the sign of the determinant. So we have to check that, for example, if you swap row 2 and row 3, that the determinant will have its sign changed. So we're going to check that if you swap rows 2 and row 3, then the D function has its sign changed for this one matrix. And of course, I'm going to try to do it in a way that suggests how the proof goes. Okay, so here we go. I'm expanding. This is the expansion up here. This is the expansion of the left-hand side. The D expansion of the left-hand side. This is the D expansion of the right-hand side. And of course they're different because they have different things in the second entry and that sort of stuff. But they match up in some way. Do you see that the 159 matches up with the 195? Do you see that the 168 matches up with the 186? And the 249 matches up with the 294? And the 267 matches up with the 276, like that. Okay, all right, so a person sees that. So the two match term by term. For example, the two 159s match up. Let's check again the two 159s. Okay, 159 and 195, obviously not an important difference. And now let's look, what does the signum say and what does the signum say? Well, in swapping row 2 and row 3, I went from a 111 there to a there. So in swapping row 2 and row 3, I went from an identity matrix that has 0 many inversions to a permutation matrix that has 1 inversion. 168. I have there a permutation matrix that a single row swap would take it back to the identity. Down here, 186, I have a permutation matrix that takes 0 many row swaps to go to the identity. So again, the difference is 1 swap. So the SIGN of this term is different from the SIGN of this term. One's plus and one's minus. And likewise here, the SIGN of this term is different from the SIGN of this term. One's minus and one's plus. One more, you get the idea, but one more. Okay, so 249 matches with 294. What's the difference? Well, let's see. How many row swaps does it take to make this the identity? I think a single row swap will make this the identity. How many row swaps does it take to make this the identity? I think you have to swap 1 and 3, and then I think you have to swap 2 and 3. So this will have this will take one row swap to get to 0, to the identity. This takes 2 row swaps to get to the identity. So the sign of this and the sign of this are opposite. Every one of these terms has the opposite sign from the associated term below. Again, the 159 has the opposite sign, the S part has the opposite sign from the S part of the 195. The 168 has the opposite sign, the S part has the opposite sign from the 186. The 249 has the opposite sign, the S part has the opposite sign from the 294, and like that. So this and this are negative, term by term, negative. Okay, last condition, the row combination condition, and this is the most involved one. It's a little on the tricky side. I don't want to say tricky, a little big. It takes a lot of real estate. Okay, so I used the numbers 1 through 9 already, so I took 10 times row 1 plus row 2. And I'm going to compare left and right. I'm going to take the D expansion left and right. So here's the D expansion on the left, and of course I didn't all fit on one slide, so the D expansion on the right is on the next slide. What do I mean by the D expansion on the left? Why, first I took, this term, this term, this term, sort of this term, this term, this term kind of stuff. So here we go. The second matrix has this D expansion. If you break along the plus signs, then you get two sums. You get the 159. There we go. I'm breaking along this plus sign, that plus sign, that plus sign, that plus sign, etc. You see the 159, there'll also be a 129. You see the 168, there'll also be a 138. You see the 249, and there'll be a 210.9, like that. And here they are. There's the 159, there's the 129. Here's the 168, there's the 138. Here's the 249, there's the 210.9. All right, so I just simply did regular real numbered, whoops, I went to the wrong place. There we go. Did regular real number distribution, went to the wrong place, there we go. Regular real number, I distributed over the plus sign, etc. Okay? Factor out the 10. Okay? Factor out the 10. 10, 10, 10, 10, 10, 10, 10, 10, 10. What's left is this D expansion. There's the 129, the 138, the 219, etc. Factor out the 10. This is 129, 138, 219, 237, 318, 327. So I factored the 10 out of that bottom one. We already recognized this. We recognize this as the left-hand one here. So I intend to show this as 0. Why is it there? Factor out 10, and you look at 129, 138, 219, 237. Okay, so I factored out 10. I'm ignoring that 10 for the moment. I'm looking at what's left. Okay, so that is the D expansion of this. For example, 129. So when you factor out 10 from 20, you get the 129. There it is, 129. When you factor out 10 from 30, you get 138, etc. You recognize this as the D expansion of something. It's the D expansion of what? It's the D expansion of this. And that involves a repeated row. Where'd that extra row? Well, we did 10 times row, right? We did 10 times row 1 plus row 2. So when we get down to the 10 part, row 1 is repeated. There it is. It's repeated. Well, this has got a repeated row. So its D expansion gives 0. For example, swapping the first 2 rows doesn't change the matrix, but would change its sign. So the same argument that we gave a couple of videos ago shows that the D of this is 0. So the D of this is 0. So this here gives 0 because it's 10 times 0. And so what we have here is the sum of 2 things, one of which is 0. So we're back to the original. All right. So very involved, very involved. At least a lot of real estate takes a lot of space. Okay, and then the last thing I want to do here in this optional section. The determinant of a matrix equals the determinant of transpose, and as happens so often, I'm simply going to do this with an example. So the proof is best done by doing the 3x3 case, and then the n by n case is much the same. So here's the 3x3 case that we've been working with this whole video. There's the permutation expansion for the 3x3 case. Here's the permutation expansion of the transpose. Can you see that says 2, 1 right there, second row, first entry, and in the transpose it says 1, 2. That's not a mistake. This is the transpose of the matrix I was looking at. Okay, and of course I'm going to compare the products. All right. So let's see. So the ones in the expansion of T are the same as the ones in the expansion of the transpose. So let's pick one at random. How about if I pick this one down here? 2, 1, 3, 2, 1, 3. 2, 1, 3, 2, 1, 3. Let's find it. 2, 1, 3, 3. What was it again here? It was 2, 1, 3, 2, 1, 3. 2, 1, 3, 2, 1, 3. Ah, found it. There it is. Took me a minute. Let's try another one if you're dubious because I bumbled the last one. How about 1, 1, 3, 2, 2, 3. 1, 1, 3, 2, 2, 3. There it is. 1, 1, 3, 2, 2, 3. Okay, so term by term, ignoring the permutation matrices for just 1 second, term by term, I get the same things. Now, that's perfectly sensible because the 6 things up here arise from how do you pick one entry from each row and column, and of course you can pick one entry from each row and column by also picking one entry from each column and row. Okay, so that's perfectly sensible. All right. Now, what about the associated permutation matrices? So each of the permutation matrices is associated in the following way. If, for example, you take the one that has a 1, 2, 2, 3, 3, 1, then that's, of course, associated with the permutation. 1 goes to 2, 2 goes to 3, 3 goes to 1. When you transpose, you get 3, 1, 1, 2, 2, 3, and that's associated with the matrix that takes 1 to 3, 2 to 1, 3 to 2. That is to say, here 1 goes to 2, 2 goes to 1. 2 goes to 3, 3 goes to 2. 3 goes to 1, 1 goes to 3. So these two are inverses of each other. And again, that's perfectly sensible because when you take the matrix transpose, you sort of flip from ij to ji. Okay, but obviously the determinant of P sub phi is got to be the determinant of P sub phi inverse because they're plus and minus 1, and so exercise 16 shows it's easy to see that that the determinant of those two has to be the same. Okay, so these are entry by entry the same. Okay, and here's just a simple example for 2x2 matrices that AD minus BC, and when you take the transpose, you get this, and it's still AD minus CB, even though that doesn't make any difference. Okay, all right, very good. So let's see. Next time we're going to be changing on to the next section, and the next section has the advantage. We'll be back to the check-ins. The next section has the advantage of doing geometry. Geometry is always nice. I like the algebra, but the geometry is always has a sort of a delightful feel. So that'll be fun. Okay, see you then.
Hi, hi. All right, so last time we finished the sort of algebraic development of the determinant. We gave a definition for a function that deserves the name determinant, and we showed that there is a one, that it's unique. That was actually not all that hard. But then, excuse me, that it's unique, that there's only one such function, and then the hard part was showing that there is one, that there exists such a function. So we did that, and we gave a formula for the determinant, the permutation expansion formula. But the point we're making with the check-in here is that to actually calculate determinants, you typically don't want to use the permutation expansion formula, is that if somebody just throws a determinant at you, this one is 4 by 4, so it's big enough to be sort of annoying to do by hand. If someone throws a determinant at you, you're going to do Gauss's method. So of course I'm going to do that. Here we go. All right, so let's see. The determinant that I wrote down is 2103, 2103, 42 minus 10, 0, 1, 1, 1, and 0, 2, 1, 0. All right, so I got to find whether or not this matrix is non-singular, and I'm going to calculate the determinant, what the determinant function returns on this matrix. And I don't think I've ever done this before, but it's obvious what I'm doing here. I'm going to write equals, and then I'm going to do the Gauss's method step here. So minus 2 rho 1 plus rho 2, just so that a person can go back and check and see what I did. So this gives me 2103, 0, 0, minus 1, minus 6. And then just copy in 0, 1, 1, 1, and 0, 2, 1, 0. All right, and then the next step is the one that's of any interest at all. I would go to use that to eliminate below, but it's a 0, so of course I have to do a row swap. So swap row 1 and row 2. 2103, 0, 1, 1, 1, 0, 0, minus 1, minus 6, 0, 2, 1, 0. And I didn't forget, when you do a row swap, you have to change the sign, so there needs to be a minus sign there. Okay? When you do a row swap, you have to change the sign of the determinant. If I had factored out a 2, then I would have multiplied 2 times the whole determinant. I didn't do that. But when you do a row swap, you have to change the sign of the determinant as a whole. Okay, so off I go now, doing stuff that is not anything new to us. So I've got to use the 1 to get rid of the 2. So minus 2, row 2, add to row 4. 2103, 0, 1, 1, 1, 0, 0, minus 1, minus 6, and 0, 0, minus 1, minus 2. Don't forget to carry the minus sign on to the next line. And then finally, I got to use the minus 1 to get rid of the minus 1. So it's minus row 3, add to row 4. And I've got here 2103, 0, 1, 1, 1, 0, 0, minus 1, minus 6, and 0, 0, 0, 4. And don't forget the minus sign. Okay, so now I have an echelon form matrix. I'll just multiply down the diagonal. Don't forget the minus sign, and I'll get the answer. So equals minus 2 times, 1 times, minus 1 times, 4 times. And when you do it all, you get 8. Okay, so the lesson is you don't use the permutation expansion. We use it for the theory, but in practice, if somebody throws kind of an arbitrary matrix at you and asks you to find the determinant, why you want to use Gauss's method. Okay, great. Now, the first section involves kind of the algebra of determinants, but one of the nice things about the subject of linear algebra is that there's this trade-off, there's this play-off between algebra and geometry, and so in this section we're turning to the geometry of determinants, and the geometry of determinants is actually kind of a lot of fun here, and it gives us a new insight into how determinant functions work. So let's start in on that. So I'm going to find the determinant as a size function. In the past, when I calculated things like I did on the check-in and I got the determinant was 8, I only paid attention to whether it was 0 or not. In this section, we're going to come to understand what 8 means as opposed to 1 or 4 or 6. All right, so we're starting with some geometry. So I'm looking at two matrices in R2, and I've drawn them, and I've also drawn the kind of parallelogram diagram that a person draws when they want to add up the two vectors. In this space in the parallelogram, this is a collection of points, but it's part of the span of x1, y1, and x2, y2. But it's a special part of the span of x1, y2, x1, y1, and x2, y2. Suppose I, for example, put my mouse right here. It looks to me that I'm about 80% of the way up the x1, y1 vector, and about, I don't know, 20% of the way up the x2, y2 vector. That is to say, if I'm looking at this as a combination, t1 times x1, y1 plus t2 times x2, y2, I think t1 is about 0.8, where I've put my mouse, and t2 is about 0.2. Similarly, if I put my mouse over here, I think there t2 is about 0.9. I'm about 0.9 of the way up in the direction of the x2, y2 vector, but x1, y1 not so much, maybe 0.1. That is to say that this parallelogram is filled with points where if you take t1 times the first vector plus t2 times the second vector, t1 and t2 are numbers between 0 and 1. So that gives me the definition. The box, or if you're in larger dimensions, you probably call it a parallelepiped, but I have trouble spelling parallelepiped, so I go with box. The box formed by this sequence of vectors is just the collection of linear combinations of the vectors where the coefficients are between 0 and 1. That's just simply motivated by the picture, that's all. We're thinking about geometry, so I'm interested in the area of that box. So I calculated the area of that box. If I gave you, as a homework problem, find the area of that box, I'm sure what you would do is you'd take out a piece of paper and you'd say to yourself, well, I have this big rectangle, and I'm going to subtract away this triangle, subtract away that triangle, that triangle, that triangle, that rectangle, and when you subtract away all that stuff, what will be left is the area inside. So there we go. That's exactly what I did. And what I was left with was x1 times y2 minus x2 times y1. And then the chapter on determinants, so a person right away says, well, that's the determinant of the matrix formed by the x1, y1, and x2, y2 as column vectors. That's the determinant. Well, it can't be a coincidence. It'd be pretty silly to be covering it in slides if it was a coincidence, and anyway, it isn't a coincidence. So we're going to, in this section, I'm going to think about instead of considering the determinant as a function of the rows, we're going to consider it as a function of the columns. And so we're going to state things about the determinant in terms of columns because that fits with the geometry we want to do. You saw on the previous slide that I wanted to look at those vectors as columns inside the array. So restating, we know the determinant of transpose equals the determinant of the matrix. So restating the conditions in the definition of determinant in terms of transpose and at the same time reminding ourselves what are the conditions gives me this. If you do column operations, then the determinant of the matrix is unchanged. So if you take a matrix, perform k times column I plus column j, where I is unequal j, and get a new matrix A hat, then the determinant of A and the determinant of A hat are the same. Condition 2, swapping two columns changes the determinant sign, the SIGN. We saw that on the check-in where we had to carry the minus sign around. Condition 3, multiplying a column by a scalar multiplies the entire determinant by that scalar. So we're reminding ourselves of the conditions, particularly in the context where we've changed them to be stated in terms of columns instead of rows. And then finally, condition 4 is that the determinant of identity matrix is 1. Doesn't speak directly to columns or rows, but anyway, that's condition 4. Okay, so here's the central slide here. We're going to argue that the conditions on the determinant function, the ones that we just reminded ourselves on the previous slide, make good axioms for a function giving the size of the box. I calculated the size of the two-dimensional box there a couple of slides ago. We want to argue that the conditions, the 4 conditions that we just went over, give good postulates, give good axioms, good conditions for the function giving the size of a box. in Rn. So just as a for example, take the third condition. Rescaling a column rescales the entire determinant. If you take a determinant and multiply one of the columns by k, say by 1.4, then the entire determinant should multiply by 1.4. And look here at the picture. I drew it in 2 dimensions just because that's easy to draw, but I took the v vector and I rescaled it by multiplying it by 1.4. I think that the area of the enclosed region multiplies by 1.4. I think this box is 1.4 times as big as this box. So if you replace the word DET with SIZE, then I think that a person has some sense that that fits. The first condition. First condition says that if you do some column operation, because we're working with column vectors, first condition says that if you do some column operation, k times v plus w, then you don't change the size of the box. So I drew a box, the same box, drew a box, and then I did a column operation on, I did k times v plus w, and I compared the new box to the old box. And what you see is that, of course, the two boxes are different, but they have the same base and the same height, and so they have same area, same size. So condition 1 also seems to fit our intuition of what sizes of boxes should do. After the definition of determinant, we noted that the second condition is redundant. It's a consequence of the other 3 conditions, so I'm going to leave it aside for the minute and talk about it more in just a second. The final condition in the definite determinant, of course, is that the identity matrix has determinant 1, and we're going to think of it as having size 1, having measure 1, having sort of a component of total of 1. Okay, well, I mean, there we go. I just made a box out of the two standard basis vectors, and we expect that to have size 1. I want to make a remark about the second condition because it says something that a person may find surprising. So the second condition in the definition determinant says that swapping columns, I'm stating in terms of column, changes the size of the determinant. Changes the sign of the determinant. I misspoke. So wait, size of boxes has a sign, has an SIGN? What? Okay, so let's look at these two. 4,2 and 1,3. So here's 4,2, see it there? Here's 1,3, see it there? I drew a little arrow that arcs over from 4,2 to 1,3. That's a counterclockwise arrow. And when you calculate the determinant using the usual 2 by 2 determinant formula, you get 10. If you swap those two, so that you take the 1,3 first and the 4,2 second, now to get from first vector to second vector, the arrow arcs clockwise. Here, to get from first vector to second vector, the arrow arced counterclockwise. Here, to get from first vector, the 1,3, to second vector, the arrow arced counterclockwise, and I get a minus 10 for the sort of content of that box. So what we're seeing then is that when we take determinant to tell us something about the size of a box, it includes information about kind of how much paint it would take to paint it, 10 square inches. But it also includes information about the orientation or the sense of the box. The first one here is oriented. The columns are stated in such a way that to go from U to V, you arc counterclockwise. Here, the columns are stated in such a way that to go from 1,3 to 4,2, you arc clockwise. And we're going to just consider clockwise to be a negative orientation. I mean, we've got to pick one of them to be negative. We're going to pick the orientation that's written there to give us a negative sense for the box. This orientation thing can sometimes seem a little weird to a person, so I want to do a three-dimensional picture, and you can see that I got the computer to draw it for me because I'm totally hopeless when it comes to drawing these things. Okay. So if I take two vectors, 1, 4, 1 and minus 2, 3, 1, and I drew them there, then they span a plane. That's this yellowish plane. Of course, plane divides 3-space into two parts, the parts up and the part down. And you can see that I drew a V3 up. It's embarrassing, but I drew a little guy there, a little person on the V3. If you take V3 above the plane, that is, if you take V3 so that V3 is on the side of the plane with the following property. A person standing on V3, looking at the arc from V1 to V2, sees that arc as counterclockwise. Looking at the arc from V1 to V2, sees that arc as counterclockwise, then we'll take that to be a positively oriented box. So the box formed by V1, V2, and V3 will be positively oriented. The idea here is that you put your right hand down on the plane, you put your hand on V1 and you curl your pinky finger over to V2. Your thumb points in the direction of V3. If so, then the box, the parallelepiped, formed by these three vectors will have a positive sign. What's the opposite of that? Whoops, there we go. There's the, can you see that the guy is below the plane and looking up? Below the plane and looking up. If you want to put your hand so that your hand rests on V1, your hand that rests on V1 and you curl your pinky fingers toward V2, and now you try to do it with your right hand, it won't work. You got to do it with your left hand instead. Now your left hand points in the direction, so those will be the negatively oriented boxes. So it has to do with right hand and left hand. I have a sequence of, to try to help a person picture, maybe a little goofy sequence, to try to help a person picture what's happening. Now I'm kind of on the underside and looking up. Here I'm on the overside and looking down. Okay? Okay. So what's happening here is that if you curl your hand from V1 to V2, then the thumb that points in the direction of V3 is your left hand. So the left hand boxes will have a minus sign, the right hand boxes will have a plus sign. Okay, so I'm using the word size here, not the word volume, because we have a sense to the box, an orientation to the box. The box are directed in some way. All right, so a couple of consequences of what's happening here is that, the first one is that determinants are multiplicative. If you take a transformation from Rn to Rn, it will change the size of all boxes by the same factor. So for example, if you have a transformation from Rn to Rn that takes the unit box, the box formed from the unit, from the standard basis, and it transforms it to a new box that is twice as big, then it transforms every box, no matter what kind of crazy big, small, it transforms every box to one that's twice as big. So the size of the image box is determinant of t times the size of the box S. So T of S, that's a box. T of S, determinant, is determinant of T times the size of the box S, where capital T represents little t with respect to the standard basis. In short, the determinant of capital T times capital S is equal to the determinant of capital T times the determinant of capital S. And the proof here is got two cases. So if t is singular and if t is non-singular. Neither one is especially complicated, but two cases. If t is singular, then it doesn't have an inverse. So I'm going to note that if Ts were invertible, then there'd be an m, so that Tsm equals I. Just move the parentheses to make it t by Sm equals I, and so t would be invertible. The contrapositive of that observation is that if t is not invertible, then neither is Ts. That is to say, if the determinant of t is 0, t is singular, If the determinant of t is 0, then the determinant of ts must be 0 also. Okay, so a little bit on the tricky side maybe, but it's right. If t is singular, then the determinant of then it's the case that if the determinant of t equals 0, then the determinant of ts equals 0 also, until we have equality. Next case is that t is non-singular. Any non-singular matrix factors into a product of elementary Gauss's method matrices. To finish the argument, what I'm just going to do is verify that the statement works for each elementary matrix, and the result will follow just from the multiplicativeness. Is that a word? Okay. So there's three types of elementary matrices. There's the multiply a row by k, there's the permute two rows, interchange two rows, and there's the k times row I plus row j. I'm going to do the first just because the other two go much the same way, and so often in the slides we try to give a feel for what's going to happen rather than cover all the details. Okay, so the matrix MIK then multiplied by S is the same as S, except that row I is multiplied by K. So this is the product of two matrices, and it's the two matrices are the same, except that row I got multiplied by a factor of K. And the third condition of the determinant function then gives that the determinant of that matrix must be K times the determinant of S. But MIK, that matrix, must have a determinant of K, again by the third condition, because MIK is derived from the identity. The definition of MIK is that it's derived from the identity matrix by multiplying row I times a factor K. And so we have the multiplicative property in the case of MIK, and a similar argument gives the multiplicative property in the case of permutation matrices and in the case of row combination matrices. And every non-singular matrix is a combination of those three, factors into a product of those three, and so we get the result. Okay, so some examples. The transformation that takes R2 to R2 and rotates all vectors through a counterclockwise angle of theta, especially important 2 by 2 matrix, is represented by this. And just geometrically, if you think in your head what it does this to everybody. So it doesn't change the size of any boxes, just rotates them. And you'll note that the determinant of t theta is 1, because cosine squared minus a minus sine squared makes cosine squared plus sine squared, which is 1. Isn't that nice? The linear transformation that's represented with respect to standard basis by this kind of arbitrary matrix, 1, 2, 3, 4, will change the box size of any box that you give it by a factor of minus 2. So 1 times 4 minus 3 times 2 gives 4 minus 6 gives minus 2. So, whoops, I spelled is wrong. Oh no, is S acting on typical box. No, I didn't. I spelled it right. So I did. It's on the next slide. I didn't fit it on this slide. So here's a box in the plane, and it's got a V1 and a V2. It happens to be the box where V1 is 1, 0 and V2 is 1, 1. And I applied S to it, 1, 2, 3, 4. I applied that to the box, and I got a new box. It's tall and skinny. Can you see it there? Tall and skinny. There's S of V1 and S of V2. And remember that the determinant is negative. Do you notice that to go from V1 to V2, you go counterclockwise? But to go from S of V1 to S of V2, you go clockwise? So we changed not only the size of the box, but we also changed the orientation. It went from a counterclockwise orientation to a clockwise orientation. That's why the determinant has a negative sign. So this box over here has the right size. The original box had a size of 1. This box here has a size of minus 2 because that was the determinant of the matrix. The determinant of the inverse. If you tell me the determinant of a matrix, I can calculate the determinant of the inverse because it's simply 1 over. and that follows directly from the previous result, is that obviously the identity matrix has a determinant of 1, and obviously the identity matrix is T times T inverse, so you split along the minus sign because the previous result says you can split along a minus sign, and you get then that the determinant of T inverse is 1 over the determinant of T, and here's a 2 by 2 example. Again, notice the sign, the SIGN, they both flip the orientation. Volume. So we focused on we're focused on size because I wanted to talk about orientation, but a lot of times in applications you don't care about the orientation, you only care about the size. So what's the story with the volume? And the answer is just take the absolute value. That's all. It's very, very straightforward. Just take the absolute value. So so this particular box, for example, to get from V1 to V2, you would go clockwise. If I asked you what is the size of this box, you'd say -2. But if I asked you what's the volume of the box, area for 2 dimensions, what's the volume of this box, you'd say +2. You just simply take the absolute value, no more complicated than that. Okay. Okay, so I want to close today by talking about something that is kind of a fun application of these area facts, and often used by people. Often people have memorized this particular application. Often used by people to sort of do things in their head. All right, so I want to give a geometric interpretation of linear systems. So here we go. I wrote down a not very complicated linear system. 1, 2, 3, 1 is the matrix of coefficients, and 6, 8 is the constants. And I drew a picture here. Here's 2, 1. There we go, 2, 1. Here's 1, 3. There we go, 1, 3. Here's 6, 8 up here, 6, 8. And so in asking what is x1 and x2, I am asking, how much do I multiply 2, 1 by, that is x2, how much do I multiply 2, 1 by, and how much do I multiply 1, 3 by, so that when I add the two, the parallelogram diagram will give me 6, 8. Okay, that's the geometry. What's happening here? I'm asking what's the x2, what's the x1, so that the parallelogram diagram gives me 6, 8. Okay. All right, so I drew the same, of course. I first drew the parallelogram for 1, 3, and 2, 1. Now, I'm going to focus on x1. x2 works the same way. Multiply 1, 3 by x1, and of course what you get is you get a parallelogram that is x1 times as big, and that fills in this portion of the parallelogram from the previous slide. So there we go. If I ask what's the area of the shaded region, it's the area of this. What's the size of the shaded region? It's this. When I multiply it by x1, the size of the shaded region is this. It's got one side x1 times 1, 3. The other side is 2, 1. And now one of the other conditions in the definition of determinant is that if you do a column operation, you don't affect the size of the parallelogram. Okay, so I'm going to do the column operation that takes x2 times the second column and adds it to the first column. x2 times the second column and adds it to the first column. Okay, so there I go. x2 times the second column added to the first column. Well, we know what x1 times 1, x2 times 2, and x1 times 3, x2 times 1 is. It's 6, 8. So I get this for a parallelogram. The vector on this side is 6, 8. The vector on this side is 2, 1. So I wrote it in, 6, 8, 2, 1. Now compare the beginning of the equation to the end of the equation. In short, I can calculate x1 by taking this over this. It didn't fit on this slide, so here it is on the next slide. Calculate x1 by taking the determinant 6, 8, 2, 1 over the determinant 1, 3, 2, 1. That is to say, to calculate x1, you write down the matrix of coefficients and you replace the two coefficients here that are x1's coefficients. You replace them with the constants, the 6, 8. That goes on the top. This is easy to calculate. This is easy to calculate. I get an answer of 2. Obviously, the same works for x2. I looked at the matrix coefficients, 1, 3, and 2, 1. To get x2's answer, I replace the 2, 1 with 6, 8. Do the calculation, you get a 2. So Cramer's rule is, I'll state it. Let A be an n by n matrix with a non-zero determinant, because you don't want to be dividing by 0. Let A be an n by n matrix with a non-zero determinant, and let B be the n tall column vector that forms the constants in this linear system. Then for any I, you can figure out xi by writing determinant of bi divided by determinant of A, where bi is the matrix you get by substituting the vector b for column I of A. In other words, if you want to calculate x1, you substitute for column 1 the column of constants. If you want to calculate x2, you substitute for column 2 the column of constants. Okay. Here's a simple example, 3 by 3. I have here a linear system, looks like first day of class. So 2, 1, minus 1, etc. 4, 2, 0 are the constants. So if I want to worry about here x2, just as an example, I'm going to replace the 1, 3, 1 with the 4, 2, 0. There it is. I replace the 1, 3, 1 with the 4, 2, 0. Find the determinant of the matrix without the replacement and the determinant of the matrix with the replacement, and that gives you an answer. 1 divided by the other gives you the answer. So you can rapidly get x2 if you can calculate these determinants. You can rapidly get x2 or x1 or whatever you want to get. So it's called Cramer's rule, and it's a kind of a nice little gadget. But I'll give you a caution. Cramer's rule is interesting, and it's a nice application of the geometry. A lot of people have memorized Cramer's rule because it allows you to solve small systems, for example, two equations, 2 unknowns, in your head, if the numbers are small and malleable. But please don't use Cramer's rule for system having 50 variables. If you're looking at a 50 equation, 50 variable system, don't do Cramer's rule because calculating the determinant is going to be very slow. Instead, just do Gauss's method like on the first day of class. So Cramer's rule is kind of fun, and it illustrates the geometry of what we're doing, but it isn't really the answer that a person should be thinking about. Okay, very good. Kind of a long day today. So next time we're going to come back, and we're actually in a third section here, so we're making rapid progress. Okay, bye-bye. Hi. Okay, so last time we talked about the geometry of determinants, so the check-in naturally asks a couple questions about the geometry. So let's have a whack. Let's see, so I'm given 2 different sequences of vectors. The first is, 1, 2, and 3, 1. And the second is 2, 4, and then again 3, 1. So all I did was make the second case have a vector that's twice as big. The question says draw them. So here comes the weak spot. So let's see. I'm going to need something that is 4, 3. So I'd better make 4 ticks. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2 looks like so. And 3, 1 looks like so. And then 4, 3 would be about there. And so the full parallelogram diagram is something like so. Okay, so that's the box enclosed by those 2. The other one, let's see, that's 5, 4. So I'm going to need 5 ticks. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so 2, 4, 2, 4. 3, 1, again, 3, 1. And 5, 5. 5, 5, about so. Okay, so we get the box. Okay, and when you see here 1, 2, 1, 2 is about there. So it does seem to me that you're looking at the box over here is twice the box over here. That's all. I mean, you know, given the limits of my drawing, the box over here is twice the box over here. All right, so let's do the calculation of the determinants. Let's see, so the determinant of A here, turning A into the obvious matrix, is, I'm just going to do the formula for 2 by 2 determinants, that's all. So 1 times 1 minus 3 times 2, so that's 1 minus 6, so negative 5. And then over here, I've got the determinant of A hat, so I've got what, 2 times 1 minus 3 times 4, so that's 2 minus 12, so negative 10. And a person notices that the size is twice. A person also notices the minus sign. What's the deal with the minus sign? And so to go from 1, 2 over to 3, 1 is a clockwise arrow. Come on, look like an arrow. There we go. It's a clockwise arrow. And likewise, to go from 2, 4 over to 3, 1 is a clockwise arrow. So that explains the negative sign, is that these boxes are oriented the opposite of counterclockwise. Okay, very good. All right, so the material that we're doing today is optional material. It's about a way to calculate the determinant that's different than the ways that we've seen. We'll only use it once later on in the book, but if you often see it in practice, and so I'm mentioning it. So it's Laplace's formula for the determinant. The determinant is just a kind of just a factory for producing interesting and amusing formulas, and this is an example of such a thing. But you know, we don't want to get bogged down in hundreds of different formulas. So I'm only covering this because there's a section later on in the book where a person might need it. Okay, so I'm reminding you here of the permutation expansion of the determinant of t. Every term has one and only one entry from each row and column. So it says t sub 1 comma phi of 1, t sub 2 comma phi of 2, all the way out to t sub n comma phi of n, where phi is a permutation. So phi of 1, phi of 2, etc., phi of n consists of the numbers 1 through n rearranged, maybe trivially rearranged, but anyway rearranged. And so what we get is one entry from each row. Obviously there's one entry from row 1, there's one entry from row 2 out to one entry from row n. And then when you think of the phis as being the numbers 1 through n rearranged, then there'll be one entry from row phi of 1, one entry from row phi of 2, etc. Okay, and here's the determinant of the permutation matrix. So I always find it easier to do this with concrete examples rather than the abstract formula. I go from concrete to abstract. That's just the way I work. So here's the 3 by 3 case. I did it with the subscripts rather than ABC because I think the subscripts help a person remember that this is row 1, that's row 2 kind of stuff. So here we go. There happen to be 6 permutations of the 3 numbers. And so there they are, 1, 2, 3, 4, 5, 6 terms. And just to pick on one in particular, I'll pick on the one here that leads the second row. And you see that it has one lowercase t from row 1, one lowercase t from row 2, one lowercase t from row 3. There is one lowercase t from column 2, there is one lowercase t from column 3, and there's one lowercase t from column 1. So just what it says, one and only one entry from each row and column, and it has to do with the permutations. All right, and there I added the signs. So p sub phi 2 is a negative 1, and p sub phi 3 is a negative 1, and like that. Okay? I want to focus on, pick out a row or a column, and I'm going to pick out the first row, just to pick out some row. So I picked out the first row, and I'm going to focus on that row. So I went through and picked out the T11 terms. There they are, these two, and I wrote that on the first line. Then I picked out the T12 terms. There they are, and I wrote that on the second line, and the T13 terms, and wrote that on the third line. Okay, so a kind of a natural way that a person would fool around with this formula. And you look what's in square brackets there on the first line. It's got 2 things minus 2 things, and it looks an awful lot like a determinant. In fact, it's the determinant of this matrix. 2, 2, 2, 2, 3, 3 minus 2, 3, 3, 2. Flipping back, 2, 2, 3, 3 minus 2, 3, 3, 2. So that's a determinant. And a person, I wonder if you can get 3 by 3s by somehow combining 2 by 2s. And so you start looking at the other two inside of square brackets and you recognize them as also determinants of some kind of matrix. Oh, okay, so what's the explanation? Where do those smaller matrices come from? And the explanation is pretty straightforward when you think about the permutation. When I focus, for example, on the terms that have a T11 in them, I've fixed that the term from the first row is T11, the term from the first column is T11. I've crossed off, in some sense, the first row and first column. I can't use those for the other lowercase t's. So what's left is picking one of each of second row, third row, second column, third column. That's this determinant. That's exactly what this does. You look in there, the permutation expansion of this determinant is you pick one entry from each row and column. There are two determinants of this matrix, and so we get what we got. Likewise, if you cross off, if you use T1 comma 2, then you've used row 1 and column 2. So what remains are row 2, row 3, column 1, column 3. And similarly here. So the matrices down here illustrate. When I looked at the terms that involve T11, I basically, in terms of what else do I have there, crossed off row 1 and column 1 from further, you can't use them anymore, they're taken. So what's left is this, and of course a person spots it right there. When I looked at the terms that involve T sub 1 comma 2, well, I've used row 1, I've used column 2, so cross those off, you can no longer use them, and you spot there, that's that. And obviously, when I looked at the terms that involved T row 1, column 3, then in terms of the permutation, I crossed off row 1, you can't use that anymore. Permutation only uses each row once. I crossed off column 3, you can't use those anymore. The permutation expansion only uses column 3 once in each term. So what's left is this, and there we go. Okay, so those smaller determinants, those appear simply because that's the way permutations work. So that accounts for the appearance of the determinants of smaller size matrices. What you might not have noticed, I kind of went by it without mentioning it, but here, if I look at this equation, those three things in square brackets are all determinants of a kind, and there's a minus sign there, and a person might scratch their head about what's with the negative sign there, what's happening there, so I got to explain that. Okay, so here's a restatement of that equation, where I wrote down the permutation matrix, instead of just writing down pluses and minuses, I wrote down the actual permutation matrix. So I took sort of a step back. Up here, when you look at this the first line of this equation, you can see here that this is all set up to consider this the determinant. Why? Well, because this first row is just like in the identity matrix. And what's happening down here? Well, this looks like the permutation that takes the first thing to the first thing and the second thing to the second thing. That's what this looks like, the matrix that you get associated with that permutation. And this looks like the matrix that you get associated with the permutation that takes the first thing to the second thing and the second thing to the first thing. So these two are set up in such a way, just works out that way. I mean, I chose to expand along the first row because it works out that way. But in any event, it works out so that these two matrices are set up here to look like what I'm thinking about. What happens on this line? Remember, there's a minus sign appears on this line. What's the story with the minus sign? Well, if you want to make this and this guy be set up to look like those folks, what do you have to do here? Well, you have to do a swap to get the first and second rows to look like this. Swap changes the sign. What about here? Well, you got to do a swap of the first and third rows to get the matrix to look like this, and that swap changes the sign. These on this line, we have two different sign changes. I brought it out in front and put it as a minus here. So it's all starting to make some kind of sense. What about down here? Why is this a plus sign? I mean, it clearly needs to be swapped around. Let's see. So you swap the first and second rows, but then you're not done. It doesn't look like this. It looks like this. But anyway, it doesn't look like this. So if you swap the first and second rows, it doesn't look like this. You got to do another swap. If you swap the first and second rows and then you swap the second and third rows, it will now look like this. Two swaps, positive sign. So same thing here. Two swaps to make it look like this. Positive sign explains the positive sign. Okay. Okay, very good. So I'm not going to go through the proofs here as we often do. We'll skip that and just focus really on the formulas. So I need some terminology here. Up when I drew these three pictures, I crossed off a row and column. So I need a word for that. If you look at an n by n matrix T, then the n minus 1 by n minus 1 matrix formed by deleting row I and column J is called the Ij minor of T. And then what's the story with the signs, with the Sig and S? The Ij cofactor, T sub Ij of T, is minus 1 to the I plus J times the determinant of the Ij minor. So the determinants are in there, the signs are in there, and the crossing out a row and column is in there. So for example, here's a matrix just filled with some kind of numbers. Nothing special about this matrix. The 2, 3 minor is cross off the second row and third column, and what's left is a 3, a 1, a 7, and a 0. There they are. The associated cofactor is, you got to take the determinant of 3, 0, 7, 1. Of course, the 2 by 2 matrix formula gives you a minus 7. And then you have to multiply that by minus 1 raised to the 2 plus 3 power. 2 plus 3 because here 2 and 3. So minus 1 to the 5th, when all the calculating is done, everything falls down and you get a positive 7 for an answer. Okay, so that's the cofactor, is positive 7. So cofactor is a number, minor is a matrix. And then Laplace's formula is that what we saw earlier is exactly right. Is that what we saw earlier here, T11 times the appropriate determinant here, the appropriate cofactor, T12 times the appropriate cofactor, T13 times the appropriate cofactor is exactly right. So, whoops, I'm sorry, one more. So if you pick a row or a column and you expand in that way along the row or column, entry times the associated cofactor, entry times the associated cofactor, all the way out to entry times the associated cofactor. Now this one is a row. This is the ith row. This is the ith column. Entry times the associated cofactor, entry times the associated cofactor, all the way down to entry times the associated cofactor. Then you get the determinant of T. So that's the observation that we got by fooling around with those numbers, with the 3 by 3 case. And the proof is an exercise. We're not interested in the proof here. We're interested in doing some examples. So this is an example of the determinant of the matrix, the cockamamie matrix that we looked at earlier. So I was expanding along the second row. I found that the 2, 3 cofactor was 7. Do you remember that from prior slide, a couple slides ago? So the 2, 3 cofactor is 7, and here I found the other cofactors on the second row. The 2, 1 cofactor is 3. The 2, 2 cofactor is minus 23. So associated with the 5 is a 3, associated with the 4 is a minus 23, and associated with the minus 1 is a 7. So here we go. 5 times the associated cofactor, 4 times the associated cofactor, minus 1 times the associated cofactor, and my calculator says that that's minus 84. Okay. So, really bundled in with all those same ideas associated with that idea, the matrix adjoint to the square matrix T is you write down here the cofactor, T sub 1, 1, T sub 2, 1, T sub 3, 1, etc., etc., etc. That's called the adjoint. And I got to warn you, it's so easy to get wrong that the entry in row I and column J is not T sub Ij. Instead, the entry in row I and column J is T sub Ji. Did you notice that this doesn't say T sub 2, 1? This says T sub 1, 2. So it's flipped from what you might think. Don't be fooled. What's the point of that? So first I'll give you an example here. So again, you see this is the same cockamamie matrix that I had earlier. So again, you see that this does not say S sub 1, 2. This says S sub 2, 1. And this says S sub 3, 1, not S sub 1, 3. So the subscripts are flipped from what a person might think. So it's one of these things when you adjoint, you say to yourself something like, okay, so one of the traps is to accidentally flip the, so be careful, don't flip the, okay, so there we go. And I calculated all this stuff. You might remember some of the earlier values. Okay. And the point here is that we have a formula for the inverse of a matrix where T is a square matrix. Then down here at the bottom you say it says T inverse is 1 over the determinant of T multiplied by the adjoint. Sort of equivalent is to say T multiplied by the adjoint, the same thing as adjoint multiplied by T, is the determinant of T times I. And this summarizes. If you take the regular starting matrix T and you matrix multiply it by the adjoint, what you get is a matrix that has all zeros except for determinant of T down the diagonal. And we're not really focused on the theory of it, but just it's such a cockamamie formula. I'll just mention in passing here what happens is that we already saw this. We already saw that you can expand along in a formula in this way, for example, expanding along row I to get first thing in row I times the associated adjoint, second thing in row I times the associated adjoint, all the way out to nth thing in row I times the associated adjoint gives you determinant of T. That's fine, that's fine. What about the zeros? Well, if you take a T sub I1 and T sub K1 there, what you're essentially doing is you're representing here the expansion along row K of a matrix where row I and row K are equal. Because this T sub K1, T sub K2, etc. doesn't know what the omitted row is. So you're sort of telling it, what does that mean? But anyway, you've got an expansion where it looks as though this is the expansion of the determinant formula that we just saw, where row I and row K are the same, and of course that's going to come out to be 0. Okay, so here, for example, the inverse of this matrix, just some crazy matrix with all sorts of numbers, is you take 1 over the determinant of S times the adjoint of S. So we calculated earlier the determinant of S. Here's the adjoint of S, and that's all it is. Well, just to close here. The formulas from this section are perfectly useful for theory, and we're going to use them for theory, but they're not the best choice for computation with arbitrary matrices. Maybe special case matrices, lots of zeros or something, but for arbitrary computations, you're always going to want to, for example, find the inverse in kind of a Gauss-Jordan way sort of stuff. Okay, so we will use these formulas for the theory, and they're perfectly interesting and perfectly correct. But if you have a homework problem, find the adjoint of this 3x3 matrix. That you're looking at trying to do that with the usual methods that we've seen before. Okay, very good. So that ends chapter 4. So very exciting, getting close to the end of the course. So chapter 5 starts by thinking about something new about vector spaces. What if the coefficients and the scalars are not real numbers, but are allowed to be, the expansion of real numbers are allowed to be complex numbers? Okay, very good. We'll see you then. Hi. Okay, so start of the 5th chapter. So very exciting, getting near completion of the semester. Now, the last section was optional, the section on the Laplace expansion. So I'm going to cheat and reuse the check-in from that. In fact, I'm going to cheat and reuse what I wrote on the piece of paper. So here was the question. It asked about geometry of determinants. So some people may not have seen the geometry of determinants question. So for each sequence, and we're given 2 sequences, and a person notices that the difference is that we doubled the first of the 2 vectors in each. So to get from here to here, we doubled to get 2, 4. That's all. It just says draw the boxes and find the volume. So here's what I did for the optional. The optional. There's the A and A hat, and I drew the two boxes, and I'm not a very good drawer. I don't know what to tell you, but it's not the worst thing in the world either. So in the first box, you can see that it has 1, 2, and 3, 1, and here in this box over here, you can see that it has 2, 4, and again with the 3, 1. I've noted here in the picture that in going from 1, 2 to 3, 1, you're going clockwise. Likewise here, in going from 2, 4 to 3, 1, you're going clockwise. Okay, and I put in the whole parallelogram and the whole parallelogram. The determinant here is if you make the sequence into a matrix and you take the determinant, I just use the formula for 2 by 2 matrices and got here -5. For A hat, same thing. I made it into a matrix and I used the formula for 2 by 2 matrices and I got here -10. So twice the size. And of course, looking up here, they have the same sign. We've already established that both of them are clockwise. Moving from the first vector to the second vector is clockwise, so the sense of both boxes is clockwise. And why twice the absolute value? Well, because here we're looking at a box that has sort of twice the content, twice the measure. So from here to here, we've kind of doubled the kind of inside of the box. Okay, so very straightforward. So what happens in the 5th chapter is that we are going to need to factor polynomials. So, so because we're going to factor polynomials, we need to, whoops, there we go. Because we're going to factor polynomials, we need to change here to away from using real numbers to using complex numbers. Real numbers are great for what we've needed to do so far, linear combinations kind of stuff. But for factoring polynomials, we really need to go to complex numbers. So I'm going to have a review here today, a brief review of factoring polynomials and complex numbers and how they connect. So we're going to use complex numbers for the scalars. So beyond real numbers, we're going to extend the real number case we've been working on so far to use complex numbers. And that'll include, for example, entries in the vectors and the matrices. That is, we're going to shift from studying vector spaces over the real numbers to studying vector spaces over the complex numbers. You can do vector spaces over other mathematical structures. You just kind of need to be able to add, subtract, multiply, and divide. But anyway, we're never going to do that in this course. We're simply going to, complex numbers is as far as we're going to go. Now, any real number is a complex number, of course. 5 is 5 plus 0i. And in this chapter, most of the examples that you'll see will be real numbers. But nonetheless, I can't state the critical theorems without having the complex numbers around. Okay, so I'm going to briefly review factoring polynomials and complex numbers. So, so the division theorem for polynomials, again, I expect that a person has seen it before, but I'm reminding you, might have saw it before and it's kind of worked its way out of your working memory, but nonetheless, I think you see it before. So I want to think about a polynomial with a leading coefficient 0, just so that the n is not foolish. And then they say that the degree of the polynomial is n. If n is 0, then you have a constant polynomial. Constant polynomials that are not the 0 polynomial, for example, the polynomial if I said p of x equals 7 or p of x equals -3 or p of x equals 1 plus I, that would be a constant polynomial that's not the 0 polynomial. Constant polynomials that are not the 0 polynomial are defined to have degree 0, and the 0 polynomial is defined to have degree -infinity. It's just convenient for some statement of some theorem. Now, the point about polynomials here and division is that you can divide. So if you give me two polynomials, here I have a cubic polynomial and a quadratic polynomial. I can divide the quadratic into the cubic. The idea goes something like this. You ask yourself, just focus on the leading terms. At this point, it's the x squared and the 3x cubed. And you ask yourself, how many times does x squared go into 3x cubed? What does it take to multiply x squared to end up with a 3x cubed? So of course it takes 3x. Now, just like long division in grade school, I'll multiply 3x times x squared plus x. I'll put it underneath and I'll subtract. So there's 3x times x squared plus x, and now I'm subtracting it away from the polynomial that's inside here. And of course, the 3x cubed minus the 3x cubed is 0, of course, which was the whole point. And now I'm looking at 2x squared minus 3x squared, and I end up with minus x squared. Just like in grade school long division, you bring down the minus x. In fact, grade school long division is basically polynomial division, only you're using tens instead of x's. Anyway, you bring down the minus x, and you now ask yourself, x squared goes into minus x squared. So just like a minute ago, I was asking myself, x squared goes into 3x cubed how many times? Now I'm asking, x squared goes into minus x squared how many times? And I'm going through the steps. So x squared goes into minus x squared minus 1 times. I'll multiply through here. So I multiplied x squared plus x times minus 1 and subtracted. So there's a minus thing happening there. Anyway, minus x squared, and that cancels, and I'm looking at minus x and a plus x, and it happens that I get a 0 there. You bring down the 4, and you got a 4. So, in short, how many times does x squared plus x go into 3x cubed plus 2x squared minus x plus 4? So the answer is x squared plus x goes this many times, 3x minus 1, into the 3x cubed plus 2x squared minus x plus 4. And what's the remainder? The remainder is 4. Writing it in the familiar n equals dq plus r form, there's the n, there's the d, there's the q, and there's the r. Okay, so where p is a polynomial, the statement of the theorem, that the example of which I just walked through, that where p is a polynomial, if d of x is a non-zero polynomial, the divisor of course, if d of x is a non-zero polynomial, then there are quotient and remainder polynomials that give you p equals dq plus r. And as always with division, the point of division is, sure, the dq plus r is there, it's necessary for the statement, but often overlooked is the fact that the remainder has to be small. I mean, you know, what kind of person would say that 4 goes into 5, 4 goes into 20, 4 times with, with remainder 4? Who would say that, you know? So you got to have that you got to have that the remainder is small. So here, the degree of r is strictly less than the degree of d. So you get dq plus r, all right, but the point is that the degree of r is strictly less than the degree of d. So if you look, the corollary here specializes as to the case where you have degree 1 polynomials when you divide p by x minus lambda, so d is the divisor here, is x minus lambda, then the answer's got to be the constant polynomial, so because that's the polynomial that has degree strictly less. Why does it have to be the constant polynomial r of x equals p of lambda? And the answer is just plug lambda in for everything, and that's what you get. Okay. If the divisor goes into the dividend evenly, meaning that r of x is the 0 polynomial, then we say that d is a factor of p of x, just like with regular integers. If 4 goes into 20 evenly, so we say that 4 is a factor of 20. Any root of the factor, any lambda, any real number lambda, so that d of lambda is 0, is a root of p of x, just from this equation here, because r is 0, so you're just simply looking at d of lambda times q of lambda. Okay. So if lambda is a root of the polynomial p of x, then x minus lambda divides p of x evenly. That is to say, if lambda is a root of the polynomial p of x, then x minus lambda is a factor of p of x. So we typically want to start with complicated polynomials. So let's say a 5th degree polynomial, a 12th degree polynomial, a 200th degree polynomial. That's crazy. Of course, we're not going to see that kind of thing in this chapter. And break it down into smaller parts. And the smallest part here, the smallest part that involves an x, is x minus lambda. So we hope to take an arbitrary polynomial and break it into as many x minus lambdas as possible. Okay. Now, so when we were in the previous chapter, chapters 1 through 4, we were working with real numbers, and the factoring situation with real numbers is just a little bit more awkward, although kind of a lot more awkward than with complex numbers, which is why we're going to switch. So I'm reminding you of the story with factoring with real numbers. If I give you a constant polynomial, you can't break it up into smaller things. Into polynomials of smaller degree, because that's as small as you get. A linear polynomial you can't break up into two smaller degree polynomials because linear is of degree 1. You can't make it any smaller. Quadratic polynomials. So a person in sort of junior high school, middle school, spends a certain amount of time factoring quadratic polynomials and finds that some of them factor and some of them don't. So a quadratic polynomial is irreducible, meaning cannot be factored, exactly when its discriminant is negative. Do you remember the discriminant b squared minus 4ac? So if b squared minus 4ac is negative, then the quadratic polynomial cannot be reduced. But if you have a cubic or a higher degree polynomial, then you can reduce it. If you have a cubic or higher degree polynomial, you can reduce it. You can imagine, for example, breaking a 4th degree polynomial into 2 quadratics. Now, do those quadratics break into smaller parts? Dunno. But the 4th degree polynomial will break into smaller parts. A cubic polynomial, for example, might break into a quadratic and a linear. A 5th degree polynomial might break into, a cubic and a quadratic. So you break these larger degree polynomials, at least in theory, you break these larger degree polynomials into smaller parts until you have a mix of linears and quadratics. The linears, you're done. The quadratics may or may not break depending on whether the discriminant is negative. So when you're factoring over the reals, you're always left with this situation where you get it down close to completely factored. Bunch of linears, bunch of quadratics. Some of the quadratics will factor, but some of them won't. So you get it down close to completely factored, but not quite. So the reals have the disadvantage that you can't completely break. If you give me a polynomial, I cannot guarantee, well, I didn't say that right. I cannot guarantee that a given polynomial will factor completely into linears on the reals. So a polynomial with real coefficients factors into a product of linears and irreducible quadratics with real coefficients. And the factorization is unique. We haven't talked about that too much, but the two factorizations have the same factors raised to the same powers. But with complex numbers, the situation is perfect. With complex numbers, if you have a polynomial like x squared plus 1, if you have a polynomial, you can break it completely into a product of linears. X squared plus 1 has no real roots, and so it doesn't factor over the real numbers. If you imagine a root, if you add the possibility of the number I, so that I squared plus 1 equals 0, then x squared plus 1 factors into a product of two linears, x minus 1, I and x plus I. So what we do is we add this number I, sometimes engineers call it j, we add this number I to the reals, and then you close up the new system with respect to addition. That is, you allow yourselves to say things like I plus I, or 3 plus I, or minus 2 plus 5I kind of stuff. And what you get is called the complex numbers. Written that way with called the blackboard boldface. Capital C, because you can, with chalk on a blackboard, you could make that symbol. Usually, when a person sees complex numbers sometime in high school, they'll see a person will picture them as members of a plane, so that the real part is plotted on the horizontal axis, and the imaginary part, the coefficient of I, the imaginary part is plotted on the vertical axis. And then in that context, the distance of the point from the origin is, you would write that, of course, with absolute value bars, because that's how you ever denote the size of an object, is the square root of a squared plus b squared. And the point about the complex numbers is that all quadratics factor, not just this one, all quadratics factor. That is, in contrast with the reals, complex numbers has no irreducible quadratic. And summing it all up, what we get is that the fundamental theorem of algebra with complex numbers, polynomials with complex coefficients, factor completely into linear polynomials with complex coefficients. The factorization is unique, but we're focused here on why did I switch from reals to complexes, and the answer is because you can completely factor polynomials. You haven't seen yet why I want to completely factor polynomials, but I do. You can completely factor polynomials if you use complex numbers. So complex numbers are a little more, shall we say, complex, but they have the advantage that polynomials completely factor. And we're going to be working with polynomials, so we're going to want to factor them. Okay? Okay, so what does this mean in terms of the linear algebra that we've been doing in the previous sections? And the answer is that we're going to have, for example, matrices. We won't see them very often for examples, but we could, in principle, see matrices with complex numbers as entries. I'm reminding a person up here how you add complex numbers is basically you add the real parts and you add the complex parts. Excuse me, I said that wrong. You add the real parts and you add the imaginary parts. Multiplication is, it's not awful, but it's just slightly more complicated too. So a plus bi times c plus di. So we do what, at least in my high school, we call FOIL. You distribute. You take a times c, a times di, and then you take bi times c and bi times di, and you account for the fact that I times I is minus 1. You gather terms and you end up with ac minus bd. Look familiar? It looks like a determinant there. But anyway, AC minus BD and AD plus BC times I. So it's kind of a slightly more involved operation, but it's pretty, from high school algebra, it's pretty much what you do what you do. It just turns out to be more complicated here. Okay, now everything that we did before, we're going to carry over. And as an example, the standard basis for Cn is we're going to have that be a vector space over C, and I'll denote it with script E sub n, and you see it's 1 plus 0i. I made the point that those are complex numbers all the way out to 1 plus 0i in the last entry. Okay, so all the stuff that we did before will carry over. We just simply are going to, at some point pretty soon, it must be pretty soon because we're coming to the end of the semester, at some point we're going to want to say, and then factor this polynomial, and we can't do that over the reals. We can't do that with confidence over the reals, so instead we've switched to working over the complex numbers. Okay, very good. So next time we're going to talk about a property called similarity, and that'll start us on the journey, finishing off here the last part of the course. So very good. Bye. Hi. Okay, last time we talked about switching from vector spaces that where the scalars are real numbers over to vector spaces where the scalars are complex numbers, motivated by the need that we will have when we work through this chapter to factor polynomials. So naturally the check-in talks about that. So you see it here. I'm doing two kind of vector spacey things with complex numbers instead of real numbers. All right, so let's have a whack. Let's see here. So the first thing is I want to represent, number one, with respect to the standard basis, the vector that is made of complex numbers. Okay, and the point here is that this is very straightforward. So I'm just going to write 1 plus I, 2 minus I as a combination of 1, 0 and 0, 1. And it's just as simple as saying 1 plus I times and 2 minus I times. That's all. So in short, the representation with respect to the standard basis of the given vector, 1 plus I, 2 minus I, is itself. So as happened before, the advantage of the standard basis is that vectors represent themselves. So many of the things that we've seen before carry over when we move to this new place. Let's see, number 2. Oh, I forgot already. It's a linear combination. It's sort of the very heart of what it means to be a vector space. 2i, 3 plus 2i times the vector is 2 plus I, 2, and then minus I times 1, 4. And again, we've seen, yeah, I talked about it last time, 2, 1, and 4. Those are complex numbers. They're also real numbers, but they're also complex numbers. So this is a combination of scalars and vectors where everybody is involved with a vector space over the complex numbers. The two-dimensional vector space over the complex numbers. Okay, so let's do the combination. Let's see here. You get kind of good at combining the complex numbers after a while. Let's see how I do. So 3 times 2 is 6. 2i times I is minus 2. So 6 minus 2 makes 4. And then 3 times I is 3i. 2 times 2 is 3i, and 4i makes 7i. And then on the bottom, 6 plus 4i. And then over here, I get minus, oh, I guess I'm going to write plus, and then 4i. And then now I'm just doing arithmetic here, so that's always the hard part. Let's see, 4 plus 7i minus I, so I think I'm looking at 4 plus 6i. And 6 plus 4i, take away 4i, so it's just 6. Okay, so the usual computations that we've done so many times throughout the course here all carry over exactly, except that you have to do maybe a little practicing multiplying a plus bi times c plus di. But except for that, you know, the calculations all go pretty much the same way. Okay, great. So we are ready now to start thinking about the material, the sort of heart of the chapter, the reason why we made the switch to complex numbers. And so here we go. Similarity. So the basic idea is I want to combine, I want to take a special case of matrix equivalence. So we define two matrices H and H hat to be equivalent. You remember this? If they express the same map, but with respect to different starting and ending bases. So I had an H hat. So H and capital H hat are equivalent if they can be thought of as representing the same little h, but with respect possibly to different starting and ending bases. Right, so that's matrix equivalence. It has a meaning. It's not just a definition about PHQ. It has a meaning. It means somehow describes the same thing. Can be thought of as describing the same thing. I want to consider the special case of transformations. That is, I want to take little h to be a transformation. Instead of v and w, I want to have v and v. And it so happens that, in fact, I'm going to have v and v both with respect to b, and v and v both with respect to d. So I'm going to take all the v's and w's and make them v's and v's. Instead of b and d, I'm going to have b and b. Instead of b hat and d hat, I'm going to have d and d. And so this picture on the bottom is just a special case of the picture on the top. Okay. So we've learned how to read these diagrams before. And so let's see, a t hat here, you can get by going straight over the representation with respect to dd of t, or you can get t hat by going up, over, and then down. So the representation here with respect to BD inverse, that's the up. Remember, it goes on the far side. It's a little tricky. Well, it's not tricky so much as it's easy to mess it up. So the representation with respect to BD inverse, because you're going against the arrow. Over is the representation with respect to BB. Down is the representation with respect to BD of the identity. Okay, so this picture is a special case of this picture in the context where you have a V and a V. We'll define that two matrices are similar if they meet that picture. Two matrices are similar if there's a non-singular capital P where T hat is capital T capital P inverse. And I'm just reminding you, you're going to go back to the previous slide. So this is playing the role of capital P, and this is obviously capital P inverse. Okay, so just as an example, one of my favorite examples here. So you consider the derivative map from P2 to P2. It's a natural map from a space to itself, a natural transformation of the space. I'm going to fix two bases, and I just, as usual, I try to fix bases that aren't too easy and aren't too hard. But anyway, I fixed B. B is sort of the kind of the easiest basis, but I fixed D to be at least not ridiculously easy. So here we go. I'm going to calculate T, and then I'm going to use that to calculate T hat. All right, so let's see how I do. So to calculate T, I of course have to find the effect of the derivative map on every one of the basis vectors in B. So the effect of the derivative map on 1, the effect of the derivative map on x, and the effect of the derivative map on x squared. I have to, of course, we know what the derivative of 1 is. We know what the derivative of x is, and we know what the derivative of x squared is, you know, the 2x and sort of stuff. So now I have to represent with respect to the ending basis, but it's still B. So represent with respect to B the derivative of 1, which we know is 0. I won't keep you in suspense. I want to represent with respect to ending basis the derivative of x, which we know is 1, the polynomial 1 plus 0x plus 0x squared. Anyway, 1. And represent with respect to B the derivative of x squared, which we know is the polynomial 0 plus 2x plus 0x squared. There we go. That wasn't hard. Did that all by eye. So what I get is the matrix capital T is put together the three vectors 0, 0, 0, 1, 0, 0, and 0, 2, 0. There you go. That's the representation with respect to, in some sense, the natural basis or the canonical basis for poly 2 of the derivative map. So next, oops, I went the wrong way. Sorry. Next, of course, I have to worry about the representation with respect to B comma D of the identity map. All right, so there we go. So the representation with respect to B comma D of the identity map. So I write down the bases, the members of capital B. So 1, x, and x squared. I apply the identity map to them. I know it's silly, but if you do every problem the same way, that's a good technique for teaching, is to do every problem the same way. And then people start saying, after 5 or 6 or 10 or so, however many, people start saying, you know, you could have skipped that step. And at that point, they're ready to skip the step. So anyway, the identity, you could skip that step. Represented with respect to the output basis. Again, going back to the picture, I just think the picture is such a help, represented with respect to the output basis. The output basis is 1, 1 plus x plus x squared, and it's easy enough that a person can eyeball the answer. The representation of 1, the representation of x with respect to 1, 1 plus x squared, and the representation with respect to 1, 1 plus x plus x squared of x squared. You put those three together into a matrix, and there you go. Okay, so I put these three together into a matrix, and there I go. Here we go, back to reminding myself what I'm doing. I have this picture. I put those three together into a matrix. That's the right-hand side. It's easy to get confused, left and right. That's the right-hand side. That's what on the next screen I called capital P. Here is what I called capital T. Here is capital P inverse. There is capital P. Capital P inverse I found in the usual find the matrix inverse way. You could, if you wanted, do this computation going in the other direction, but anyway, I found the inverse of this matrix by, you remember, you write down the matrix and you write the identity to it, and then you do Gauss-Jordan elimination, and you end up with the inverse. So there it is. Okay, so here are the parts. There's T, there's P inverse. When you multiply together P times T times P inverse in that order, when you multiply together P times T times P inverse. That means you're following this diagram. And you get this. So we have this. All right, we've basically calculated the bottom line of that arrow diagram. Now to check that, just to underline what the arrow diagram says, of course, I'm going to compute it by hand. So I'm going to compute the representation with respect to D of little t here. So the representation with respect to D of the derivative map. All right. So here is the effect of the derivative map on the members of capital D. So capital D, the derivative map's effect on 1, the derivative map's effect on 1 plus x, and the derivative map's effect on 1 plus x squared. So we know what the derivative of 1 is, we know what the derivative of 1 plus x is, we know what the derivative of 1 plus x squared is. Finally, to get the representation, I have to represent those with respect to the output basis, which is again D. So represent 0 with respect to 1, 1 plus x, 1 plus x squared. There it is. Represent the quadratic polynomial 1 plus 0x squared with respect to 1, 1 plus x, 1 plus x squared. And there it is. You can do those by eye, for sure. And then finally, represent 1 plus 2x with respect to 1, 1 plus x, 1 plus x squared. And obviously 1 plus 2x, you need a 2 for the x, and it's like that. And of course, that better be the same answer as I got earlier, and it is. Okay, the definition, of course, the definition of here we go, back to the definition of similarity is phrased in terms of matrices, so strictly speaking, it doesn't require me to think about the underlying maps. I can just compute the matrices, and sometimes that's what we want to do. If you give me a T and a P, I can, of course, compute P times T times P inverse, provided that you can find the inverse for P. And so I just computed it. The point here is that I don't have to think about the underlying maps. I can simply do the matrix computation. We take the point of view in this class that the underlying maps, that understanding the underlying maps gives a person an idea about where all the definitions come from, what are all these computations supposed to be talking about. But we're going to be pragmatic. Is that if simply doing the matrix computations gets the sort of clear answer, then we'll simply do the matrix computations. So the definition doesn't require me to open it up and figure out what is the underlying map. I can just simply compute. The only matrix similar to the zero matrix is if you take P times Z times P inverse, then you get P times Z, which is Z. And the identity matrix has the same property because of P times I gives you P, and then P inverse gives you I. So the zero matrix and the identity matrix have the property that they are similar only to themselves. Now other matrices are similar. It's possible these two matrices are similar, so these matrices are related, but the zero matrix is sort of related only to itself. The identity matrix is related only to itself. So some matrices are kind of alone, and some matrices have friends. So of course, you've seen this, I don't know, maybe half a dozen times in this course. Now you know where we're going. Similarity is an equivalence relation. That is to say, similarity breaks the universe of all matrices up into subsets. Some matrices are similar to each other, some matrices are not. Matrices that are similar belong in the same part, matrices that are not similar belong in separate parts. So we can, in some sense, understand what matrices are about by saying all of these matrices represent the same transformation in that arrow diagram picture. All of these matrices represent the same transformation in that arrow diagram picture. And so these are somehow all the same, whatever that means. Now, matrix similarity is a special case of matrix equivalence. That's what I meant at the beginning of this video when we took the matrix equivalence picture and specialized it by writing VV instead of VW. That is, I took W to be V kind of thing. So matrix similarity is a special case of matrix equivalence. So it follows from that, because it's a special case, that if two matrices are similar, necessarily they are equivalent. But what about the converse? if two matrices are equivalent, must they necessarily be similar? They're going to be square to be similar. And the answer is no. Just as an example, the matrix equivalence class of the identity matrix, you might remember, the matrix equivalence class of the identity matrix consists of all non-singular matrices, all matrices that represent an isomorphism, all non-singular matrices of that size. But just a second ago, we showed that the similarity class of the identity matrix contains only one matrix. So matrix similarity takes the matrix equivalence classes and breaks them up into smaller parts. You can have two matrices S and T that are similar. Those are going to be square matrices. You can have two matrices S and T that are similar, but that are not equivalent. Okay, just to name an example, take S to be the 3x3 identity matrix, and take T to be any 3x3 matrix of rank 3, that when you do Gauss's method on it, you end up without any zero rows. You end up with 3 different non-zero rows. Okay, so similarity gives a finer partition than does equivalence. Similarity breaks the universe of cases up into smaller cases. So, of course, we've done this many times before now, half dozen times anyhow. What we want is a canonical form to represent the similarity classes. We want to say, give me a good representative of this similarity class. Give me a good representative of this similarity class. Give me a good... So we want to represent here the similarity classes. And the thrust here of this chapter will be that some classes, not all, but some classes, are represented by a diagonal matrix. Okay, and so we'll talk about that next time. We're going to talk about diagonalizability. That's the next topic. When can you find a matrix similar to the one you have that is a diagonal matrix? Again, when can you find a matrix that fits the arrow diagram that you have, but the matrix you're finding is diagonal, so easy to understand. Matrix you're finding is diagonal matrix. It's all zeros except for possibly non-zero entries on the diagonal. Okay, very good. See you next time. Hey. So last time we talked about the definition of similarity between two matrices, and we described how similarity is the specialization of matrix equivalence to the context where you're looking at transformations. So instead of having V and W, you have V and V. Instead of having B and D, you have B and B. So we look at the specialization of the arrow diagram to the context of transformations. So of course the check-in asks us to do one of those. So let's have a whack here. Let's see, so I've got a map T, a transformation T, that sends the plane to the plane. And it just simply takes x, y, and as always, I try to pick a transformation that isn't too hard, but most importantly, isn't too easy. You don't want to do the identity map or something like that. So I took a x plus 2y and 3y. Right? And so you want a more generic example. So B is, I guess I chose 2, 0, and 0, 3. For one of the bases. That one might have been a little too easy. And then the other of the bases, I chose one that I've often used, 1, 1, and 1 minus 1. Okay, Hadamard. So we've often used this and found it, not too hard, not too easy in the past. So question number 1 says, represent the map with respect to the B's. Great. So we've done this many, many times. You've got to take the two basis vectors, 2, 0 and 0, 3, and figure out where T sends them. And then at the end, I'll have to represent with respect to B. So 2, 0, if you plug in 2 for x and 0 for y, goes to 2, 0. So it so happens to be not changed by T. 0, 3, you plug in 0 for x and 3 for y, and you end up at what, 6, 9. So what I want to do next is represent those outputs with respect to the output basis. So representation with respect to the basis B of 2, 0, and the representation with respect to the basis B of 6, 9. And let's see, what the heck. So 2 zeros, of course, 1 times the first basis vector plus 0 times the second. That was easy. And then 6, 9, in terms of 0, 3, I want to get here let's see, I got to get 3 times the first basis vector and 3 times the second basis vector. And so finally I've calculated the representation of the map with respect to b comma b. And if you just simply write those down as column vectors, we've done this many times before. There we go. Next, to do the arrow diagram, is that I have to go, of course, up, over, and down. So we saw in the section that represent the down and then take the inverse to get the up. So here we go. Representation with respect to b comma d of the identity. So that'll represent the down, and then the up will be the inverse of that map. Okay, so let's see. I got to figure out what the identity. I know this is silly, but I do it anyway, and all it costs me is a minute or two. The advantage is uniformity. With respect to the identity map, 0, 3. And when you're teaching a subject, uniformity has the advantage that a person who is at the moment confused can say, oh, every time you do X. So anyway, I got to represent those with respect to the output basis. So the representation with respect to the output basis of 2, 0. And the representation with respect to the output basis of 0, 3. So the output basis is this 1, 1, 1 minus 1. So let's see, to represent 2, 0, you want to do to represent 2, 0, you want to take 1 of the first and 1 of the second. So this plus this makes 2 on the top line, this plus this makes 0 on the bottom line. And then 0, 3. So let's see, so 0, 3, so I want to take, so 0, so I want to be halfway, so I'm looking at, okay, so 1.5 and minus 1.5. Right, remember how you do it? You got to take the average of the two, and then what's the increment? Anyway, Gauss's method, of course, would get you the answer if you had a brain cramp and couldn't remember what you were doing. So we get, finally, the representation with respect to b comma d of the identity. And you write those two in as columns, 1, 1, and 1.5 minus 1.5. That's in the up, over, and down. This is the down. So while I'm here, I'll do the up. So I got to take the representation, the same vector, same matrix, b comma d of the identity, inverse. Rather than calculate it straight out, I'm just going to take the inverse just because I know the inverse formula for 2 by 2 matrices. So I get 1 over minus 3. And what are you got to flip these two, minus 1.5 and 1, and you got to take the negative of the other two, so minus 1.5 and minus 1. And when I multiply by minus 1/3, what do you get here? You get what? A half? That's not a minus sign, that's an equals. And a third, and minus a third. That's right. That's right. Good thing I have my notes. I had to flub that up. And then finally 3. We want to use the work that we have here to do the up, over, and down. So 3. Can you represent with respect to d comma d, the map T? And of course, you got to do the up, over, and down, and the only part that a person can flub up here is to put them in the wrong order. Up goes first, and first means rightmost. So so it's going to go 1/2, 1/2, 1/3, minus 1/3. That's up. Over is 1, 3, 0, 3, and down. Down is 1, 1.5, 1, minus 1.5. And then you multiply those three together, and that gives you t. And now I multiplied them together, and just to save myself from flubbing it up on the camera, so I happen to get this 3210. Anyway, I happen to get this, so that's the bottom line, the representation with respect to d comma d of t. Just to remind a person what that's about. So this is about this map where you look where the first basis vector goes and you look where the second basis vector goes. So where does the first basis vector go? It goes, so 1, 1 goes under t where, and 1 minus 1. 1 minus 1 goes under t to where. So 1, 1 under t goes to what? 1, 1 makes 3 on the top and 3 on the bottom. And 1 minus 1 goes to where? So 1 and minus 1 makes minus 1 and a minus 3. And now you ask yourself, is that 3 times the first plus 0 times the second? 3 times the first plus 0 times the second? Yes, it is. Is this minus 2 times the first plus 1 times the second? Is this minus 2 times the first plus 1 times the second? Minus 2 plus 1, yeah? Minus 2 plus 1, yeah. Okay, so the two calculations agree. The calculation that I get by actually doing it out and the calculation that I get by multiplying the three matrices agree. Okay, very good. So last time we defined matrix similarity, and I think naturally we defined it by saying that two matrices are similar if they represent the same transformation. So okay, so now I said what are the canonical representatives of the equivalence classes, and I said that not all the equivalence classes are represented this way, but that many of the equivalence classes are represented by diagonal matrices. Diagonal matrices are especially easy to work with, so that's especially convenient form. So now I'm asking, if you give me a matrix, when is it the case that that matrix is similar to a diagonal matrix? That is to say, when can I say that I can represent a transformation by a diagonal matrix? Okay, so that gives me, finally, a transformation is diagonalizable if it has a diagonal representation with respect to b comma b, the same basis for the codomain as for the domain. And then a diagonalizable matrix is one that's similar to a diagonal matrix. So capital T is diagonalizable if there's a P where you get P, T, P inverse. So of course this is the map version of the statement, and in this course we're taking the point of view that the map version is our touchstone for sensibility. When we try to say what does it mean, then we think about the maps. This is the matrix version of the statement. So when we want to compute, we think this kind of thing. That doesn't, we sort of give this a primary status, but that doesn't mean that this is silly. All right. So the very first example is the very first example. I wrote down a 3 by 3 matrix. I took a P and a P inverse, and I multiplied P, T, P inverse. And when I multiplied P, T, P inverse, I got this. Now, of course, when I actually made up the problem, I did the opposite. I started with a D, and I multiplied in the opposite order to get T. But anyway, the statement that's written here is that you can take a matrix, re-multiply it by P, post-multiply it by P inverse, and get a diagonal. Then you say that the matrix is diagonalizable. Never mind how I cooked up the example. So the first point is that there are matrices that are not diagonalizable. So there are going to be similarity classes in which there is no diagonal matrix. So this idea that we're going to represent transformations by a diagonal matrix is not always possible. So convince me that this matrix right here is not diagonalizable. It looks nearly diagonal. I mean, you just got a 1 below the diagonal. Can't you somehow, move, swap the two rows? So the answer is no. So n is not the zero matrix, obviously. So it's not similar to the zero matrix, because remember that the zero matrix is alone in its similarity class. Okay, all right, so that's fine. So if n were to be similar to a diagonal matrix, then the diagonal matrix would have at least one non-zero entry on the diagonal. Now the whole point of diagonal matrices, the reason why we're interested in diagonal matrices, is because they're so easy to calculate with. So picture in your head a 2 by 2 diagonal matrix. Put some numbers on the diagonal. I don't know, 3 and 5, 1 and 2, A and B. I don't care. Put some numbers on the diagonal. Square D. What happens when you square D? D is a 2 by 2 diagonal matrix. Multiply it by itself. When you square D, you just square the entries on the diagonal. So one way in which a diagonal matrix is easy to compute is that it's easy to find the square of it. But here, when you square n, do it in your head, you get the zero matrix. So there's something wrong with that. Is that n squared is the zero matrix. So if you had a map that was represented by n with respect to b comma b, that would mean that the composition n composed with n is the zero map. That would mean that any matrix representing n with respect to any basis comma basis has a square that is the zero matrix. Because the only thing that represents the zero map is the zero matrix. But d squared isn't going to be the zero matrix. So n can't be diagonalizable. Okay, so what we find is that some matrices, and this is an example that we were able to talk our way through, some matrices just simply cannot be expressed in diagonal form. So there are some transformations for which there is no diagonal representation. Namely, for example, fix the standard basis, and the transformation that does this, that is represented by this with respect to the standard basis, that transformation is not diagonalizable. But there's lots of diagonalizable transformations, it's just that that one isn't. So we're pointing out that some can be diagonalized, some cannot. All right. So the lemma that we have here, it's really a restatement of the definition of diagonalizable. But anyway, the lemma here gives us a criteria for when a transformation is diagonalizable. When can you find a diagonal representation? So I mentioned this is really just a restatement of the definition of diagonalizable, definition of diagonal representation, but it puts in all the words. By the way, it's convenient in this context and standard in this context to use for the scalars, for the entries on the diagonal, to use lambda, the Greek letter lambda, lambda 1, lambda 2, etc., up to lambda n. It's a convention, but everybody uses it. If you stick to that convention, sometimes it helps a person be, understand what you see, like if you Google around, or understand conversations that you hear. So I'm going to follow the same convention. Those will be the numbers on the diagonal. So what does it mean for T to be diagonalizable? It means that there's a basis, and T is going to be represented with respect to B comma B, and the matrix representing T with respect to B comma B will have these numbers right here, scalars, down the diagonal. Well, if the scalar is down the diagonal, that simply means that T of beta I equals lambda I beta I. That's just what the representation means. All of the coefficients of that vector are zeros except for the 1, and that one is a lambda I. So this is really just a restatement of what it means for a representation to be diagonal, and that's what the proof says. The proof says that the representation with respect to B comma B of T is, you write down the column vector for T of beta 1 and the column vector for the representation of T of beta 2, and all the way out to the column vector for the representation of T of beta n. And the definition of diagonalizable exactly is that you have a lambda 1 there, and everything else in that column is zeros. And lambda 2 is in the second entry, and everything else in that column is 0, etc. Down to lambda n is the last entry in the last column. and then just trying to understand here, what does the representation do? And of course, we know what the representation do. The whole point of the representation is that if you take the representation and you multiply it by a vector representing, then it's by definition matrix vector multiplication. That was the point of matrix vector multiplication. But we can see what happens here. If this 1 is in the ith position, then this is the representation of beta I. So everything in this column vector is 0 except for a 1 in the ith entry. That's beta I. So what happens if you multiply this matrix times the thing representing beta I? Why, you get the thing representing lambda I times beta I, just what it says. T of beta I is lambda I times beta I. Okay, so really, this should be thought of as not a kind of a discovery. This is really a restatement of what it means to have a diagonal matrix for a representation, is that when you think about what the representation does, it represents this action right here. So a transformation is diagonalizable if and only if the basis that you're using, the b comma b, the basis that you're using has this property that if you take t of beta I, then you just multiply it by a number. Maybe it's beta I gets mapped to 7 times beta I, or beta I gets mapped to minus 3 times beta I, or beta I, remember these are complex numbers, gets mapped to 2 plus 2 I times itself. So of course, need an example that illustrates the result, and specifically, I'm gonna put down an example that is at least in the direction of not cooked up. The example that I gave you earlier of a diagonalizable transformation, I cooked it up. I wrote down a diagonal matrix, then I wrote down a P and the P inverse, and I kind of went backwards, and I arrived at some matrix that is all jumbled up numbers. And I said the jumbled up one can be diagonalized. Well, that is kind of a cooked up example. But this one is at least a little bit less cooked up. I'm starting with T and trying to find the diagonal matrix representing it. So that's more realistic. You would more typically in practice on the homework problems or wherever you're working, start with a matrix of jumbled up numbers and be asked to find the diagonal matrix that represents the same map. The diagonal matrix that's similar to T. Okay, so let's have a whack. How would you try to do such a thing? And you won't be surprised to find that it turns into a linear system. And anyway, off we go. So you suppose that you have that T represents, capital T represents lower t with respect to the standard basis, and we're going to try to find a basis capital B that gives a diagonal representation. All right, fair enough. So we suppose that T represents lowercase t with respect to the standard basis. We want to find a basis capital B giving a diagonal representation, and I don't know, I called it D for diagonal. I may regret that. Anyway, there we go. Strictly speaking, what's on the screen is correct. Okay, I can't overemphasize how much the arrow diagram, as with everything else, helps here, is that when a person starts saying to me, look, I get it, I'm sick of the arrow diagram, maybe they're ready to put it down. But for the first, I don't know, dozen problems that you do, please write the arrow diagram every time. I write it every time. I've done hundreds of these, I don't know, thousands maybe of these. Write the arrow diagram, I urge you to. So anyway, here we go. I have E2 and E2. Okay. Identity, identity. B and B. I'm looking for B. All right. So I want lambda 1 and lambda 2. This is a statement from the lemma. Excuse me. I want lambda 1 and lambda 2, where if you multiply the matrix times the basis vector, which I don't know yet, it will be lambda 1 times the basis vector. And also, if you multiply the matrix times the second basis vector, it'll be lambda 2 times the second basis vector. And again, I don't know the first basis vector, and I don't know the second basis vector, and I don't know lambda 1, and I don't know lambda 2. So pretty full of ignorance at this point. More specifically, what I want is I want to find when does multiplying this matrix times some basis vector multiply the basis vector by a scalar. So I want to find the scalars with the property that multiplying the matrix times the basis vector multiplies the scalar times the basis vector. third time. I want to find all the scalars x with the property that matrix times basis is the same as x times basis vector. Okay, so this has turned into a linear system. And a person can look at this linear system. I know you see the answers down here, but a person can look at this linear system and say, well, it's got 3 unknowns and only 2 equations. How could I hope to solve it? And the answer is you can hope to solve it because we know some things about linear systems. This is a homogeneous linear system. 99 times out of 100, a homogeneous linear system will have exactly one solution, b1 equals 0 and b2 equals 0. So when will a homogeneous system, and 0, 0 won't work for a basis vector, so that's right out. So when will a homogeneous system give something other than b1 equals 0 and b2 equals 0? Well, you got to have, right? You got to have some situation where, for example, the bottom row is 0 equals 0. Well, for example, if x is minus 1. If x is minus 1, then the bottom row becomes 0 equals 0. So if x is minus 1, then the bottom row becomes 0 equals 0. b2 is free. The top row then becomes, let's see, x is minus 1, so that's 5b1 plus b2 equals 0. There's infinitely many solutions. b2 is free, remember? And so I get that if x is minus 1, then I get a solution, and I call the x is a variable, lambda 1 is a constant. So I call the solution lambda 1 equals minus 1, and then solving that system in the usual way, b2 is free, so I'll express b1 in terms of b2. If x is minus 1, then I have 4 minus a minus 1 gives me 5, and when everything clears out here, I end up with the basis vectors for beta 1 have the property that the first component is minus 1/5 times the second component. So up here, if you take lambda 1 to be minus 1, and you take that the first component of beta 1 is minus 1/5 times the second component of beta 1, you're good. Cool. All right, so now I'm looking for the other possibility. What else can happen? Well, the other thing, you see the game now at this point. So I worked with the beta 2 free. Now I must be working with the beta 1. All right, so how do I make this fella here not have a trivial solution? And if you take x to be 4. So x is the variable, lambda 2 is the constant. So if you write 4 minus 4, then you get 0 times b1, and b1 is free in that case. And let's see, minus 1 minus 4, right? Minus 1 minus 4 gives you minus 1 minus 4 gives you minus 5, doesn't it? It says minus 5 times b2 equals 0. So that gives you that b2 is 0. b2 is 0 in this equation gives you 0 times b1 plus 0 equals, so I'm looking simply at b1 can be anything, b2 is 0. So I found 2 solutions. I found how to make this true. The first is to fix the variable x at minus 1, and then I solve that in the usual Gauss's method back substitution-y kind of way. The second is to take x to be 4, and I solve that in the usual back substitution Gauss's method kind of way, and I got infinitely many solutions for that. Okay, so the original matrix is diagonalizable to minus 1 and 4 on the diagonal by taking appropriate basis vectors. I could have taken any basis vector that I wanted, but I found these 2 convenient. So there are infinitely many beta 1 and beta 2s that I could have used for one of the basis vectors, and there are infinitely many, b1 and b2s. I said beta 1 and beta 2, forgive me. There are infinitely many b1 and b2s that I could have used for the first. There are infinitely many b1 and b2s that I could have used associated with lambda 2 equals 4, but I picked 1, 0. I don't know, I just picked 1, 0 just because it seemed easy. So, in short, when I'm asking the question for this particular matrix, when I'm asking the question, how can I diagonalize that transformation? I'm looking to solve systems that look like this. They have a variable x in them, and I'm finding different x's that make it possible to get non-trivial solutions, because let's face it, b1 equals 0, b2 equals 0 doesn't do you any good as a basis vector. 0, 0 is not a basis vector. So I need x's that make this linear system have non-trivial solutions. This is a homogeneous linear system, or it turns into a homogeneous linear system. And how can I make it have non-trivial solutions? Different x's give you different non-trivial solutions. And then finally down here, there was one way was to do it by taking -1. One way to do it was by taking lambda 2 equals 4. I have a basis vector associated with -1 and a basis vector associated with 4. Okay, very good. All right, so next time we're gonna tackle a very important subject, eigenvectors and eigenvalues that is tied to what we've just been talking about. So very important subject, big subject. So good, looking forward to it.
Hi. Okay, so very exciting, getting down toward the end, and this is really the last topic that we're going to talk about for the entire semester, for the series of videos. Okay, great. So let's get in. So we're looking at a matrix here for the check-in, and we're looking to find the lambdas, and for each one we're looking to find an associated basis vector. So it's a check-in just really of exactly what it was we talked about last time. So let's have a whack. Let's see. The matrix is 3, 0, 4. 0, 1, 1, and 0, 0, minus 2. Okay, and I'm looking to solve the equation b1, b2, b3 equals x times b1, b2, b3. That is, I'm looking for those vectors that are made x times as big. They're not rotated at all. They're simply multiplied by a factor of x. So for which x's is there such a vector? Now, obviously, of course, if you take the 3 b's to be 0, you can take x to be whatever you like, and you'll get a correct answer. We're going to throw 0 out as an acceptable answer because we're thinking of these as basis vectors. At the moment, we're thinking of these as members of a basis, and no 0 can't be a member of the basis. So we're going to regard that solution as not what we need. Okay, so let's have a whack then. What we saw is that you bring this over and you factor out the b's, and you're looking at 3, 0, 4, 0, 1, 1, 0, 0, minus 2. Take away x, 0, 0, 0, x, 0, 0, 0, x, all multiplied by b1, b2, b3 equals 0, 0, 0. In short, I'm looking to solve here 3 minus x, 0, 4, 0, 1 minus x, 1, and 0, 0. What happened to the minus? No, there it is. 0, 0, and it's minus 2 minus x. There it is. Minus 2 minus x by b1, b2, b3 equals 0, 0, 0. Okay, so I get the x's down the diagonal there. The minus x's down the diagonal. This is of course a linear system. I'll write it as a linear system. 3 minus x times b1 plus 4b3 equals 0. And what do I got then? 1 minus x times b2 plus b3 equals 0. And then finally minus 2 minus x times b3 equals 0. Alrighty, and of course we saw last time, we saw in the video, what the idea is here is that you say to yourself, for example, if I take x to be minus 2, why then I have 0 times b3 equals 0. This is a 0 equals 0 equation. So now I've got a free variable, namely b3, and so I've got infinitely many solutions, almost all of which are non-zero, and that's exactly what I need. So in my mind, I'll think of one of the answers as being -2. And then likewise here, if I take x to be 1, that will give me, similarly, will give me a non-trivial solution for the homogeneous system. And if I take x to be 3, that will give me finally a third solution, a third non-trivial solution for the homogeneous system. So let's have a whack. I want to put it all on one piece of paper, so I need a fresh piece of paper. Hope I don't forget what I was doing there. So let's see. I'm going to take this system right here, and I'm going to look at what happens when I take x to be -2. We're in the habit of, when you fix the x here, we're in the habit of writing the Greek letter lambda. So I'm going to do lambda1 equals -2. All right, so if I plug in lambda1 equals -2, and I remember the previous problem, here it is down here, I'd better use this to copy. So 3 minus a -2 gives me 5b1. And then there's a 4b3 equals 0. 1 minus a -2 gives me 3b2. And then there's a b3 equals 0. And then finally, of course, if I take x to be -2, if I freeze the solution of -2, why then I get 0 equals 0. So I have a homogeneous system. That has, of course, infinitely many solutions. I recognize that B3 is free, and B1 and B2 are leading variables. So let's see, what do I get here? That B2 is minus 1/3 B3. Of course, parameterizing with the free variable. And then up here, what B1 is minus 4/5 B3. And now, if I'm looking for an explicit B1, B2, and B3 that satisfy these three, of course, I could take B3 to B1 and get a lot of fractions, or I could take B3 to be 15 and get all integers. So I'll do that just to do something. So the basis vector of interest is I'm taking B3 to be 15. So 15. I could have taken B3 to be minus 109, whatever worked, but I just picked 15. And then to minus 5 and minus 12. Okay, so I think that if I take the matrix that I started with, 3, 0, 4, and write in minus 12, minus 5, 15, I will find that what I get over here is negative 2 times minus 12 minus 5, 15. Okay. Let's try the other ones. What was the second one? 1. So lambda sub 2 equals 1. So when I plug lambda sub 2 equals 1 into the same system, I'm not going to have space to write it here below, but same system. No, maybe I can fold this thing up. Just like arts and crafts here. Here we go. Here we go. Okay, so if I take x to be 1, if I look at the constant when x is 1, then what I get for a system is 3 minus 1 is 2b1 plus 4b3 equals 0. And then 0, of course, b3 equals 0. And minus 2 minus 1 is a minus 3 b3 equals 0. All right, so this, of course, is a linear system with infinitely many solutions, and I guess I get here, obviously, B3 is 0. B2 could be anything. There's no restriction on B2. Right? This doesn't mean that B2 is 0. This means there's no restriction on B2. So B2 can be anything. B2 is free. Don't write reals there. Write complexes. And then B1, well, if B3 is going to be 0, then B1 has to be 0. So if I pick a basis vector, I'm just picking one of the choices. There are lots of choices. I'm picking one. Oh, how about 0, 1, and 0? So 0, 1, and 0. I could have picked 0, 12, and 0. I don't know. I just picked. Okay. Okay, and then it seems to me the last one is lambda 3 equals 3. So again, I'm plugging it into this system of equations. I'm plugging in 3, 3, and 3. And what do I get here? If I plug in 3 there, I get 0 times b1, so I get 4b3 equals 0. If I plug in 3, then I get to what, minus 2. Minus 2b2 plus b3 equals 0. And if I plug in 3 there, I get minus 5b3 equals 0. Minus 2, minus 3, minus 5. That's right. Okay, so what do I make of this linear system? Well, obviously b3 is 0. So b3 is 0. If b3 is going to be 0, then b2 is 0 also. And again, there are no restrictions on b1. It isn't that b1 is 0, it's that there's no restrictions on it. So b1 can be anything. b1 is an element of the complex numbers. And so if I'm picking a basis vector, I could pick any complex number at all, but I'll pick 1 just out of sheer boringness. Okay, so what I've got then is a basis 1, 2, 3 that we saw in the result at the end of the last video, that associated with each of these lambdas is a different basis vector. Associated with each of these lambdas is a basis vector. So it happens that for each lambda there's one and only one basis vector here. Okay, all right, very good. Let's see, so let's get into the material that we're doing today. And I'm reminding you, starting off by reminding you that, that what we talked about last time was that what we were just doing in the check-in is that you can diagonalize the transformation exactly when there's a basis. In the check-in, of course, there were 3 basis elements, beta 1, beta 2, beta 3. Here it's beta 1 through beta n. And associated scalars, lambda 1, lambda 2, lambda 3, they were in the problem we just did, where t of beta I is lambda I times beta I. So we saw, for example, t of beta 1 was minus 2 times beta 1. T of beta 2 was 1 times beta 2. And t of beta 3 was 3. It says 3 of beta 3. 3 times beta 3. So t tripled beta 3. Okay. Okay, very good. Oops, went just too far. Okay, so I'm going to introduce the word eigenvalues and the word eigenvectors here. So a transformation has a scalar eigenvalue lambda. If there's a non-zero eigenvector, that's a zeta, the Greek letter zeta. I like that because I can use z's for the elements of the eigenvectors, so lowercase z's. So that's a Greek letter zeta. So a scalar eigenvalue lambda, if there's a non-zero eigenvector zeta, so that t of zeta is lambda times zeta. So it's just what we've been looking at. It's exactly what we've been looking at. And then this is the associated definition for a matrix. This is a transformation, this is a matrix. A square matrix T has a scalar eigenvalue associated with a non-zero eigenvector if T times zeta is lambda times zeta. Okay, so T is the matrix times the vector zeta is, a lambda is a scalar times the vector zeta. All right. Okay, and again, we saw that on the check-in. So here's an example, a small scale example. If I write down the diagonal matrix, happens to have 4 and 2 on its diagonals, then it has 2 different eigenvalues. The first one is 4, the second one is 2. So lambda 1 is 4, lambda 2 is 2. And I mentioned in the last videos, very standard to use lambdas for the eigenvalues. That's very common. Okay, and to say lambda 1 equals 4 here, I have to justify that by naming a vector that gets multiplied by 4, naming a non-zero vector that gets multiplied by 4, that is naming an associated eigenvector. All right, so I named 1, 0. I could have named 2, 0, or 3, 0, or minus 5, 0, but anyway, I named 1, 0. If you do the matrix vector multiplication, what you find is that you've multiplied the input vector by 4. And similarly down here, just simply because the diagonal matrix is so easy to understand what it does, if you write down here, associated with the eigenvalue of 2, if you write down here what happens when you do the matrix multiplication of this kind of vector, 0, 1, or 0, 5, or 0, 100, remember 0, 0 isn't acceptable, got to be non-zero. if you do the matrix vector multiplication, you end up doubling the vectors. So the idea here is that if you think of the matrix as representing a transformation in the plane, especially like in the check-in, if you think of that matrix as representing the transformation in the plane, then the transformation acts on those vectors in a particularly simple way. So the advantage of the diagonal matrices is that they're very easy to understand. However, note that not every vector is just simply rescaled. Just as an example, if I don't take 1, 0 or 0, 1, if I take something kind of in the middle, it doesn't get rescaled. So the vectors that are rescaled, the eigenvectors, are in some way special. Okay, so obviously I gave a definition and you know how I operate. Next up is to be able to compute. We want to be able to compute the things we just defined. So I'm giving you a matrix here. T is just a matrix with some screwball numbers in it. And it says find the eigenvalues and associated eigenvectors of this matrix. So here we go. We want to find x's where t times zeta is x times zeta for non-zero zetas. So we've done this before, and in particular, we've done it just a minute ago with the check-in. You write, you bring everything over to the left-hand side of the equation. You factor out the vector so that you've got now 0 minus x, 7 minus x, 4 minus x in the diagonal. And this is a homogeneous system. So when we think about what we know about homogeneous systems, of course, what we know is that a homogeneous system has a non-zero solution. That's what we're interested in. Homogeneous system has a non-zero solution exactly if the matrix is singular. And we saw those in the check-in. We got with lambda 1 equals minus 2, we had a singular system. Remember, the bottom row was 0 equals 0 sort of stuff. Okay, but now we know something about singular systems. So we know that the matrix is singular is exactly happens if the matrix has a determinant of 0. So I'm going to take the determinant of that matrix. Here we go. It didn't all fit on one slide, so I put it on the next slide. I took the determinant of that matrix. The matrix has numbers and x's in it. When you take the determinant, you end up with an expression that has some x's in it, and I'm not going to go through the details of taking the determinant of that matrix, but it turns out to give you a cubic. Kind of easy to see because there's 3 x's there, but anyway, turns out to give you a cubic, turns out to give you this particular cubic. It's also not easy to see, but nonetheless true, that this cubic factors into x minus 5, x minus 4, and x minus 2. You'll remember that at the start of this chapter we said that we're going to work with the complex numbers because we want that the polynomials factor completely. Now this doesn't have complex numbers in it, but nonetheless the explanation for why did we switch to complex numbers is exactly this. I want to figure out for which x's is this matrix singular. That leads to a polynomial. When can I factor the polynomial? You can factor the polynomial precisely if you're working with complex numbers. So that's exactly why we made the switch, is what's written here. Okay, but see, I don't want to be distracted by the details of complex numbers here. I want to be focused on what eigenvectors and eigenvalues are about. So I wrote down a cubic that happens to factor into 3 easy numbers. So I get the eigenvalues of the first one is 5, the second one is 4, and the third one is 2. Now, just as we did on the check-in, I want to find some eigenvectors associated with those eigenvalues. So here we go. To find the eigenvectors associated with eigenvalue of 5, you do what we did on the check-in. Oops, sorry, clicked not far enough. To associate with an eigenvalue of 5, you do what we did on check-in. You plug in 5, 5, and 5. You get 0, 5, 7, negative 2, 2, 7, negative 1, 1, negative 1. So again, I'm subtracting 5 because I plugged in for x equals 5, and that will give me a solution, a non-trivial solution to the homogeneous system. I know that plugging in x equals 5 gives me a non-trivial solution, and here it is. I did the computation kind of off screen. So Gauss's method gives the solution set, and the non-zero elements of that solution set are called the eigenvectors. Here's the solution set. I call it V sub 5 because it's the V, the vector space, associated with 5. you can see that it's a vector space. It's a dimension 1 vector space. It's all multiples of 1, 1, 0. Obviously, then on the next slide, I'm going to worry about the eigenvectors associated with lambda 2 equals 4 and the eigenvectors associated with lambda 3 equals 2. So here we go. The eigenvectors associated with an eigenvalue of 4. Well, I'm going to flip back. I know it's annoying to keep flipping, but I'm going to do it anyway. I'm going to flip back and remind a person, where do you plug in 4? Here we go. Plug in 4 right here. You get minus 4, 3, and 0. When you do, you get minus 4, 3, and 0. Now you have a matrix, and you're going to do Gauss's method. You're going to find that it has infinitely many solutions, and we've done this so many times that I think we can take a high-level view at this point and not mess around with the details too much, and say here that when you solve that system, you get infinitely many solutions. It's all the multiples of minus 7, minus 7, 1. Do you see that when I say multiples, I say complex number multiples, but anyway, all the multiples. I write it as V sub 4, just when you're working your way through the book. I write it as V sub 4 because it's clearly a vector space. It's the one associated with 4. And finally, what do you do for x equals 2? I'm going to flip back. I know it's annoying, but I'm going to do it anyway. There we go. There we go. You plug in the 2, the 2, and the 2. That gives you a linear system that Gauss's method will solve. There we go. That gives you a linear system that Gauss's method will solve. A person sees right away the first 2 rows are the same here. So it's pretty obvious that there are infinitely many solutions to this linear system. And it so happens when Gauss's method solves it that you get all the multiples of 1 minus 1, 1. Okay? So in short, I can find the eigenvalues and associated eigenvectors of this matrix. The eigenvalues are on this slide here. The eigenvalues are 5, 4, and 2. The associated eigenvectors are the non-zero vectors in this set. That's associated with 5. The non-zero vectors in this set, those are associated with 4. And the non-zero members of this set, those are the eigenvectors associated with the eigenvalue of 2. Okay. Obviously going to do the same problem. One is not enough. One example is not enough. But just to really step back and take just that sort of 10-second breath here, is that we are given a matrix and want to find the eigenvalues and then use those eigenvalues to find the associated eigenvectors. Okay. To find the eigenvalues, we realized that we need to find a determinant. Okay, here we go. Okay, so 3, 1, 1, 3. You start with this equation. It asks which vectors b1, b2 are multiplied by a scalar, which vectors are doubled or tripled or multiplied by 4 or minus 1 or minus 2 or minus 3 sort of stuff. Now, there's lots of vectors that have crazy things done to them. Which vectors have this, in some sense, the simplest possible thing done to them? Just like the diagonal matrix would multiply some vectors by the things on the diagonal, well, which vectors here are simply rescaled? All right. And that leads immediately to this equation right here, homogeneous linear system like we were seeing in the first week of class. We want to know, when does this homogeneous linear system have infinitely many solutions, because the unique solution of 0 won't do. So we ask ourselves, when is the determinant of the matrix equal to 0? I took the determinant of the matrix. For a 2 by 2 matrix, it's not very hard. You get a quadratic, and we know we could apply the quadratic formula, or anyway, we spent a lot of time in high school practicing factoring, maybe junior high, practicing factoring quadratics. There we go. This one factors into x minus 2 and x minus 4. So when is it equal to 0? It's equal to 0 for the two cases of 2 and 4. If I take the x equals 2 version of what's here, I get a linear system. So many times we've done Gauss's method, I'm really reluctant to get up to my elbows in doing Gauss's method here. But a person does see right away, right, that this is the same two equations. Anyway, so we get here the vectors associated with the eigenvalue of 2, the eigenvectors associated with the eigenvalue of 2 is all the ones where b1 and b2 have the opposite sign. And of course, they can be complex numbers. b1 and b2 have the opposite sign. Next up, what about if you take the eigenvalue of 4? So then you get a -1 and a -1, and you look here and you say to yourself, well, these two are not the same equation, but one's a negative of the other. So again, infinitely many solutions. Here we go. The eigenvectors are the non-zero vectors in this set. And of course, we're very good at this stuff by now. This is a dimension 1 vector space. It is all the ones where b1 and b2 are the same, and we're only interested in the non-zero members. But anyway, the ones where b1 and b2 are the same, and again, complex numbers. So for example, 3 plus I, 3 plus I. 5, 5, minus I, minus I. If the matrix is upper diagonal or lower diagonal, then the polynomial is especially easy to factor. So you'll see like homework questions that do that. Factoring polynomials is a separate question entirely. If you get a sort of a tough polynomial to factor, what exactly do you do? But I'm trying not to focus my attention on how do you factor hard polynomials. I'm trying to focus my attention on how do you find eigenvalues and eigenvectors. So we're just at the moment trying to think about problems where the factoring is not the hard part, where the hard part is the conceptual understanding of eigenvalues and eigenvectors. Okay. So if the matrix is upper or lower diagonal, then it's very easy to see what to do. Obviously here that the determinant, because of these zeros, the determinant is simply the product down the diagonal, and so you get 3 minus x and 2 minus x appears twice. So there is an eigenvalue of 3 and an eigenvalue of 2 that gets repeated. Here's the system when you plug in lambda 1 equals 3, 2 minus 3, 3 minus 3, 2 minus 3. And a person sees right away that the second and third equation are multiples of each other, so we're going to have infinitely many solutions. And here's the infinitely many solutions. The eigenvectors associated with an eigenvalue of 3 are all of these that are non-zero. So all the multiples of 1, 1, 0, where z2 is not equal to 0 and is a complex number. So just as a for instance, 3 plus I, 0, or 7, 7, 0. Those are eigenvectors associated with an eigenvalue of 3. Right? What about the eigenvalue of 2? So for the eigenvalue of 2, you plug in 2, 2, 2, and you get 0, 1, 0. There we go, wrote it down there. A person sees right away the 0 row. So you solve this and you get, again, infinitely many solutions. I know that 2 is a repeated eigenvalue, but this is only a dimension 1 space. So you don't get repeated eigenvectors necessarily. Sometimes you do, sometimes you don't. But in this case, you don't. In any event, here, we've done Gauss's method so many times. You're simply looking at the eigenvectors associated with an eigenvalue of 2 are all the multiples, the non-zero multiples, of 1, 0, 0 for any complex number. Okay, and then comment here before we close. Matrices that are similar have the same eigenvalues, but not necessarily the same eigenvectors. So here's an example. These two matrices are similar. I wrote down the p that it takes to transform the one to the other. It's easy to check, because this is a diagonal matrix, that 1, 0, 0 is an eigenvector associated with the eigenvalue 4. But a little bit of computation shows that that just simply isn't true for the second one. It just isn't true. That's all there is to it. So matrices that are similar have the same eigenvalues, but don't have to have the same eigenvectors. Okay? Okay, that's enough for one day, so a person should try some homework and have a whack at getting a better feel for it, but we'll come back next time and do some more with eigenvalues and eigenvectors. Very good. Hi. Okay, so as I mentioned last time, we're wrapping up. This is really the last section that we're going to do. So we're starting on the check-in with the obvious thing. We have a matrix and we want to find the eigenvalues and the associated eigenvectors. I used a couple words there that we're actually going to see today, but it's pretty clear what they mean. Okay, so let's have a whack. So let's see. The matrix is, let's see. A is, in my notes it says 1 minus 3, 3. And then 3 minus 5, 3. And then 6 minus 6, 4. Okay. Okay, and of course, when we want to find the eigenvalues, we want to look at A minus xi, where x is a variable, and so we're looking at let's see, that's 1 minus x minus 3, 3, and 3 minus 5 minus x, 3, and 6 minus 6, 6 minus 6, and then 4 minus x. Okay. Now, so when you take the determinant of A minus xi, it's a 3 by 3 determinant, so you could do it in a variety of ways, but one way is that we saw a formula for 3 by 3 determinants, so of course you could use that. That's actually how I did it. I worked it out with the formula for 3 by 3 determinants, and I'll spare you the sort of 10 lines it took me to get it right, and I'll just say that it is minus x cubed, plus 0x squared, plus 12x, and then plus 16. Now, as always is the case with a cubic, it's not, we don't have sort of familiar high school experience from factoring cubics so much, but this is kind of a cooked up problem. So so that is to say, I'm going to look at the divisors of 16, and one of them is the roots. So when you try the divisors of 16, you find that x equals 4. So that's the characteristic polynomial. So that's question 1. And now I find that x equals 4 is a root of the characteristic polynomial. So of course, if it wasn't sort of cooked up to come out to have nice answers, then I'd be in some trouble. I'd have to do something more sophisticated, but that's just beyond the scope of what we're talking about in this course. So it is cooked up, so I got x equals 4. If you factor out x equals 4, if you factor out the x minus 4, then what you get is x minus 4. I did the division, and I got x minus 4 times x squared plus 4x plus 4. And you can either recognize how to factor that, or else you can you could use the quadratic formula. Or you could just eyeball the answer to get a complete of x minus 4, x plus 2, and x plus 2. That is to say, positive 2 is a repeated root. Okay. Okay. So next I need to figure out here what is the what are the eigenvectors, eigenvectors associated with an eigenvalue of 4, and what are the eigenvectors associated with an eigenvalue of minus 2. So I'm going to need a new piece of paper for that. That's not going to fit all that in that piece of paper. So I've got too many papers here floating around. Let's see. Okay, so for lambda 1 equals 4. So I just simply look at what happens when you plug in 4, 4, 4, and 4, and at the resulting linear system. And so what I get is minus 3b1 minus 3b2 plus 3b3 equals 0. 3b1 minus 9b2 plus 3b3 equals 0. And 6b1 minus 6b2 equals 0. And really, I'm just gonna, oops, sorry about that. Just gonna have a whack here at Gauss's method. I took row 1 plus row 2, and also 2 row 1 plus row 3. And I get here, let's see, minus 3b1, minus 3b2, plus 3b3 equals 0, minus 12b2 plus 6b3 equals 0, minus 12b2 plus 6b3 equals 0. So it's straightforward Gauss's method. Obviously, I'm going to do a minus row 2 plus row 3, and that'll finish me off. So minus 3b1 minus 3b2 plus 3b3 equals 0, minus 12b2 plus 6b3 equals 0. And so I get that what here, b2 is 1/2 of b3. Obviously b3 is free, and so I'm expressing b2 as in terms of b3. And then plug that back into the original equation, into the top equation, minus 3b1 minus 3/2 b3 plus 3b3 equals 0, gives me what here, minus 3b1 plus 3/2 b3 equals 0, and so b1 is 1/2 of b3. Okay, so I decided I was going to do out that calculation just to emphasize that there's nothing happening here that isn't routine Gauss's method stuff. So what we get then is a collection of eigenvectors. The eigenvectors are the non-zero members. Eigenvectors are the non-zero members of this vector space. It's all the multiples of b3. It's 1/2, 1/2, and 1 times b3, where b3, of course, is a complex number, and that's called the eigenspace. Eigen is a German word, means something like characteristic of. So that's and the eigenvectors are the non-zero multiples. So b3 can be any complex number, it could be 5 or 12, but it could also be 3 plus I, 12 minus 4i. And then finally, maybe I'll put a line there, if I look at lambda 2 equals 2. Then I get 3b1 minus 3b2 plus 3b3 equals 0. 3b1 minus 3b2 plus 3b3 equals 0. 6b1 minus 6b2 plus 6b3, sorry about the handwriting, equals 0. And again, where the heck did that come from? Well, I have up here, I have this, and I'm simply plugging in lambda equals minus 2. So I'm simply plugging in here lambda equals minus 2. 1 minus a minus 2, negative 5 minus a minus 2, 4 minus a minus 2. 1 minus a minus 2, negative 5 minus a minus 2, 4 minus a minus 2. All right, and then off we go with Gauss's method. So it's obviously here minus row 1 plus row 2, minus row 1 plus row 2, and minus 2 row 1 plus row 3, minus 2 row 1 plus row 3. I'm sorry, it's a little bit insulting at this point in the semester for me to not just say, you know, well, you get zeros there. But so I told myself I was going to do it out long, and here I am. 3b1 minus 3b2 plus 3b3 equals 0, and of course 0 equals 0 and 0 equals 0. So then I'm looking here at b1 is b2 minus b3. So this is a two-dimensional. Remember that minus 2 was, this doesn't look very good, does it? So e equals minus 2. There we go. So remember that this was a repeated root. So it appears twice when you factor out, and we happen to get a two-dimensional subspace, two-dimensional eigenspace. So when all is said and done here, I get v sub minus 2 is the set of all b2 minus b3 and b2 and b1 what? And B3, couldn't read my own handwriting. Where B2 and B3 are complex numbers. And that is to say, you get it's the set of 1, 1, 0, 1, 1, 0 times B2 plus minus 1, 0, 1 times B3, where B2 and B3 are free. So easy to write reals there, but reals isn't correct. So we get a two-dimensional eigenspace associated here with the repeated root of minus 2. Okay? Okay, so the calculations go like the calculations from last time. All right, very good. So now we're ready to finish off. So very exciting. Okay, so we already saw that you get a polynomial, and that polynomial can be sometimes awkward to factor, but that nonetheless you get a polynomial. That's called a characteristic polynomial of the square matrix T. The characteristic polynomial of the square matrix T is the determinant of T minus xi, where x is a variable. Characteristic equation is set at equals 0. And of course, the characteristic polynomial of the transformation T is the characteristic polynomial of any matrix representation. Well, I've already defined the characteristic polynomial of a matrix, so the characteristic polynomial of transformation I can define as the characteristic polynomial of any matrix representation. Now, the characteristic polynomial of an n by n matrix is of degree n. So the exercise there checks that the characteristic polynomial of transformation is well defined. That is to say, it's the same no matter what basis we use for the representation. But you know, we try in these slides to stay away from you know, it's not a small point, it's an important point, but you got to focus on something. You know, Van Clausewitz says, you know, the general who defends everything defends nothing. So too here, you got to make some point, and the point we're trying to make in these slides and in these videos is to give some concrete feel to what these things are about. So the lemma is that a linear transformation on a non-trivial vector space has at least one eigenvalue, and the reason is because in the complex numbers, the characteristic equation will have a root. It might have the same root repeated n times. That could happen, so you only have one eigenvalue, but nonetheless, it's got to have at least one. So any root of the characteristic polynomial is an eigenvalue, and in the complex number, any polynomial of degree 1 or greater has a root. And we remark in the last video, remarking again here, that we switched from real number scalars to complex number scalars precisely for this moment, that we want to be able to factor these polynomials, and in order to factor polynomials, in order to be confident that you can factor polynomials, you need to be in the complex numbers. All right, so we always saw that when we found the collection of vectors associated with that eigenvalue, that we got some kind of subspace for the non-zero vectors. So we're calling that the eigenspace of the transformation T. And the eigenspace of a matrix is defined analogously. So you recall that this particular matrix that we saw earlier has three eigenvalues, 5, 4, and 2. And we got the three different eigenspaces. The eigenspace associated with 5, the eigenspace associated with 4, and the eigenspace associated with 2. And again, it's a small point, but I think it's worth noting here that the eigenvectors are the non-zero members of the eigenspace. The eigenvectors are the non-zero members of the eigenspace, and the eigenvectors are the non-zero members of the eigenspace. So the lemma is that an eigenspace has got to be a subspace. I mean, we've done now, I don't know, half dozen examples, and it's been in every one of the examples, so it can't be a surprise. But anyway, it is. If eigenspace is a non-trivial subspace. And the proof is you have to note that V sub lambda is non-empty. It contains a zero vector for the obvious reason. And then to show that it's a subspace, what you have to do is check closure under linear combinations, and that's easy to see because if you take T and apply it to a combination, then you get in each case the lambdas. So T times zeta 1 all the way down to T of zeta 1 all the way down to T of zeta n gives you lambda times zeta 1, and then the lambdas come out. And so T of the combination is lambda times the combination, and that's exactly the criteria to be in V lambda. Okay, and that it contains the space V lambda contains more than just the zero vector because by definition lambda is an eigenvalue only if there are non-zero solutions. And then we saw before, oops, I'm sorry, I meant to go back instead of forward, there we go. We saw before that if you have three distinct eigenvalues for this 3 by 3 matrix, then you got three distinct eigenspaces. We just saw in the lemma that they have to be eigenspaces. So I get a basis. This is a three-dimensional space. Excuse me, this is a 3 by 3 matrix, and I get three basis vectors. I'll just pick the ones that are laying here. I could take C to be 2, and C to be 5, and C to be minus 7. There's nothing wrong with that, but I'll just take the ones that are here, this one, and this one, and that would be a basis for three-dimensional space. So what I get here is that for any set of distinct eigenvalues of a map or matrix, a set of associated eigenvectors is linearly independent. The proof is a little awkward. I'm going to actually pass over the proof. It's not ugly or anything, but it's just I'm trying to focus on the computations at the moment. So the proof is done by induction on the number of eigenvalues, and the base step is that there are zero many eigenvalues, and so the set of associated eigenvectors is empty, and so the empty set is technically linearly independent. And for the inductive step here, you can see what you do. You just sort of go up by one. But again, I'm going to pass over that in favor of doing the computations. When a person goes back and looks at the book after watching the videos, you go back and look at the book. Person goes back and look at the book. You should look closely at that. Okay, so here's the matrix from above with the three eigenvalues 5, 4, and 2. And I just picked a non-zero vector from each eigenspace to get this linearly independent set. So I'm going to do this annoying clicking back and forth. So the 1, 1, 0, there we go. I just picked the 1, 1, 0, just picked it. So that's fine, you can do that. If for some reason it's convenient to do something else, minus 14, 2, I just picked minus 7, 1, and doubled it. Not for any great reason, I just did. And then over here with the 1, minus 1, 1, just to illustrate what kinds of things you can do, I multiplied through by minus a half. So that's all fine, and that's going to be a basis for R3 because it has three elements. This obviously has three columns, so it acts on three tall vectors. Here's an upper triangular matrix. You'll remember that the eigenvalues of an upper triangular matrix are easy to pick out. This upper triangular matrix has eigenvalues 2 and 3. I know that the eigenvalue 2 is repeated twice, but anyway, the eigenvalues are 2 and 3. And you can pick a vector from each of V3 and V2 that we saw earlier, and there you go, you get a linearly independent set. So the criteria for diagonalizability is if you have an n by n matrix with n distinct eigenvalues. If you have an n by n matrix with n distinct eigenvalues, like this guy right here, this is a 3 by 3 matrix with three distinct eigenvalues. Why then you get a basis of the correct size, beta 1, beta 2, beta 3, by picking a vector from the eigenspace, a vector from the eigenspace for 4, and a vector from the eigenspace for 2. So this is a basis because it has the right size. It's a linearly independent set of size 3 in R3. So it's a basis. And now we saw, of course, it was some time ago now, but nonetheless we saw that if there's a basis that acts in this way, T of beta 1 is 5 times beta 1, T of beta 2 is 4 times beta 2, T of beta 3 is 2 times beta 3, why then you have diagonalizable. So this is our criteria for diagonalizable. An n by n matrix with n distinct eigenvalues is diagonalizable. Okay, now it turns out that distinct eigenvalues, it comes up a lot in practice, and anyway, it gives us a criteria for when is a matrix diagonalizable, and we are interested in diagonalizable, seems like a long time ago now, but we're interested in diagonalizable exactly because we're trying to find representatives of the similarity classes, we're trying to find matrices that represent transformations in somehow the simplest way or a simplest way. And diagonalizable is certainly, diagonal matrices are certainly simple in the sense that, oops, I forgot to slide forward. It's certainly simple in the sense that, that it's very easy to figure out what a diagonal matrix is doing. Okay. So for next time, we're going to talk about the geometry of eigenvectors. The eigenvectors and eigenvalues comes at the end of the course. That always means that a person will be left with some sense of I was busy and I got a little wrapped up. I'm not 100% sure that I understood eigenvalues and eigenvectors. The end of a course tends to do that. And it's also the case that eigenvectors and eigenvalues are maybe not quite as intuitive as some of the other things we do in the course. So I have a little extra section here where we're going to draw a couple pictures. Very good. Okay. So see you next time.
Hi. Okay, so last time we worked through the definition of eigenvalues and eigenvectors and did a lot of examples of those. The check-in is to do one more of those, and then today is kind of an extra section that covers just a very small topic about the geometry of eigenvalues and eigenvectors. Okay, so let's have a whack. All right, so let's see here. I'm looking at the transformation of the plane that takes xy and goes to minus x and 2y. Okay, so pretty straightforward transformation. And I'm asked to first represent it with respect to the standard basis, so some pretty easy bases. So let's see, I've got to figure out where do the standard basis vectors go under T. And I mean, it's, so it's minus 1, 0, and 0, 2. And then I have to figure out how to represent that with respect to the standard basis and represent that with respect to the standard basis. And I'll put it into a matrix and then I'll be done. So it turns out that this is all pretty easy. So representation with respect to the standard basis of T equals, we can do this by I. So how do you represent that with respect to the standard basis? Why, with respect to the standard basis, any vector is represented by itself. So that's how. And how do you represent that with respect to the standard? Well, I hardly got the words out of my mouth when a person knows right away what the answer is. So the standard basis makes the whole job, boy, so much easier. All right, and then question 2 says, figure out what's the story with the eigenvectors and eigenvalues of this matrix here. So 2. So of course, what we're looking at here is we're looking at solving minus 1 minus x, 0, 0, 2 minus x by b1, b2 equals 0, 0. Okay, and what we learned is just to follow through the steps that we learned. I'm not claiming that this is hard to do or anything. I'm just following through the steps that we learned. Is you take the determinant of t minus xi, that's this matrix right here, and you figure out when is it equal to 0. And the determinant of t minus xi, because t minus xi is a diagonal matrix, also upper triangular, is pretty obvious, and it's also obvious how to factor it, that it factors as minus 1 minus x and 2 minus x. And so x equals 2 and x equals minus 1 are the two solutions to that equation, so to that characteristic polynomial, the roots of that characteristic polynomial. So I'm going to write down that the first eigenvalue is minus 1, and I'll find the associated eigenvectors. And then the second eigenvalue is 2, and down here I'll find the associated eigenvectors. So really, other than the fact that this is kind of algebraically easy, it's all the steps that we ordinarily go through. But it is algebraically easy, I have to say. When you put in minus 1 here, whoops, right here, when you put in minus 1, you end up with a system that says 0b1 equals 0, and then 3b2 equals 0. And it's easy to see, of course, how to solve that. Oops, the sun has come out. It's easy to see, of course, how to solve that, and you get here that you get that B2 is 0 and B1 is not 0. B1 is free. B2 is 0 and B1 is free, and so we get that the associated solutions look like this. So it's all the multiples of the standard basis vector E1. Complex multiples, but anyway, multiples. And likewise down here, this is similar. You get, let's see here, when you plug in the root of the characteristic polynomial, when you plug in 2, -1, -2, so you get -3b1 equals 0, and then 0b2 equals 0. And again, we come to the conclusion that b1 equals 0, but down here we don't come to the conclusion that b2 necessarily equals 0. Instead, b2 is free. B2 can be anything. So we're looking here at the space of associated vectors is all the multiples of 0, 1. Okay, so the algebra was remarkably easy for this, and that is, of course, all attributable to the fact that this is a diagonal matrix. Diagonal matrices are so easy. But the algebra is all pretty easy, but the steps are all the same. Okay. Okay, great. Here we go. Okay, so one of the things about eigenvalues and eigenvectors that I remember finding difficult about the topic when I first studied it is that it doesn't seem connected to things. When I studied, let's say, a derivative, well, I'm familiar with rate of change because, I've driven in a car. When I studied integral, well, I'm familiar with, accumulating continuous quantities because I poured water into a bucket kind of stuff. But eigenvalues, I couldn't sort of put my finger on exactly what they had to say. Now, it seems to me that that the ultimate understanding of what's happening there, it comes in studying systems and understanding what the effect of these ideas are on systems. That is to say, that you can look forward to it in differential equations course. But that doesn't prevent a person from still getting a couple of ideas, look at it this way, look at it that way. And we've already looked at it in a couple of ways. In particular, we've looked at it that the eigenvalues are those x's, those values for which the vector gets rescaled by that factor. And I want to take something of a twist on that today and look at eigenvectors and eigenvalues in a related way, but draw some pictures, so some geometry. Sometimes looking at something a different way is a help, doesn't necessarily solve the problem, but is a help in trying to build an internal model of exactly what's happening here. Look at the same thing 3 or 4 different ways. Okay, enough talk. Time for some action. So let's see here. So in order to do that, I need to talk a little bit about the geometry that I'm going to do. I did some of this geometry earlier in the semester, but it was in an optional section, so a person might have missed it. But I'll go back and sort of quickly go over it again. So a defining property of a linear map is that T of RV equals R times T of V. Of course, that's one of the 2 conditions in the definition of a linear map. And if I'm looking at a linear transformation from Rn to Rn, then obviously it has to have that property. So T of a multiple of V is the multiple of T of V by the same factor. In real n space, Rn, a line through the origin is the set of multiples of some vector. So when I'm looking at RV, I'm thinking to myself, well, if I look at RV and let R vary over all possible real numbers or complex numbers here, then I'm looking at a line through the origin. So the action of a transformation, T, is to take R times V to R times T of V, is that the image of the domain line R times V is the codomain line of all multiples of T of V. I used a different letter because I want a person to focus their attention on, you have a line here in the domain and a line here in the range. If you don't imagine that they're the same, if you imagine one's over here and one's over here, I call them R just because that seems more real to people. We could have said Cn. But so you have a domain and a codomain, and I understand that they're both Rn. But so you have a line over here and a line over here. Oops, no, a line over here. So the image of the domain line is a codomain line. Lines map to lines. Lines to the origin transform to lines through the origin. Multiples of V transforms to multiples of TV. And furthermore, the action of T is entirely determined by its effect on any non-zero vector element of the line. So if you want to see what T does to elements in this line, pick some non-zero V, calculate T of V. Why that tells you what happens to every vector in that line. If, for example, this vector here gets turned from, there we go. If this vector gets turned from so to so, then every vector in the line will get turned, to whatever the geometry is there. Okay. If this vector gets flipped around to be the negative of itself, then every vector will get flipped around to be the negative of itself, whatever the geometry is there. Here's an example, simple example. Always a good example to reach for y equals 2x. We've talked many times that y equals x might be too easy an example, but y equals 2x is at least a start. So there's y equals 2x. It's all multiples of 1, 2. All multiples of the vector where the second component is twice the first. So I took a transformation of the plane, and I'm not I'm not a very creative person. I have 1, 2, 3, 4. I picked one that is easy, but not too easy. And it's easy to see there that 1, 2 maps to 7, 10. What that tells you, exactly what this defining property of linear transformations tells you, is that if 1, 2 goes to 7, 10, then 2, 4 has to go to 14, 20. And minus 3, minus 6 has to go to minus 21, minus 30. And in general, R, 2R has to go to 7R, 10R. So again, restated here with a concrete numerical example. That's how a person makes abstract concrete. That's how a person wraps their mind around abstract, is by having a bunch of concrete examples in their head. The action of T on any non-zero vector determines its action on any other vector in the line. I wrote the line as the span of V. I'm imagining that V is a non-zero vector. So the action of T on any non-zero vector determines its action on any other non-zero vector. If you know what happens to 1, 2, you necessarily know what happens to 2, 4, and what happens to minus 3, 6, and etc. Okay, so what does this have to do with eigenvalues and eigenvectors? Okay, here we go. If we want to understand, for example, the plane, every plane element is in some line through the origin. So to understand the action of the plane, and again, I wrote R2 and R2 just because that seems familiar. People close their eyes and instantly think of R2. To understand the action of a transformation on R2 is we only need to understand what it does to lines through the origin, because every point is on some line through the origin. So if I understood what it did to every line through the origin, I'd be done. Okay. On the prior slide, we've shown that to understand what T does to a line through the origin, we only need to understand what it does to one point in that line. So again, I'm reducing the idea of understanding the action of T to the action of understanding what it does to lines through the origin. And I further reduce that to understanding what it does to one point, non-zero, point in that line. Okay. That is to say, summarizing all the previous stuff. One way to understand the action of a transformation, one geometrical kind of draw some pictures way, is to fix a set containing one non-zero vector from each line through the origin and describe what the map does on that set. And then I'll understand, in some sense, what the map does to every point in the plane. So a natural set that has one non-zero element from each line to the origin is the upper half circle. I start there. Can you see that that's a closed-in dot there at 1, 0? And then I take the upper half circle. I go in the counterclockwise direction, as is traditional. And then over here, can you see that that's an open circle? So I'm not counting that twice. The x-axis is not counted twice. There's only one point on the x-axis, namely 1, 0. The colors I'll get to in just a second, but of course this is the familiar description of the upper half circle. Okay, so just a couple of examples. That's all, and then we'll close it out. So here's an example of a plane transformation. Xy goes to 2x plus 2y. And if you saw the optional presentation that we did earlier in the semester, we talked about this. So xy goes to 2x plus 2y. So this is what we call there a skew. And pointing out here what the point of the colors is, can you see that it goes red, orange, yellow, green, blue, indigo, violet kind of stuff. And here it goes red, orange, yellow, blue, indigo, violet kind of stuff. So the red points map to the red points, the blue points map to the blue point, the green point map to this. So a person gets some idea of who maps where because I included the colors. And this was a very easy program to write. I just had the program perform this action on a bunch of points, called some of them red, some of them yellow, like that, and drew it. So something a person could try for themselves. As we move through the upper half on the left, as I move through the upper half circle on the left, the transformation has a varying effect on some vectors. Different vectors get their length multiplied by different factors, and they're turned through various angles. So just as an example here, can you see that the point 1, 0 is turned through an angle that looks, I don't know, it looks to me like a pi over 4, but maybe that's not right. But anyway, the 1, 0 is turned here. In addition to being made longer, being multiplied by a factor of, I don't know, is it 2? I don't know. It's also turned through some angle. Other vectors may be turned through a different angle or rescaled. These ones don't look nearly as far from the origin. Are these indigo? The indigo ones don't seem to me to be nearly as far from the origin as the yellow ones. So the yellow ones are multiplied and turned, but they're multiplied by a much bigger number than the indigo ones are multiplied by. So we get some picture of the varying action of this transformation on different lines in the plane. Okay. So just as an example, I looked at what happens to 1, 0 and what happens to cosine pi over 6 sine over pi over 6. In other words, the point that is at pi over 6 on the upper half unit circle. And I drew. Okay, so the starting 1, 0 is there in red, and the effect of the transformation is there also in red. And you can see that it's made 2 square roots of 2 times as long and rotated counterclockwise by 0.78 radians, if you do the calculation. How about orange? So if you take a cosine pi over 6 sine pi over 6, that gets mapped to here. And you can do the calculation. It turns out to be multiplied by a factor of square root of 7, different than 2 square roots of 2. Right? 2 square roots of 2 is square root of 8. Square root of 7, and rotated by about 0.48 radians, so different than 0.78 radians. So the different vectors are having different effects, sometimes being turned quickly, sometimes being turned only a little bit, sort of stuff. Sometimes being stretched out quite a lot, sometimes not. So if I take a rubber band, I found this circular rubber band in my drawer. I'll make it into an upper half circle just to try to replicate what I'm looking at. Some of the points are rotated. Some of the points are stretched away because points nearby are being rotated at different angles, being maybe made longer, made shorter, kind of stuff. So in the prior slide, what we see is that the map has different effects on different points. Okay, so I drew. I mean, I got a computer, I'm determined to use it. I drew what happens here. The horizontal axis is the angle of vectors from the upper half unit circle. So you see red, orange, yellow, green, blue, indigo, violet. You see the different points here. That's this axis here, the horizontal axis. The vertical axis is the angle through which the transformation rotates that vector. So the red vectors got rotated by an angle of pi over 4. Oh, I didn't point to it. Pi over 4. And some of the other vectors got rotated by a bigger angle. Some of the other vectors got rotated by a smaller angle. One of the vectors got rotated by an angle of 0. Some green vector got rotated by an angle of 0. That is to say, did not get rotated at all. So the action of the transformation on that particular green vector is that t of v is lambda times v. That vector did not get rotated, it only got multiplied. T of v is lambda of v. So we are trying to find a first take on what eigenvalues and eigenvectors are doing here in this particular picture, is that we're trying to find the natural point here, the point where you get a rotation of 0 radians. Okay, so here's a perhaps silly alternative definition, is that a non-zero vector that's rotated through an angle of 0 radians, or else entirely flipped to the opposite side, pi radians, is an eigenvector. The factor by which it's dilated is called its eigenvalue. And I'm going to take the angle of rotation to be in the range of possibly including 0 up to 2 pi, not including 2 pi. I don't want to have repeat angles. Okay, really only another example or two just to illustrate what can happen. Here's the plane transformation that we did in the check-in. You remember x goes to minus x, y goes to 2y. The transformation was pretty straightforward, and it came up with a diagonal matrix, so it was easy to understand. And in particular, it has a pretty simple action on the upper half circle. There's, you can see, for example, that the green vector here, that at x equals 0, y equals 1, gets doubled. Sure, it does. Of course it does. Look at what happens when x equals 0, y equals 1. So the green vector is now twice as tall as it was before. And intermediate vectors, meaning intermediate between 1, 0 and 0, 1, are made intermediate lengths. Some of them, the ones at the beginning, are just about 1 times as long, but the ones at the end are just about 2 times as long. Okay, fair enough. But don't miss out here. Do you see that if you look closely, that's red, but the red here is not at the start, it's at the end. So this vector, the vector 1, 0, gets flipped around to be the negative of itself, minus 1, 0. And again, of course, when you look at it, of course that's true, of course that's true. So another point of the colors. When I draw exactly the same plot, xy goes to minus x2y. And when I draw exactly the same plot, on the horizontal axis here is my name for the vector that is on the upper half unit circle. Namely, I'm naming them by the angle they make with the x-axis, counterclockwise angle they make with the x-axis. And what you see right at the start here is that the point 1, 0 is flipped entirely around, so it gets rotated through an angle of pi. And what you see here is that there is a point right there where this curve, it's not a line, it's kind of a curvy curve. There's a point where this curve crosses the axis. So obviously 2 interesting points in this picture are the point at pi and the point at 0. And I'll remark that this goes, sort of up to, it has a sort of an open circle at minus pi. So one upper half circle vector is rotated through an angle of 0 radians. And of course, that's the thing we're interested in. And of course, that's what happens to vectors on the y-axis. They get not rotated at all, they get doubled. Okay, so what happens is that t of E2 is 2 times E2. That's the definition of eigenvector, is that it only multiplied, nothing else. Okay, well that's exactly the picture that we're drawing. Only multiplied, not turned. And we're also interested is those vectors that are multiplied by, those vectors that are sort of turned a full pi. So those vectors that are multiplied to be back on their own line. So this vector is not turned in the sense that it is mapped back to its own line, back to the x-axis. I don't know, I always write 1, 2, 3, 4 and type it into the computer and see what happens, and so I did. So what kind of crazy things can happen with 1, 2, 3, 4? Well, what you see is that this half circle has become a half ellipse. What you also see, did you notice that again the direction has turned? There is red, there is red. So here to go from red, orange, yellow, green, blue, indigo, violet, you go counterclockwise. Here you go red, orange, yellow, you go clockwise. So that's kind of interesting. One thing that, again, you notice is some of the colors are stretched out, and some of the colors are compressed. So you can have that the angle through which vectors are being mapped is changing. Okay? And I drew the picture, have computer will draw. And obviously what's of interest here is that plotting the angle of each vector in the upper half unit circle against the angle through which it's rotated, I got the computer to draw it, gives that one vector has a rotation of 0 degrees, 0 radians, there we go, and one vector has a rotation of pi and minus pi are basically the same thing here, but anyway, pi radians, namely this vector right up here. And we know how to calculate the eigenvectors for this transformation. I'll leave that to you. But the point is that we find the two interesting spots on this graph, where the rotation is 0 and where the rotation is pi. So in both cases, the vector is mapped back onto its own line, mapped back onto the line that it defines. So one geometric picture of what's happening with eigenvalues and eigenvectors. What the heck are we talking about? Is that we're interested in those vectors that the action of the map is to map them back onto the line they define. I know that doesn't explain why is it so interesting, but it's at least one way to look at what's happening here. Okay, very good. So very exciting. That brings us to the end. We're finished now looking at the entire semester's worth of work. This is where our course would traditionally end. So I hope you enjoyed it. Hope you found it useful. Very good.